oranges with apples, and then like there are different training recipes. There are a lot of factors that could contribute to the to this robustness in VIT. So we really want to ablate and understand where these robustness come from for better understanding. So in the second part of the talk, I will delve deeper into VIT's robustness. So I want to start from something that's almost like a pre-deep learning era stuff, visual grouping and information bottleneck. And if I'm not sure how many of you actually read these papers, but I came from a background where I read all these wonderful papers from Jitendra and Berkeley, and these before the deep learning came out. The visual recognition community, a lot of the papers were talking about the cognitive process of like visual grouping guided by the Gestalt similarity law, and people talk about segmentation, and people talk about the grouping of pixels. And why is this important? Well, because visual grouping is actually a process, a phenomenon that is at the core of mid-level vision. And mid-level vision is the bridge that connects the low-level vision to the high-level vision. But it is very difficult to study this part because for high-level vision, we know it's a semantic output. For low-level vision, we know that our retina cells are like Gabor filters. It's like boundary detection. It's like detecting the boundaries, detecting these motions. But for mid-level vision, it's been really like a mystery. I still remember at CMU when I was studying Alyosha's course, he talks about this mid-level vision. It still fascinates me today and still influences my research. And what's really happening in the mid-level vision is that there is this like when object-centric representation and this object-level representation with pixels grouping into objects, and with this, this is a bottom-up process, and it's really important for it's kind of the source of the generalization capability of human. And in the old days, if you look at the people doing segmentation, actually a lot of times people kind of formulate the problem as a graph-based problem. So you can represent the image as graphs, and then for every pixel you can consider it as a node, and there are edges that connecting every pair of the pixels that represent the similarity of the pixels. And if you want to segment the image, and basically it's a graph cut problem where you want to cut the graph into pieces by looking at the weakest links. So this is in the old days how people do this. But I'm going to come back to the talk because we are talking about vision transformer, and here's the connection. So if you look at how people usually do it, and a very popular technique is a spatial clustering. So if you look at the early days, like normalized cut, spatial clustering, and all kinds of different graph cut algorithms, they kind of all point to this spatial graph theory using eigenmaps to find the significant component of the clustering of the clusters of the data. So for example, imagine these are the feature space distribution of the pixel features. And what people usually do is you construct a pairwise affinity matrix. And from the affinity matrix, you can get the graph Laplacian, which is nothing but basically a normalized version of the. And then people do is you take the eigen decomposition. You can basically use eigen decomposition on the affinity on the graph Laplacian, and you find the top several eigenvectors, and these top several eigenvectors, they're actually the main components of the clusters. And if you look at, if you treat every row of these eigenvectors as the new data, they are actually the data that's actually projected into a kernel space where these originally non-compact clusters, they suddenly become compact in the kernel space where it's very easy, linearly separable, and easy to perform the clustering. So this actually indicates some very interesting things. So it means that actually these special clusterings, they are like kernel k-means. They transform the data into a linearly separable space where the code becomes very clean and very good. And if you look at this form, do you think it's familiar, this affinity matrix? Well, it does look familiar to us, and very surprisingly, I personally don't see a lot of people talking about this, but maybe I missed something. Maybe I was missing, but it seems that there is an interesting connection here. So if you look at the self-attention, where is basically trying to also model these pairwise affinity matrix and normalize with the softmax. And this normalization of the softmax is also very similar to the graph Laplacian, although there are some differences. And then if you look at the form, it's actually quite similar to this eigen decomposition, except that everything in the VIT is like, of course, these two are not exactly the same. You cannot say they are exactly the same because this one is like explicit eigen decomposition. This one is like driven by your learning goal, right? However, it's really when I look at this, I can't help to notice the connections. So indeed, people found very interesting emerging behaviors from the VITs that further strengthen these kind of hypotheses. For example, this Dino paper from Facebook AI research, they found that if you use self-supervised learning to train VITs and interesting these behaviors such as the segmentation of the foreground object emerges. And these indicate that, well, it is possible that VITs kind of capturing the mid-level representation in a correct way. And in this work, we kind of wonder whether there are some correlations between the grouping phenomenon and the robustness of the network. If that is the case, then that is very, very interesting because it's echoing what people are doing in the old days. So what we did is we look at the number of significant, we look at the number of significant eigenvalues. If we take the tokens from the VIT and perform some sort of eigen decomposition, we can see there is actually a very significant correlation between the number of significant eigenvalues versus the robustness of the network over different blocks. So especially in the mid-level blocks, you see there is a very significant improvement of the network in these areas, and then there is a very significant drop of the of the zero eigenvalue. There is a significant drop of the significant eigenvalues. So this means that grouping is happening here, and while grouping is happening, the robustness is also increasing here. But if we go back to examining the same thing in ResNet, let's say ResNet 50, the behavior doesn't, we don't observe very similar behaviors. So if we further visualize the clustering of the token, and we can see that this kind of clustering result also refines across different blocks. So you can see better and better segmentation. And notice that this segmentation from the VIT is actually not supervised by mask. It's just naturally emerging when you are training on ImageNet. So this is very interesting. And actually, in the paper, we kind of further delve deeper into the relation to information bottleneck. So what we found is that actually in the self-attention can be written as one step of the iterative optimization of the information bottleneck goal. So if you look at the information bottleneck, the objective, if you kind of optimize it iteratively, you can rewrite it into the self-attention form. And this is very interesting. So you can, for the VIT, you can kind of think of it as a layer-wise repeated, like promotion of this information bottleneck. And we all know that information bottleneck promotes the clustering. So that this kind of explains or echoes why these kind of clustering results, this segmentation kind of emerge in the VITs, because the self-attention kind of promotes the clean code, which are very which show very compact cluster structures in the feature space. And this one shows basically a trinity of the three things: the visual grouping, information bottleneck, and self-attention. So they kind of form a trinity that helps that has a process with a robust generalization. And of course, actually in VITs, we don't just use vanilla self-attention. What we use is a multi-head attention. And multi-head attention actually can be interpreted as a mixture of information bottlenecks. You have several information bottlenecks that in parallel with each other. Each one is kind of capturing a region, different regions, different parts of the object. And in this work, we actually are interested in the robustness versus the number of heads. We actually did a brief study, and we found that at some point there is a trade-off between the clean accuracy and the robustness. And if you keep adding the number of heads, and actually it's getting more and more robust. However, there's a drop in the clean accuracy at some point. So because the multi-head self-attention can be interpreted as a mixture of information bottlenecks. So the important thing is actually how to aggregate them, because at the end of the network, people usually just use a all MLP block. This all MLP block is kind of just using one-by-one convolutions followed by some nonlinear transform, then another one-by-one convolution to aggregate the information from different heads. However, so here's actually the design of the fully attentional network. So we think that this channel aggregation part is very important, and because you are capturing this grouping information when you are doing this token mixing, when you are capturing these tokens, then it's important that you come up with a design that can capture these results more holistically, instead of using the MLP block to make the decision locally. So what we come up is a attentional design at the channel processing part, and basically you can think of it as adding the weight to the channel when you are doing the aggregation. You kind of highlight some of the channel because they kind of capture more important information, and then you de-emphasize some of the channels. And this, when you are computing these channel attention, and actually there are different ways you can do it. A most standard, straightforward way you could do it is something very similar to XCIT from Facebook. Like you just apply a standard channel attention, and you should be able to do it. But an even better way we do it is this something called efficient channel attention, which is this figure. Instead of using, because when you are using the channel attention, the standard channel attention, it requires again a quadratic number of memory with respect to the number of channels. And at the end of the network, you have a lot of channels. And with this kind, it increases the complexity and memory. So what we did is something a little bit similar to squeeze and excitation. So we first take an average of the channel and basically forming a prototype of the channels, and use this prototype to attend different channels to obtain the weight at different channel, and use this weight to as a channel attention vector to basically to reweight these channels before going out. So this is basically the design of the fully attentional network, and the reason why this one works is because with this channel attention design, you kind of have a more holistic understanding of different channel that is you are taking more effectively using the grouping information I just mentioned previously. So here are the main results of this work. So our work actually achieves very competitive performance on both image classification and downstream tasks. So image classification, so just want to mention this is similar to ConvNeXt. It's a general purpose vision transformer backbone. And when you talk about backbone, you have first do image classification, and then you do downstream tasks like you use the model to transfer to segmentation and detection problems. So on the image classification problems, we achieved competitive performance compared with a ConvNeXt model. For example, with the ImageNet 22K pre-training, so our model achieves 87.1% accuracy on the clean data, and outperforms the ConvNeXt with a comparable model size. And actually, the improvement on the robustness becomes very significant. So we achieve 35.8 MCE, which is a state-of-the-art result on ImageNet C, and outperforms ConvNeXt with a very significant margin, as you can see here. Our model actually outperforms the largest model of ConvNeXt, which is like more than double the size of our network. And actually, you can also see that the fully attentional network, it kind of promotes very good mid-level segmentations from when you are training on ImageNet. These segmentations, they emerge as a result of the label supervision. There is no mask supervision. They just emerge naturally. And you can see more examples here. The second columns are from the proposed network. And then we also transfer these results to semantic segmentation and also object detection. We compare both on COCO and cityscapes and their corrupted version. So we can see that the robustness, so we compare with SegFormer first on Cityscape C, on both Cityscapes and Cityscape C. So an advantage of the model is that usually robust models, they will need to sacrifice the clean accuracy to exchange for the robustness. But actually, in fact, we don't observe this. The good thing is like your clean accuracy will always be slightly better than state-of-the-art models, but your robustness can be much better than these state-of-the-art models. And it's really important for safety critical applications. So you can see, like, for example, here on the clean COCO, our clean accuracy actually outperforms the both ConvNeXt and Swing using the Cascade RCN as a head, and so these actually shows the potential, or these potentials of the network. And we have made the code available. It's already, we are still in the process of releasing the pre-trained models, but the code itself is already available on NV Labs. And so this concludes the talk, and thank you very much for attending.
Okay, we have 7 minutes for questions, and after that, we'll have the spotlights, and then we'll have the coffee break and the poster briefing. You can come to the front if you have to ask any question.
I was wondering if since this is a noise and consisting, it seems to be able to be applied not just as a layer but on the other layers as well. Have you tried something like that and see if it's
actually, this is applied at every block. So it is actually a very modularized design. So whenever there is a channel aggregation, so we apply this. Yeah.
The other question, I guess, for that is have you tried only using the faculty class boxes because the information of bottleneck was already there in other layers. So only the last layer is didn't have that additional bottleneck.
Yeah. That is actually a good question. So one thing I forgot to mention very clearly in this one is actually the design contains in our design we have several different backbones. So we have the one backbone which is similar to DIT like or VIT like straight trunk, and then there is a hybrid backbone. That one shows the best performance, and it's actually echoing a lot of the talks happening yesterday. For example, Sai Ning and some other people, they suggested, okay, there is a converging design between CNNs and VITs. And actually, one of our best performing model is this hybrid design. And the hybrid design is we take the convolution blocks from ConvNext as a first few convolution layers. And then following that, we will have this attentional design, fully attentional design. And this works best because it's you don't have to have these attention designs from the very beginning. Very similar to human, like we have convolutions in our eyes. You don't have to do it. You don't have to have global receptive field from the beginning. Just use convolutions, and it's actually more efficient and works better. So to answer your questions, yes, I think this actually works better. So you don't have to be last layer, but last a few blocks. Yeah.
Okay. Thank you for your awesome presentation. So I have one question about the properties of the VIT. So,
sorry, which page?
I forgot about the properties of the VIT.
Oh, VIT, okay.
Do you think like the VIT one is gonna be vulnerable or gonna be attacked by some well-designed adversarial learning or something like that?
VIT is adversarial learning.
No, I mean like the VIT is gonna be like attacked. Can it be attacked by some well-designed adversarial learning or adversarial attack?
So I have seen works. Actually, if you look at the state-of-the-art results on papers with code before FAN, there is another work. Actually, the second best, actually the third best robust network. It's using adversarial training. I think it's from Google, from Deqing, one of my previous colleagues, and they use adversarial training to train the network, to train the VITs, and they show this adversarial training can improve the robustness of the network. Yeah.
Thank you.
You're welcome.
Thank you. I have a question about this attention map that you show for the VIT. So in this figure, you can see that it's focused entirely on the object. Does that mean that the VIT uses all the object information for classification and it just doesn't look at specific properties of the object for classifying. For example, here you can potentially classify this based on the redness or the red part of the object. So do you have any thoughts on that?
Could you repeat the question again? Sorry, I wasn't capturing the thing.
So in this attention map, it focuses entirely on the object.
Yeah.
On the whole object.
Mm-hmm.
Does that mean that the VAT uses all for classification, or and it doesn't look at essay parts which are significant parts? So
I see. I see. Yeah. So I think this is the result after the aggregation of different self-attention heads. So if you look at each self-attention head, they kind of capture different parts of the object. We did some visualization, and that was indeed the case. But after you aggregate the information, it seems it's quite, so the result you are seeing here is like you already aggregate different parts and it's capturing the whole object holistically. Yeah.
Thank you.
Thank you very much.
Thank you.
Thank you.
Yeah, I can start. Here's the mouse. This is blocking a little bit. Okay. Sorry for the pause. So during training, we trained the group VIT jointly with the text encoder. We are on the noisy image text pairs, just like clip, and the grouping automatically emerged without using any mask annotation. And during inference, we could therefore transfer these groups to semantic segmentation without any fine tuning. We just extract the group first and then assign the label to each group by given the test category of the testing data set. Here we show the details of group VIT architecture and show how we group the image into different parts. Given an input image, we first project the image, split the image with into patches, and then project them with a linear layer. Besides this projection gets the gets the image tokens, we also randomly initialize a set of group tokens, which are learnable. And we concatenate these tokens together, feed them into the transform block and the grouping block. In the grouping block, we will calculate the similarity between the group tokens and the image tokens, and assign the image tokens to the groups. Here's the visualization of the grouping assignment. Each group token actually represents one region in the image, and this region is image conditional and learnable. This is actually the stage 1 grouping. After the stage 1 grouping, we could further grouping on top of this stage 1 grouping result to merge the small regions into larger ones. In this process, we are actually merging the irregular shaped groups and the irregular shaped visual concept in a hierarchical way. And this is the second stage grouping. After the second stage grouping, we will contrast it with the global feature of the output by the network with the text embedding of the image pair. Sorry, of the text pair. Here is some additional visualization. This will help us step deeper into what have been learned by the group token. We visualize the attention area of each group across the different image on the data set. And interestingly, we found that some tokens will focus on some specific concept that match our mindset. Here, in this token, it's a block. It's a group token 5, and it's always attend on the human eyes or animal eyes if there's eyes in the image. And this another token will focusing on the limb of the animal or human if there's a hand or the feet of the animal. It's very interesting that if the human is present image, human has hand, and this token will focus on the hand. But if the animal is present image, most animal does not have the hand like human. This token will focus on the feet like the bird and the dog. This is the stage 1 group tokens. And in the stage 2 group tokens, these tokens are more likely to focus on some high-level concepts, such as the body of the human and the face of the human. And here we show some quality results on different test datasets, such as the Pascal VOC, Pascal context, and the COCO dataset. Our model could generate reasonable groupings regardless of the dataset we are using. And this model does not require fine-tuning all the training set of the datasets. To summarize, firstly, the group VIT explores self-attention in the transformer layers and hierarchical grouping the visual concept into irregular shapes. And this is also the first work that tries to learn from text supervision and transfer the grouping to the semantic segmentation without using any mask annotation. And lastly, we've also found that this grouping has a potential to generalize very well to different testing data sets of different categories without any fine tuning. And our code is also publicly available. The main poster session will be in Friday 4.1. Please visit us at post session at that time. Thank you very much.
Hi everyone, good morning. I'm Hakan Biran, so the first slaughter couldn't make a way home because of visa issues. So today I will talk about cross-domain few-shot learning with task-specific adapters. Okay, so in few-shot learning, our aim is to learn a classifier from few images only for previously unseen tasks, a set of categories. And here you can see that, for example, this is done in a way that we get a support set during meta testing period. Like so, we have 3 categories with 3 images each, and given a query image, we would like to classify it to the one of the correct to the correct category. And so, previous work, broadly speaking, split the learning process into 2 stages. In the first one, meta training, because we do not have many images in this stage, we go to a big data set and then pre-train a classifier, feature extractor. And in the meta test stage, we adapt the classifier to the this task with few images. And typically, we learn just a classifier. We freeze the rest of the network and learn a classifier on that. So recently, the focus of the community has shifted to a more challenging setting where during meta training stage, we get some domains and then we learn a feature extractor from them. But in testing time, we are getting support images from previously unseen domains. So this is very challenging because we have, for 2 reasons, we have a large generalization gap. So here you can see, for example, these are the train categories and these are the meta test categories. They look completely different. Another problem here is, another challenge is that we have very few images to close the domain gap. So at the meta test time, we have very few images to learn and close this gap, domain gap. So the existing solutions, again, in meta training stage, go to a large training set from which consists of multiple domains. You train a classifier on them. So this is a task agnostic model. And this time, instead of just learning the classifier, we only learn task-specific adapters, because this is a more data-efficient way of doing it, because you cannot train the whole network on few images. So our contribution is we systematically study this task-specific adapters. So previously, there were many works with different design decisions. So here we do a systematic study of how they should be estimated, this task-specific adapters. how they should be connected to a network, and how they should be parameterized. And in addition, we also show that the optimal setting outperforms the state of the art, especially when there is a big domain gap between train images and test images. Okay, so let's start with an overview of what is task adaptation. So typically, we have a, let's say, a RESTnet with multiple modules and blocks. And so we have a support set, and then in the we use a nearest mean classifier, so which takes the features, takes the images, extract features, and then take their mean per category, and then find the assign the query image to the closest mean to that category. So as I mentioned, so the training the whole network on FIB images is like too expensive, and then it will overfit. So the recent papers add some compact adapters, which is indicated with R alpha with these green blocks. So we just freeze the network and learn them. So the first question we ask in the paper is, how should we estimate them? So these adapters. So one way of doing that one is having a meta network, like hyper network kind of network. It's shown with n lambda here. So it basically takes the n lambda and then outputs the weights of the adapter, basically. So it's estimation done through a network. And we also look at other strategy, which is like maybe more straightforward. So we just add adapters and then learn them on the small support set in the second on the right image. And we also study how they should be connected to the network. For example, you can connect them in a serial way. So given, for example, a 3 by 3 block in RESTnet, we can just add them in serial way. So then it's like composition of two feature maps, two operations, convolution and the adapter. And also we also connect them in a residual way. So this is inspired from residual networks. The advantage of this one is obviously you do not make the network deeper. You make it just parallel, and then gradient flows in a better way. And finally, we also look at how they should be parameterized, the adapters. So one way of parameterizing them, just as simply doing a channel-wise scaling operation, and this is more compact and efficient. We can also have a matrix multiplication. So this is given a feature, given a coordinate in a feature map. Okay, so in short, what we found best working optimization, best working configuration was directly attaching the adapters instead of estimating them through another network, connecting them in a parallel way, and then using matrix form parameterization. And then we evaluated our method in the augmented metadata set, so which has 8 data sets for train, well, and test, and then in the for test only, we have unseen 5 data sets, and we use our previous model for the backbone, URL backbone, and we evaluate average classification accuracy for various few-shot tasks. So here you can see the seen domains and unseen domains in this data set. So in our analysis, first we look at how they should be estimated, and then we found that learning them directly from the data, optimizing them on the data is much more effective. So it's quite noisy to estimate them through a network, directly splitting the parameters of the adapter. Second analysis we had is they should be connected serial or parallel, and then we found that parallel connection is more effective. Finally, we look at channel-wise and like to their parameterization, and then we found that matrix form is better, though channel-wise has less parameters. So this also offers a good trade-off. Okay, so after we found the best configuration that I shown you in the previous slide, we compared to previous work, state of the art, So here I'm showing the average over all the categories. So we obtained the best results, significantly better results than the previous work. Okay, so this concludes my talk. You can find the code and more material in the link here. Thank you. Yeah, I see. Back there. It's bigger than I thought it was. The center here. I had sort of vague memories from iClear, but I didn't feel it was there.
That was your right.
Yeah. Yeah, that's right. And
I think they kept us on one side.
I think that's right.
Yeah, 'cause I didn't realize this thing extends all the way across.
Yeah, me neither. Yeah.
But who's coming here? Perhaps it's coming here.
NeurIPS, yeah. But NeurIPS had this concern that this, whatever space they have, which might be everything, they thought it might still be too small. But it's hard to predict because, of course, like you can't, maybe we won't go back to the actual numbers we had before, but maybe we will, like who knows? So I don't know what the CVPR looks like.
Especially in December, but I can tell you this, the average age of participants went down. So a lot of these were significant.
Oh, yeah.
Just fear of COVID.
Yeah, that makes sense.
Hi, welcome back. It's my pleasure to introduce the next invited speaker, Hugo La Rochelle. He's a research scientist at Google Brain and a lead at Montreal Google Brain team. He is also a member of Joshua Benjos Mila and adjunct professor at Université de Montréal. He has made a number of contributions to the foundations of deep learning, including unsupervised pre-training of deep networks, the noising of the encoders, zero-shot learning, domain adversarial networks, and meta-learning for few-shot learning. He was program chair of iClear 2015, 2016, and 2017, program chair for NeurIPS 2018 and 19, and general chair for NeurIPS 2020. He is a member of the boards of NeurIPS and ICML, and was founding member of the board of ICLR. Presently, he co-founded the Transactions of Machine Learning Research.
All right, thanks for the introduction. Thanks for inviting me here. Good morning, everyone. So this is my first in-person talk in forever, which I guess is probably true for a few people who will be presenting. So I might be rusty, so bear with me. But at the same time, I feel it's also one of the few opportunities we get to kind of talk to each other in person. And so I'm gonna try to keep this short and put in some opportunities for exchange and discuss. And hopefully, even it could be during the talk. I don't mind if someone comes up to the mic and wants to ask a question. Or if you want to wait at the end, that's also fine, but please don't hesitate to interrupt me. And in many ways, the talk that I had in mind is kind of meant more to be brainstorming in nature, where I'm going to try to sort of put forth this framing of thinking about how we solve few-shot classification problems through the lens of something I call recycling deep learning, which is not a formal thing, but it's more like a point of view, which I think can be interesting to sort of use to think about all the work that we do and how we might want to move forward. So I will do that as soon as I figure out how to advance my slides. There you go. All right, so what I'll focus on and the type of task I have in mind for this full talk is illustrated here. It's we're going to think about few-shot image classification. That is, we're given a training set that's very small. In this case, it's the extreme case of one image per class, where we have 5 classes. And in few-shot classification, we're interested in methods that can give you, for this training set, a classifier that will generalize well to new examples on some test set, as in here. All right, so that's the kind of problem that we're hoping to solve. And we're going to do that through a form of transfer learning. And I think a lot of people, certainly in this room, but I think in general, actually in our field, more and more are very much interested in doing that. I think this has been a research agenda for me for a while, but I think for many others as well. We acknowledge that you're relying on a lot of labeled examples for every single task we'd like to solve with deep learning is not really reasonable. And also scientifically, it's kind of interesting because we know people also learn tasks, from small amount of examples or experience. And so there seems to be also a gap between the systems we've engineered and our own ability as humans to learn new tasks. And so there's something there also that's also interesting to study beyond the technology that would be beneficial if we could do few-shot learning effectively. And one of the most prevalent approach is what I've referred to here as the pre-train plus fine-tune approach. In fact, it's so prevalent that when people say transfer learning, oftentimes they actually mean this. They sort of equate transfer learning to pre-train plus fine-tune approach, which is a little bit of a pet peeve of mine. I think transfer learning is much broader than this, but pre-train and fine-tune is definitely like one of the most robust and popular way of doing transfer learning. And in that setting, how do we approach solving a downstream task that has few examples? Well, upstream, we sort of assume that we have a lot of data for some task, and then we're going to pre-train our model with, say, regular training. So oftentimes in image classification, that means just training on ImageNet, and we have a lot of images from ImageNet. So we train on that upstream task. The upstream task here would be ImageNet. And then we effectively recycle the weights that we produce from our pre-training. And we use that to initialize the model that will then fine-tune on the task that I will call the downstream task, that in few-shot learning has very few examples per class, if it's a classification task. And so I've introduced this term here. I've used this term recycling. And we're going to sort of play with that, and we're going to encourage you to think about it in this way in this presentation. Because in a way, it is a form of recycling. We're taking something that was meant for something else, and we're going to reuse it, to repurpose it for a new purpose. Hopefully, sort of, taking advantage of the resources that went into creating the first artifact, which was the pre-training, so as to limit the amount of resources we need to deploy for the new purpose, which is our downstream few-shot class. And now, why is that potentially useful to sort of play with that concept and think about things in this way? Well, I think one possibility where I think this is maybe interesting to sort of inform our point of view is that when we think about transfer learning, I think we're oftentimes mostly concerned about trying to not rely so much on a lot of labeled data downstream. And that's the resource that we're trying to save. We're trying to avoid requiring so many examples downstream. But in fact, there's, data is not the only expensive resource when we're trying to solve a downstream problem. Compute might also be a problem. Memory might also be a problem. And so by sort of using this term, this presentation, I'm trying to encourage us all to sort of think beyond that. And think about generally what kind of resources come into when we're training these models, and trying to think about the ecosystems of models that we're training. How can we sort of be resource efficient, whether it's labels or data, compute, and memory, and so on. So I'm hoping that, by just, stating this term or using it, it increases our focus on when we do pre-training of wanting to create as much value for many different downstream tasks. I think that can sort of legitimize putting a lot of compute in pre-training if it turns out that in the end, it helps a lot of other tasks downstream. It also encourages a reduction of compute and memory for resources used downstream. So an example that will sort of come is that when we do pre-train and fine-tune, we need to effectively copy the weights and then fine-tune them. And so we need to instantiate a new copy of our classifier in the downstream task. There might be settings where that's not really reasonable, where we need to introduce a small number of weights because we have some memory constraints, perhaps in terms of storing all the weights for the different tasks that we want to solve. And so that's something to think about. And generally, I like the idea of us to think about transfer learning more in terms of like, we have a lot of different tasks that as sort of engineers of machine learning. We would like to solve with machine learning. And so let's try to think about how do we take the somewhat limited amount of resources we have to serve all of these different tasks that could be solved with deep learning. You know, this is partly why we introduced recycling in our economy, is that we kind of felt like we had a lot of different purposes, or, you know, this material was useful for a lot of things in our society, but the amount of resources to produce all that material was somewhat limited. So we sort of thought about recycling to try to allow for all of these purposes while relying on less resources. So I think we can have this kind of mindset as well here. And this is kind of what I'm suggesting we maybe have in mind in this more kind of speculative presentation here. And it's kind of interesting because in a way, I think a lot of researchers already kind of rely on transfer learning for forms of, through sort of a motivation that's kind of related to recycling. People will download some weights from an ImageNet pre-trained model, partly I think sometimes because it speeds up, you know, training that model in that downstream task because it's more or less already trained. I was kind of, but the word recycling had never been used before. But then recently I saw in DeepMind's Flamingo paper, which has been really, really interesting, in their sort of broader impact statement, they kind of mentioned that because they're reusing some frozen language models and visual encoders in their work, and they kind of talked about that as doing a form of recycling. So I thought maybe that term is not completely crazy. At least some people seem to think like intuitively, maybe it makes sense. And so really, I'm not necessarily strongly advocating we should do this, but I think it's kind of interesting in the context of a workshop to kind of think differently about things and see where that brings us. And so, but going back to pre-train and fine-tune, that sort of suggests, well, you know, should we sort of expand the kind of tools that we have for doing transfer learning because other approaches might be more beneficial from other reasons than, well, they allow us to generalize better from the same amount of small amounts of data downstream. And in many ways, I think there's probably a lot of people here who actually already know that it is fine-tuning is not always the right thing to do. It's not always the best thing to do. I'm just giving you this example, which is quite relevant because this is going to be presented at CVPR this year as an oral. This comes from my group, Cristina Vasconcelos, who's going to present that on Thursday. And this was in the context of taking a pre-trained ImageNet backbone and using that for object detection. And what they had shown, if you freeze the backbone, you actually reduce drastically the amount of compute that's required for solving that downstream task. And interestingly enough, also actually, it also brings oftentimes for different types of backbones an improvement in terms of performance, in terms of the quality of the solution that you reach. Okay, so clearly that suggests that there's more to pre-train and fine-tune. And in this particular case, it's even better motivated by the fact that it requires less compute to actually solve the downstream task. All right, so my goal really is not to go really deep into a very specific technical result. I kind of want to present a few research vignettes for us to kind of think about different directions that are sort of taking different approaches to pre-train and fine-tune as a way of recycling some pre-trained backbone. And so I'll try to go fairly quickly over these, but I'm happy to answer more specific questions later on. And so I categorize these into two different sort of categories of approaches. The first one I'll go through is to think about approaches where instead of trying to recycle the representation that's given to you at the end of the backbone, to actually think about some pre-trained backbone that's providing you with a set of representations, a multi-layered representation, and actually try to leverage the richness of that, as opposed to just assuming that the representation only lives at the top. And we'll see how that can be beneficial. And then the other one, which I think has not been looked at as much, is in a setting where there might be multiple pre-trained backbones that are available, multi-sources from which we can do some transfer learning. How do we combine that into a solution for a specific downstream task? And I'll talk about some of the ideas that we explored recently about that. Let's start with the first one on recycling different levels of representations. So if we're particularly interested in having a downstream solution that doesn't require a lot of memory or in terms of storing the solution and compute as well, linear probe is a really attractive approach. If presumably you know what linear probe is, or maybe you know it through some other name, but essentially what it corresponds to is you just take your pre-trained backbone, you don't change it, you freeze it, and you only train a head on top for your downstream classification task after perhaps having trained so the pre-training, I'll assume, has been done on ImageNet, and then we have some downstream tasks, and we have a bunch here that are listed at the bottom, and you just train a linear classifier on top of the top representation. And somewhat surprisingly, it turns out that fine-tuning more or less always does better than that, even in the few-shot learning setting, even in a setting where the amount of training examples are available for the downstream task is actually quite small. So in this figure, you can just pay attention to fine-tuning, which is the solid line, and then the dotted line, that's linear, or that's linear probe. And you can see it's essentially always below the solid line. And what's interesting is that the gap increases in terms of accuracy of both, the more different the downstream task is. And intuitively, that sort of makes sense. The more different the task is, the less appropriate might the representation provided by ImageNet training be. And this is where fine-tuning might be beneficial because it allows you to adjust the representation. And so in this work, which we call head to toe, this was led by Utku FC, we aimed at trying to have something like linear probe that is competitive with fine-tuning. And our sort of working theory was that actually fine-tuning, what it does when you fine-tune on the downstream task is that it takes some of the very informally information that's captured by early layers and figures out a way of sort of bubbling up that information to the top representation. So one thought was, well, maybe if we allow a linear probe to access the internal representation directly, maybe that's all it needs really to sort of catch up to fine-tuning. And in effect, that is sort of what we're seeing. So just to visually see this, linear probe is this. We just train a linear classifier on top of a frozen representation. And the head to toe here is a linear probe that has access to the internal hidden units. And there are a lot of internal hidden units. So we're going to heavily regularize our linear probe. And specifically, we're going to apply some form of sparsity so that it effectively selects different internal hidden units for the downstream task. And what we find here, you have the performance of head to toe minus the performance of linear probe. And we do find that generally it actually does better. In particular, it does better on these tasks that are very different from ImageNet, either because they're sort of synthetic or the images are not so natural or the concepts are represented are quite different. And just in numbers, so you know that I'm not lying, essentially, we see numbers here evaluated on the VTAB benchmark. So this is a benchmark where people are assumed to pre-train on ImageNet, and then you have a lot of downstream tasks that are categorized based on whether they're natural, specialized, or structured. And what's interesting, you have head to toe here, and actually where it does particularly well is on these really out of distribution structured tasks that are quite different from ImageNet. And overall, on average, it does better than fine-tuning. These results were obtained by training on by using a ResNet 50 backbone. And if it turns out it doesn't quite completely catch up to you, you can also do a first phase of head-to-toe pre-training of the linear head, and then actually start from that and do more fine-tuning of the full backbone if you have the resources required to have an entirely separate classifier with its own weights. We've actually found in our experiments in the paper that we kind of had to do this for VIT backbone for some reason to be able to catch up to VIT and do better. All right, but I'll stop here. I don't want to go too deeply in this, but the idea here is to say, well, when we train a backbone, maybe it's not just the top representation that's useful. Maybe there's something more in this backbone that can be extracted for solving other downstream tasks. And I'll briefly mention another piece of work that is trying to get at this, leverage this concept or this idea that's going to be presented this week from my colleagues at Université Laval, and the first author is Armen Afraziabi. And you can go check it out. But essentially, in this setting, we looked at computing a distance metric between examples in order for us to do some classification, not by comparing the distance between just the top layer, but actually allowing to do comparisons between the intermediate layers of both pre-trained or both trained backbones. And specifically, we would take the minimum. So for each layer of some query example, we look at what is the other layer in this supporting or training example that has the smallest distance, and effectively kind of pairing layers. So trying to find which representation here is closest to which representation in some training example. which allows us to sort of think more flexibly about what is the structure of the full representation as captured by the complete backbone. And we found that to be to give us a bit more better result on a few shot learning tasks. And I won't say much more about this, but you can go check it out this week. Okay, so that was one idea, to think about pre-trained backbones when we're trying to leverage them or recycle them as providing more than the top layer representation. And then the other thing that I'll discuss briefly is the idea that if we're training models all the time on a bunch of different sources, sometimes disjointly. And so how do we leverage all of that and combine that towards a downstream task? And I'll talk about two ways in which we've explored this recently. So the first work by Lu Liu, who was an intern with me and at Mila, the idea that we were trying to get at was so imagine we're in a setting where we have a lot of pre-trained backbones where we've been trained on different types of domains. Maybe one's trained on handwritten characters, another one on bird species, another one on common objects. And now we have a downstream task that's illustrated here. And we're trying to sort of think about the process of solving that downstream task as trying to first, based on the information we have about the task, fetch or retrieve the best backbone to help me solve that task. And from that, we'll just use that as the representation in order to solve the downstream task in question. And in this particular method, to represent the process of retrieving a backbone, we decided to use an attention type of process that we're now quite familiar with, which led to this name of Universal Representation Transformer. I don't want to go too quickly in the details of this, but conceptually, the query in this setup is essentially information about the task, because a query is effectively a task, and what we have to represent the task is its support or training set. And then the keys are effectively some information about each of the different pre-trained backbones that we can retrieve. And then the values is the backbone itself that we can then apply for representing the training and the test examples and do something like a form of nearest neighbor search or nearest centroid classification, like prototypical network, if you're familiar with that. And I'm not sure it's worth really going over the complete details, but the idea here was to essentially represent that as a form of self-attention where the query would be the concatenated representation average over the full support set under each of the backbones. So again, here we're querying with a task. So we thought, well, when we're representing that task is to just look at what does the average representation look like for each of the available backbone. And then the key is simply the representation for a specific backbone that's available to me. And again, average over the support set. And so we pass that through a scale.product attention. That's going to give us attention weights on each of the possible backbone that I can use. And then to get the final representation, we essentially just do this like we do in soft-attention. We just take the weighted average of each of the representation provided by each of the pre-trained backbone FI. And what's kind of nice about thinking about this in terms of an attentional network is that we can invoke the notion naturally of having multiple heads, which would mean effectively that we would try to retrieve maybe more than one backbone. So maybe one task is best represented by picking a bit of a representation of, say, ImageNet, but also of some more maybe specific data set about birds or something like that. And what we find, in fact, in the benchmark that we measured is that retrieving a single backbone was not the ideal. Retrieving two backbones was actually what led to the best results. I'm actually not going to go over the specific numbers we get. These results at this time, it's been a year, so of course they're somewhat outdated. And in fact, Hakan presented results actually better from his team, which are more recent on metadata set. But what I'll show is that these more qualitative results, which we thought were interesting, where what you're seeing here is the attention head of the model that is retrieving two different backbones. And the columns correspond to different backbones that are available, pre-trained on different sources, different domains. And then the rows are some potential source for the downstream task. In this case, we're using the common few-shot learning setting where we separated the class between classes that are available for upstream training and classes that are available for downstream training. So there's no overlap images, but also of classes. And there's one head that has become really good at picking the backbone from the right domain, if that domain was also had also some task in the training data, in the upstream training data. But what's interesting is what the second head was doing, which is it was usually picking a complementary backbone for that task. So for instance, for a task that comes from Omniglot, if you don't know Omniglot, essentially images handwritten of different symbols from different alphabets. Well, one of the head would actually pick the right backbone from Omniglot, trained on other classes. And then the second head would actually pick another backbone, this time trained on QuickDraw, which is also a set of images that are hand-drawn. Okay, so it kind of picked two things that were complementary, and it learned that naturally without the supervision. It learned that by just training it such that it did well on classification, few-shot classification tasks. All right, so that's one way in which we can sort of potentially have a process that combines different pre-trained backbone. The last one that I'll talk about is from this work with L3D-IVU and others that we published at ICML on Flute. It was briefly mentioned by Hakan. That's the method that he beats. So I'm not going to show results here, but I think some of the concepts are interesting. So in the previous work that I talked about with the universal representation transformer, we kind of assumed that we had a collection of backbones that we can sort of pick from them. And if we don't have a lot of backbones, that's maybe useful, but that's maybe scalable. But at some point, if we imagine a community that keeps contributing different backbones, that might get to a point where there are too many, and we might want instead to have a way of compressing these backbones so that it's more manageable when it comes to solving a problem that's downstream. And so in this paper, what we were trying to explore is the idea of not have one backbone per data set, but actually have some way of sharing a bunch of parameters across the backbones of different domains, while having only a number of parameters, a small number of parameters that would be domain specific. And so conceptually, the way we think about it is that each backbone is going to come from a template. The template is going to have holes, and these holes are going to be the domain specific or data set specific parameters. And the other parameters are going to be shared across backbones that they constitute the template essentially. In the experiments that we did, essentially what we were, I think, working with ResNet 50, and the convolutional layers were shared across task and domain, and then the film layers, so these parameters that are essentially a bias and scaling parameter as part of the model, would actually be domain specific. So in this setting, what we did is that we trained the template on the upstream data directly. You could imagine doing something where you actually have the backbones that are already been pre-trained on different upstream domains, and then actually doing a form of distillation. This is a bit closer to what Hakan presented, in fact, and that led to better result, but it didn't have the notion of a template here. So combining these two ideas could be interesting. But essentially, when we would train on a particular example from some domain, we would always update the same shared convolutional parameters, but we would update the specific parameters for the film layers that are specific for that domain from which the data comes from. And then when we would be faced with a downstream task, a few shot downstream task with a few examples, the only thing we would fine tune all the parameters in these film layers. So in other words, we're confronted with a new task, and we're going to fill in the slots in the template. And the template are these film layer parameters. And another way to think about this is that when we're solving a downstream task, we're kind of walking on the lower dimensional manifold of backbones for representing image data. And that's defined by the subset of parameters that we tune here, which are the film layer parameters. And at the time, that led us to get the best results on metadata set last year. But I think this is kind of an interesting concept of finding a way of taking a bunch of different backbones and potentially compressing those so that they're easier to leverage downstream by other people. Okay, I do want to leave some time for questions and discussion. So I'm going to more or less stop here. I did bring about a few sort of food for thought remarks that I think can be useful to think about more generally this notion of doing model recycling. In a way, I feel like we have some elements potentially of the puzzle, but I think it would be really interesting to think about what would be kind of a more formalized framework about engineering with deep learning model recycling. And questions we might want to sort of explicitly investigate is, for instance, quote unquote recycling methods exist and what are their properties, in which situations do they work well. So by that, I think we can leverage, or we can sort of look at all of the different adapter methods that exist. I can mention a few of these. Residual adapters is one that works really well. Prompt tuning for more, maybe a bit more in vision, where we have a large language model, is another one where we're only tuning a subset of parameters to sort of recycle a huge pre-trained model. Diff pruning is another interesting one, where we're trying to identify only the subset of the full backbone that we're actually going to fine tune downstream, keeping all the other parameters fixed. So that's more on the sort of like, if I have some pre-trained model, what is the space of methods for recycling it into a downstream task? But then there's also the question of what are the principles that lead to models that are more recyclable for a bunch of different, hopefully a large spectrum of downstream tasks. Here, I wanted to mention one piece of work which sort of falls in a different category of forms of pre-training on upstream tasks, which is obviously quite popular these days, which is to train large language models on lots of unlabeled data, or doing a lot of self-supervised learning. And I think in a way, the reason we're really interested in that form of pre-training is that it seems to come with emergent properties that allow for a lot of different recycling towards different downstream tasks, from classification tasks, but also forms of perhaps weaker forms of reasoning. And that is very interesting, but obviously we still don't quite understand why it is that this actually emerges. I wanted to call out this particular work from DeepMind that was put on arXiv recently, because I thought it was an interesting kind of work that was trying to understand how do we actually get this kind of emergent few-shot learning behavior from transformers. And it was kind of making a point that, and this is not in the vision domain, but in the text domain, that text has this particular property where words are bursty. So when we start using a word, we tend to see it again a lot of time nearby in the same text. And in a way that's sort of similar to how we construct episodes in meta learning, where we are going to sort of construct tasks where there's going to be a context that's going to include a concept. And then in the query set, where we are trying to, when we do few-shot learning, we try to have a good prediction. We're also going to see obviously that concept, and we're going to try to learn from the context to generalize to the query. And they're kind of advocating that in natural text, that sort of is present naturally by the burstiness of property of text. And I thought it was kind of interesting. I think more work like that would be useful. Also, something that I think there's not as much work as there could be is this notion of how do we recycle a lot of models together. And I pointed to approaches that we might be able to do that. There's a lot of other ones online I'm available that people have looked at. I'm not giving a really thorough summary, but I did want to call out this one, which I thought was really interesting, and I think about these days, which is to actually find ways of combining models just by averaging them in the weight space. And it turns out there are situations where we can do that effectively. And if we could really understand in which situations we can do that, in which situations we can, I think that could be really useful to facilitate the ability of people to kind of mix and matching different models and combining them, because doing averages or weighted averages in weight space is something that's very simple. And that's also, in the end, produces a compressed model that we sort of can build on without having the problem that, you know, our ensemble keeps getting bigger and more compute expensive. Then I was trying to sort of take even a bigger step back and think about, you know, when we think about recyclable material, there are different types of materials that are recyclable in different ways. Maybe that's a nomenclature that we would benefit from defining. Maybe there are certain models that are more broadly applicable or recyclable, and maybe there are models that really should be reused in very specific setting. How do we think about that, and structuring that space would be interesting. What would be best practices to document the full life cycle of a recycled model? I think, you know, we're used to just having a pre-trained model and having a fine-tuned model, and that sort of stops there. But I think we might benefit to try to go beyond this, where we imagine a model being the result of, you know, tens or even hundreds of different combinations of different models that existed before. Well, how do we document that? Because that might be valuable to know, well, what data has each of these models seen, and what data can be truly considered as being a new example that we can measure generalization on versus not. And this also poses challenges in terms of reproducibility as well, because if we have an artifact, a model, that's the consequence of a very complex process of combining and tuning and so on and recycling a bunch of different models together, that starts being hard to really replicate that. And one particular line of thought that I thought was really interesting, I encourage people to look at, is this blog post from Colin Raffel, where he is trying to sort of think about what we can learn from open source software development in the context of developing these models, where we'd have notions of versions, notions of pull requests and merges and tests, which I thought he made some interesting sort of first connections there that maybe we'd want to leverage if we want to sort of go deeper in that direction. All right, I was just hoping to present these kind of somewhat wacky ideas for you to think about. Hopefully this can fuel our discussion as part of the workshop. And with that, I'll stop here and take some questions. Thank you.
The questions that they make?
Yes.
Here online.
Yeah.
So just first of all, what you said about so software, so I think this next up, which has to do that.
Okay. What's the name of the package again?
Next up.
Okay, thanks.
My question is more of a business question. So after learning the whole point is to kind of train a huge model that offers some advantages for its tasks. The question is, how do you convince the company to invest the engineering manpower and the cost of actually training the model?
Invest in training the upstream model?
Yeah.
Right, that's okay. So the question is very practically, I guess, how do you determine whether it's worth it to invest in training these large, potentially large pre-trained model that has multiple purposes? That's a good question. I mean, hopefully you can be in a setting where there's some precedence and some evidence that for the problem setting you're interested in, that this can be beneficial. And in this case, I think you might be able to do some amount of, cost benefit analysis where you're sort of like, well, okay, so I think it would be very much grounded in the application you have in mind. How frequently will you face different downstream tasks? If you only face it once, well, maybe it's not worth to sort of think of it as first pre-training a model, a base model, and then fine-tuning it for just one purpose. But if you're gonna continuously do that, or you're gonna have a lot of, say, different customers have their own tasks or something like that, then I think you sort of can kind of lay out what are the rules of the game, what are the economics of the problem that you're trying to solve, and you can potentially try to make some small scale version of that and try to see how does that compare, hoping that these observations also apply in a larger scale. So that's sort of how I would think about it. I think in this setting, what I also like about the term recycling is that it refers explicitly to the notion of cost. Everything has a cost, and in some cases the cost is worth paying, in some cases it's not. But the only way you're going to know that is if you establish kind of what is the economy in which these models are going to be used, and what are the costs that are being faced, and so on. So I guess that's sort of how I would approach it at a high level. Sure. And also, if there's a question online, I'm happy to take one if I just look at the chat. I'll just leave it open over here. Okay, I'll answer this one in a bit. Yes.
I just want to follow up on the previous question. When do you decide when to go back and retrain before deciding you want to recycle the model via fine-tuning or some other strategies that you have to decide? When do you say this is not good enough and this is going to get mixed up in a local optima that will not fit my work?
Yeah, that's a great question. So I guess the question is, when do you know you're done with pre-training and then you should start doing fine-tuning on your downstream tasks? I do not have a good solution to this. Like, even if I go back, when early on in, mid 2000s, where we were doing unsupervised pre-training, we kind of treated the amount of pre-training we did as a hyperparameter. and in a very dumb way, exhaustively explored different amounts of pre-training. I think it's complicated because it might be ultimately task specific, meaning that different downstream tasks might benefit from various amounts of upstream pre-training. In a way, this might advocate for keeping around multiple models and sort of think of it as like, when I'm pre-training, I'm not generating just one model. I'm sort of generating a bunch of checkpoints. And then in terms of the downstream sort of model reuse or recycling, I'm going to think about having a process that kind of picks the right checkpoint accordingly. That's how I would sort of think about potentially approaching that. But unfortunately, I don't think there's a very, I mean, this is partly what I want to advocate for, and in some ways to kind of develop best practices for doing this, which I think if you go into different papers, you'll find different ideas that are kind of simple, but they, having them evaluated thoroughly and sort of put in the same context might be useful.
Sorry to follow up again, but I had a slightly different concept. Maybe let me ground it in an example. Say you teach an AV to drive on the streets of San Francisco, then maybe we can recycle that model for the streets of New York. But if I want to take that same model on the streets of Mumbai, that's a completely different domain, so to speak. And so at what point do I say recycling is not good enough and I need to go all the way back to random initialization and start from scratch?
Yeah. I think if you have a particular downstream task in mind, that suggests you would want to at least have some sort of evaluation set on that downstream task. And I think ideally the way you would want to think about it is that your pre-training phase is constituted of multiple tasks, multiple training tasks. And then it's always a matter of like, which job do I take and I continue pursuing? And there's been efforts a few years ago to try to think about this and to capture this problem in a machine learning way. There's the freestyle Bayesian optimization paper you'll find on, I think it's only on Archive. This is from Ryan Adams' group. I think Kevin Swirsky is the first author, and Jasper Snook, I think, is on the paper. Where the idea is that you would represent this choice of like, which model do I sort of unfreeze and have it continue training based on an estimate of what's going to be the benefit ultimately of doing that, given how much I've trained it so far. And hopefully in this setting, you'd be able to kind of reason in a way that's grounded in statistics and machine learning for how to kind of handle that full decision-making process. That could be interesting to revisit in this setting. So that might be something worth looking at, but definitely not a problem that has a trivial solution. I have this suspicion, and I think this is another thought for me that came up when I started thinking about this area in terms of recycling. That to me kind of suggested that probably we're not frequently enough just picking a previous backbone or checkpoint and training it some more. Like maybe we should actually doing this half of the time in some ways, because in a way we're off, very oftentimes our reflexes just start from the beginning. I wouldn't be surprised if we're doing that way too often, if we really care about the downstream problem, as opposed to just starting from a checkpoint and kind of exploring a little bit around it a bit more, and maybe coming back to it more frequently than thinking about it just, doing that just one time. So anyways, I like the idea of exploring that more for sure, and maybe more formally in the freestyle Bayesian optimization paper would be one place I would start. Sure. And there was a question, how are the internal nodes selected and head to toe? So we're effectively doing a form of group lasso on all of the hidden units. And it's not all the hidden units, because even that is too many. So I think we use some form of local averaging to have fewer units that we could deal with. But essentially we did a form of group lasso. And then I think we had another formal step where we did that for a little bit, which gave us a sense of the magnitude of the weights associated with different features, where the features here are these internal nodes. And then we would just rank them by this magnitude. And that allowed us to sort of apply different amount of sparsity, which is sort of like somewhat approximately trying to solve the real sparsity optimization problem, but worked decently in our work. So hopefully that answers your question. to iPad to everyone. I'm not sure what that is, but yeah. Any other question? We're at time. Sure.
Thanks for the question, Tom. What are your thoughts on comparing this to the large language models and the story in this approach of having multiple models going to be advantageous or
Yeah. Yeah, sure. So I guess the question is, where do these large language models fit into this notion of having, instead of a zoo of models, or one thought that came to me is first that I think to some extent that's probably already happening, but yeah, that we should probably find ways of doing that. Like, these models are really expensive to train, and so we would benefit even more from having grounded ways of reusing different checkpoints from these large models and finding ways of combining them that's beneficial and allows us to not always start from the beginning. And there's a lot of hand-holding in some ways that happens when it comes to training these models. Sometimes you do have to go back to previous checkpoints because things diverge and things like that. But there's probably something a bit more rich in terms of thinking of doing this, not just for a single training run, but multiple training runs that are in parallel. I really like this recent sort of set of papers that have been looking at averaging models together directly in weight space and trying to think about when is that likely to work, or how can we make that work? Because if it did, then I would think this would be a very effective and useful way. And when we're combining different large language models are very different in architectures, that's a bit more complicated. Colin, in some way, has advocated for the fact that these models have a structure that's a little bit like a sparse mixture in sort of construction. Then you could imagine sort of combining experts together by initializing the initial gating in such a way that it does something reasonable. So that could be one sort of approach, which is to sort of introduce subparts of different networks as different elements of the same mixture of expert within a model that has these kind of components. So that could be another approach, but I think I think there's probably value in thinking more deeply about that. Sure. I guess we should wrap it up here. Yeah. All right. Thanks, everyone.
After that, we'll have the lunch break.
Hi, my name is Jake Snell. I'm currently a postdoc at Princeton University working with Professor Tom Griffiths. It's really an honor for me to be speaking here at each polygamma augmented Gaussian processes. This talk is based on joint work with Professor Richard Zemmel that we presented at ICLR last year, with some additional perspective a little bit. Deep learning is a powerful class of machine learning. It's really an honor for me to be speaking here at L3D-IVU workshop. I'd like to thank all the organizers for putting together this workshop and for inviting me to speak. So today I'll be talking about Bayesian few-shot classification with one versus each polygamma augmented Gaussian processes. This talk is based on joint work with Professor Richard Zemmel that we presented at ICLR last year, with some additional perspective added in that we've sort of gained since then. So first, I'd like to motivate the setting a little bit. Deep learning is a powerful class of machine learning algorithms that learn representations from scratch on raw input data. They're useful for a wide range of applications, including image classification, speech recognition, natural language processing, and many, many others. Deep learning has made tremendous strides in recent years in terms of predictive accuracy, and one of the key factors to their success is the use of large amounts of training data. For example, here are some tasks and corresponding data sets that have been used for training deep neural networks. One unifying theme is their vast scale, with sizes often in the millions or billions that allow the neural networks to learn rich representations. Another aspect of the standard supervised deep learning sort of paradigm is that the space of outputs is fixed and known ahead of time. So for example, if we want to train an image classifier on ImageNet, we know that there are 1,000 classes, and that doesn't change even at test time. However, we would like our machine learning systems to quickly adapt to new circumstances where data is not so plentiful. For example, imagine a content recommendation system where we want to recommend movies or books that a user may be interested in. We'd like to make good recommendations to a new user joining the system, even if they have very little history. This is known as the cold start problem. Or we may want to classify documents into different topics based on the contents of the document. So over the course of time, the meaning of words can shift based on their usage. So we may want to be able to adapt the topics to handle the new usage of these words, but we have very few instances of these words yet used in their new context. Or we may have a pre-trained medical diagnosis system that predicts what disease somebody has based on a medical image. There may be new or rare diseases that we want to recognize, but we have very little data collected for them. So a natural question arises, which is how can we broaden the standard supervised learning paradigm, which has large data set sizes and a fixed number of output classes, to be able to handle these sorts of situations where data is scarce and new classes may arise over time. So one alternate paradigm for studying these questions is known as few-shot classification, which I'll sometimes call FSC for short. So in few-shot classification at training time, a learner has access to a large labeled data set with an ample amount of data for each class. But at test time, the learner is presented with what are called few-shot episodes. So in a few-shot episode, there is a small labeled data set called a support set, consisting of just a few examples of each of a few novel classes. Then it must classify new examples, also called query examples, across these classes. So this procedure may be repeated many times, and the performance is then averaged over these few-shot episodes. So an episode with k classes and n examples per class, we would call that a k-way n-shot episode. In the example shown here, the classes at training time are letters from the English alphabet, and at test time, the learner is presented with a 5-way, 5-shot episode of Korean letters. And then it must classify this new query example as belonging to one of these 5 classes. So few-shot classification is a challenging task for machine learning systems. But the good news is that there is at least some hope because humans are successful few-shot learners. So hopefully over time, the research community can borrow maybe some tricks from humans in order to solve this challenging task. So 2 of the most popular approaches to few-shot classification are gradient-based meta-learning and metric learning-based approaches. So gradient-based meta-learning approaches such as MAML, they seek to learn an initialization of a neural network that can easily be adapted to a few-shot episode with just one or maybe a few steps of gradient descent. On the other hand, metric learning approaches seek to learn an embedding space where few-shot classification can easily be performed with a simple model like k-nearest neighbors or nearest centroid algorithms. So I'll be focusing on metric learning approaches in this talk as they are more closely related to Gaussian processes, as we will see a little bit later. So one of the original metric learning-based approaches is known as Siamese networks, introduced by Bromley et al. In 1993. The key feature here is that there's a shared neural network that extracts representations from each of a pair of images. More specifically, given 2 images, xi and xj, the probability that xi and xj belong to the same class is determined by a shared embedding function f theta, where this f theta would be some deep neural network. So the probability that yi, or the class identity for example I, and yj, which is the class for example j, given those input images, is equal to the sigmoid of the negative distance between those 2 as computed with respect to this embedding space. And so the intuition here is that If two examples are very far apart in this latent representation space, then they're less likely to belong to the same class. And conversely, if they're very close, then they're more likely to belong to the same class. So this objective is, this network rather is trained by minimizing binary cross entropy for randomly selected pairs of same or different images. So after that, matching networks were introduced. So here the notation is a little bit different. So given a support set S consisting of n examples, which are input-output pairs x1, y1, x2, y2, all the way up through xn, yn. So given that support set in a query image x star, attention is computed over the support according to this expression. So what this is doing is, this is a softmax over the support examples. And the input to the softmax is the negative distance between the query example and each of those support examples as computed by this embedding space parameterized by theta. And the idea is that if a query example is particularly close to some of the support examples in the latent space, then those support examples are going to have a large attention value corresponding to them. And so we can create a predictive distribution, and the way matching networks does this is it uses some weighted indicator functions. So if we are interested in predicting the probability that y star is equal to c, where c is some class, what we do is we find all the examples in our support set that belong to class C, and we just add up their corresponding attention weights. And that's the predicted probability predicted by matching networks. And so essentially it's a form of attention over the entire support set where each example can contribute to the output prediction. So later, after matching networks, prototypical networks were introduced. And so in prototypical networks, instead of having a form of attention over the examples themselves, first each class is summarized by a prototypical representation. And what that is it's essentially the mean of the representations of all the examples belonging to that class. So in this case, we have 5 examples for class 1. We would take their mean, and that would give us the class prototype for that class. And so the prototypes are these black dots here. And then if we want to make a prediction for a query example, we would project it into this embedding space, compute the distances to each of the prototypes, and then we would take a softmax of the negative distances. And the idea is that if a query example is close to a particular class's prototype, then it's more likely to belong to that class. So in this case, this query example would be classified as class 2 because that's the closest prototype. So now that I've sort of introduced these background metric learning approaches, I wanted to discuss 2 issues with applying these sorts of algorithms to few-shot classification. And the first is what I'll call a sort of need for model selection. So what I mean by this is that we typically think of few-shot classification just in terms of a certain number of examples per class. So we may focus on, let's say 5-shot. But I think as we sort of look towards applying these sorts of algorithms to real-world situations, it's very rarely the case that we actually have exactly 5 examples per class. And so I think when we're designing few-shot learning algorithms, I think it's important to think about how they can scale up as more and more examples arrive for each class. And so here's a figure from Triantafilo et al. Essentially what it's showing is classification prediction accuracy as a function of the shot. So what this means is that On the right-hand side, we have 100 examples per class, and on the left-hand side, we have maybe one or just a few examples per class. And here the matching networks is this green line here, and prototypical networks is this red line here. And what we see is that prototypical networks captures a simpler inductive bias, and that ends up translating to better performance than matching networks for very small number of examples per class. But at the same time, as more and more examples arrive for those particular classes, the performance of prototypical networks tends to flatten out. But on the other hand, matching networks, as more and more examples arrive, the performance continues to increase. And so one question is, how can we sort of gracefully scale from simpler models that work well in the very low shot setting to more complex models that can better capture more and more data as they are observed? So that's the first issue. The second issue I wanted to talk about is the importance of uncertainty for few shot classification. So we know that if there's not many labeled examples for a particular class, then there's a significant amount of model uncertainty, in the sense that there may be multiple models that are all consistent with the observed data. And if we had observed many examples for these various classes, then maybe we could really sort of pin down what the best model is that explains those observed data. But in the few shot case, we often don't have that luxury, which means that there's uncertainty around which model is going to be the best one. At the same time, few shot classifiers are increasingly being used for user-facing applications, where it's very important to know when the model is uncertain. So here I'm showing a dermatological disease diagnosis application where we may want to make predictions for rare classes that don't have very much labeled data. And on the right-hand side, I'm showing a facial recognition for assistive technology application, where a user may want to control a computer based on their facial gestures. And in both of these cases, capturing uncertainty is very important, because let's say a classifier confidently predicted the wrong class for the disease diagnosis. Well, based on that information, a doctor may recommend some treatment that's not appropriate for the patient. And at the same time, in terms of the facial recognition application, if the system tries to adapt to a new user with very little data, but confidently predicts the wrong action or the wrong gesture, then the user may become very frustrated with the system and just give up altogether. So in both of these cases, what we would really like to be able to do is marginalize over models that are consistent with the observed data and use that to help to better capture predictive uncertainty. And so both of these concerns, both the model selection and the uncertainty issue, I think can be naturally addressed with Bayesian models. So in Bayesian models, we first specify a prior over models, indicated here by this P of H, and then we use Bayes' rule to compute the posterior given some data. So we do that by using Bayes' rule, which says that the posterior distribution over models is proportional to the prior times the likelihood. And if we expand the likelihood, that consists of the product of n terms, one for each example in the dataset D. And what this means is that since the prior has just one term here, we may, our prior may bias us towards simpler models. But as more and more observations arrive, that prior may be sort of overridden by the likelihood term, because the likelihood term will play a larger and larger role as this n increases. Now, of course, if the data end up coming from a very complicated distribution, then this prior may be overridden fairly quickly, or if they are in fact consistent with a simpler model, then the Bayesian posterior should reflect that. So that's how Bayesian models can sort of address that first concern, which is gracefully scaling from simpler to more complex models in the face of additional data that may arrive. And in terms of the second concern, which is capturing uncertainty, if we look at the way predictions are made in Bayesian models, we would probably use the posterior predictive distribution, which I'm showing here. It's this P of y star given x star and the observed data D. And what that is it's the integral over the likelihood times the posterior. And what that's essentially doing is it's saying we have this collection of models and we're going to look at the posterior and essentially weight the predictions of each model by its posterior probability. So what that means is if we have some models that are very good explanations of our observed data, they will have large posterior probability, and we're going to weight those more heavily in terms of making our predictions. And in particular, if there are multiple models that fairly equally well explain our observed data, then when we make a prediction, if we do it in this way, we'll actually be averaging over each of those different models. And that naturally captures this uncertainty that we would like to capture, especially in user-facing applications. So to get a little bit more specific, we typically have some model parameters W, and we have some hyperparameters indicated here by theta. So our prior distribution over the model parameters would be this P theta of W. And then after observing our data D, the posterior over the parameters is computed according to this expression. So here we have the prior, we have the likelihood, and we have the evidence or the marginal likelihood in the denominator here. So the marginal likelihood is essentially how well does this entire class of models explain the observed data. And we get that by integrating the likelihood times the prior. And once we compute the posterior distribution, we can also compute the posterior predictive distribution, which, similar to the previous slide, is the integral of the likelihood times the posterior. And this, as I mentioned before, that's what allows us to make predictions while marginalizing over the model parameters. And so one thing we might want to do is try to learn what these appropriate hyperparameters theta are. So we may want to actually try to maximize this marginal likelihood and find the hyperparameters theta that really maximize the probability of our observed data. And that's what empirical Bayes does, and that's the approach that we take in our work here. So now I wanted to talk about Gaussian processes, which are a very interesting class of Bayesian models that I think may be particularly relevant for few-shot classification. So what is a Gaussian process? Well, a Gaussian process, or a GP, defines a distribution over functions such that the output of the function evaluated at a finite set of points is jointly Gaussian. And it's specified by a mean function m of x and a covariance function, also known as a kernel, k of x and x prime. So let's say we're interested in the function value at 3 input points. Let's call them x1, x2, and x3. Well, if we were interested in what the GP prior is evaluated at these points, what we would do is we would plug x1, x2, and x3 into our mean function, and that would give us the prior means. And then we would need a 3x3 covariance matrix. And the way we do that is we plug in all pairs of inputs into the covariance function. So we would get our 3x3 covariance matrix by evaluating k of x1, x1, k of x1, x2, k of x1, x3, and so on and so forth. And so conditioned on some finite set of input points, the GP gives us this recipe for getting a Gaussian prior. And so one nice thing about GPs is if we end up using a Gaussian likelihood, as we would often do for, let's say, regression, closed form expressions exist for both the marginal likelihood and the posterior distribution. And that's because a Gaussian is conjugate with itself. So if we have a Gaussian prior and a Gaussian likelihood, then you can multiply those together and you get another Gaussian out. So the covariance function plays a pretty important role in GPs, and the properties of the functions that we get out are determined primarily by this covariance function. So here I'm showing some different choices of kernels we could use. If we use a squared exponential kernel here, we get these fairly smooth looking functions out. Or if we were to use a periodic kernel that has these sort of long range dependencies determined by the form of the periodic kernel here, we can get these functions with some periodic structure to them. So choosing the proper covariance function that matches our data is pretty important. At the same time, we would really like to leverage the power of deep neural networks to learn a good kernel. And so in our work, we borrow the approach of deep kernel learning by Wilson et al. That applies kernels on top of a learned representation space. So an example of how we might do that is on the left-hand side here, I'm showing a squared exponential kernel. And well, instead of computing the kernel directly on the input space, we would instead project both x and x prime first to some shared embedding space, and then apply the kernel there. And what that allows us to do is have these powerful and expressive kernels, but still also maintain some of these qualitative properties that we might want to maintain. So what are some benefits of GPs for few-shot learning? Well, compared to other Bayesian approaches, such as Bayesian deep learning, where we put a prior directly on the weights of a neural network, computation of marginal likelihood and posterior predictive distribution is relatively straightforward. In fact, as I mentioned before, it's closed form for Gaussian likelihood. So one of the traditional drawbacks of GPs is that they have poor scaling with the number of examples. They scale cubically with the number of examples in your training set. But that is less relevant for few-shot episodes because by definition, they're few-shot. So we don't have many examples in our support set, which is what we're conditioning on in the few-shot case. So another advantage of GPs is that the deep covariance functions that we might learn, they're powerful because they're applied on top of a learned deep neural network, but at the same time they're interpretable in the sense that we can input two examples, x1 and x2, and then the deep covariance function will tell us how similar or how different it thinks that they are. Another nice aspect of GPs is that they can be situated pretty nicely with respect to previous metric learning approaches. So with respect to Siamese networks, rather than using some distance function to directly predict the probability of two examples being same or different, we have our covariance function that's specifying a priori how similar x is to x prime. And with respect to matching networks, rather than using the attention to weight the contribution of the support examples directly, our covariance function just specifies the prior covariance, and then Bayesian inference tells us how we can get predictions that incorporates both this prior covariance while also being consistent with the observed data. And finally, with respect to prototypical networks, instead of specifying a simple model class directly, GPs can learn the appropriate prior that facilitates few-shot adaptation. So now I'm going to talk a little bit about how we actually would apply GPs to do classification. For a standard classification task, we would have a softmax, let's say over C different classes. in order to do that, if we had n data points, what we would want to do is we would want to compute the logits of across these C classes for each of these n data points. And so we could represent that by, say, an n by C matrix. Or we could flatten that out and treat it as one flat vector with n times C number of elements. And that's what this F is doing here. It's essentially taking all the logits for the first class, for examples 1 through n, then all the logits for the second class, for examples 1 through n, and so on and so forth, all the way up through class C. And what we're going to do is we're going to put a GP prior directly on this F vector. And the way we're going to do that is we have a zero mean function, because a priori we don't expect any one of these classes to be more or less likely than the other. And then we have to specify a covariance function, and what's typically done in GP classification is we make the covariance function block diagonal, in the sense that all the logits for class 1 covary with each other, but not with any other classes logits, and so on and so forth. So one drawback, of course, is that if we were to use the softmax likelihood, that renders inference intractable, because the softmax likelihood is not conjugate with a Gaussian prior. So there are various approaches to deal with inference in this case, such as Laplace approximation, expectation propagation, variational inference, multinomial probit regression, or we could just treat the observations just as if they were from a Gaussian likelihood and to predefine the ground truth logits as either +1 or -1. So the approach we take here is we use something called polygamma augmentation, which I'll explain here in terms of just binary classification. So the way this works is that we take the logistic likelihood, which is a product of individual logistic likelihoods for each data point. You can rewrite that as this, where we have a sigmoid to the yi times 1 minus the sigmoid to the 1 minus yi. And you can rewrite it a bit to get this expression on the right-hand side. So what we're going to do is we're going to use a technique called data augmentation, somewhat confusingly, because here it doesn't refer to augmentations of an image like transformations or rotations or crops or anything like that. Instead, it means we're going to have a new random variable, in this case omega, and what we're going to do is we're going to define this omega such that if we were to integrate it out, we would recover the original likelihood. Now this seems a little bit counterintuitive because we had a difficult likelihood, and now we're going to introduce some new random variable. Wouldn't that make things even more complicated? The trick is that if we choose this omega in the right way, this p of y given f and omega becomes a lot easier to deal with. So conditioned on omega, we get some nice p of y given f and omega, and we're going to be able to handle that much better than the original likelihood. So I won't delve deep into the details, but I'll just say it turns out if you define omega according to a standard polygamma distribution, there's an integral identity that we can use, which ends up meaning that if we condition on this omega I, we get something that's proportional to a Gaussian. And so what that means is that even though this p of y given f is not conjugate with a Gaussian prior, if we define this omega to be coming from a polygamma prior conditioned on that omega, then we do get something Gaussian. And the nice aspect of that is what we can do is we can set up a Gibbs sampling procedure where we sample from omega and then sample the f values and then back to omega. And we can do that sampling fairly efficiently. And conditioned on those omega values, we have a Gaussian, which means that we can apply these nice closed form expressions for marginal likelihood and the predictive distribution. So one thing that we would like to be able to do is extend it not just to binary classification, but also to be able to handle multiple classes. The issue is that that polygamma integral identity doesn't directly apply to the softmax likelihood. So there have been some approaches proposed in the past. One is to use a stick breaking construction where we decompose a multi-way classification into a sequence of one versus rest classification problems. But unfortunately, we found that that introduces some undesirable asymmetry across the classes. Especially in the few shot case where we don't have that much data to sort of override a prior like that, we found that that was not the best strategy for few shot classification. And in terms of, there's another approach called the logistic softmax, which is similar to the ordinary softmax, except it replaces the exponential with a sigmoid. And we found that this approach, it's difficult for it to capture confident predictions because there's a sort of saturation effect. If a particular class's logit, this FC here, if that's very large, then the maximum that this sigmoid can attain is 1. And that's unlike the ordinary softmax where X of FC could be very, very large and sort of you can get a nice confident prediction. So those are two previous approaches. So we decided to do something a little bit different. Our approach is, we call it the one versus each likelihood. It's based on the one versus each softmax approximation introduced by Titius in 2016. In that case, it was originally proposed as a lower bound on the softmax to handle sort of extreme classification with a large number of classes. The way it works is that it rewrites the softmax likelihood as a sum of differences between the ground truth logit and each other logit. And then it uses this inequality here to rewrite it as a product of sigmoids. So originally it was used as a lower bound on the softmax, but we propose to use it as a likelihood in its own right, sort of as an approximation to the softmax directly. And the nice thing about this form is that since it's the product of many sigmoids, we can directly apply the standard binary polygamma augmentation to this difference FC minus FC prime. So it turns out that this is actually what's known as a composite likelihood that results from considering all pairs of classes. So how does this look like? So here I'm visualizing the likelihoods for softmax, Gaussian, logistic softmax, and the one versus each likelihood. And in this case, I'm considering 3 classes where F3 is always clamped to 0. So the x-axis is going to be F1 and the y-axis is F2. And intuitively what we would expect is that F1 is large but F2 is small, then we would get a confident prediction for class 1 and vice versa. And so here's the probability contours for the softmax. And in terms of the Gaussian, the way the Gaussian likelihood works is it assumes that the ground truth logits would be F1 is equal to 1 and F2 is equal to -1. So anything sort of that's not close to that sort of has less probability assigned to it. And as I had mentioned before, the logistic softmax has this issue where it's similar to the softmax, but it's quite a bit more flattened in the sense that it's less able to have confident predictions. Notice that the scale here only goes up to 0.64 as opposed to the softmax, which goes up close to 1. Similarly to the softmax, R1 versus each is pretty close. I would say the main difference is here where F1 and F2 are fairly similar. It's a bit flatter, but it still is able to capture these confident predictions that we would like. And overall, I think its shape is quite similar to the softmax. Okay, so one thing we could do is apply it to a simple data set. So here we're applying Gaussian process classification to a two-dimensional version of iris classification. And we can see, basically get a qualitative sense for these. So the Gaussian likelihood has some artifacts. Here you can see where it's predicting fairly well close to where the data is, but it has these classes can kind of jump over each other, which I think is less than desirable. Logistics softmax, the decision boundary itself is fairly nice, but as I mentioned before, it's less confident in regions where there is a lot of data. One versus each is similar to the softmax, but perhaps a little bit more overconfident in some cases, but it is fairly close to the softmax. So how do we actually do hyperparameter learning? Well, we consider two objectives. One is the log marginal likelihood. What the log marginal likelihood does is it takes the support set and the query set and pools them together and then looks at the log marginal likelihood of that sort of data as a whole. And then we also consider the log predictive likelihood, which is very analogous to standard few-shot training procedures where you condition on the support set and then you try to optimize the log predictive likelihood for the query set. In both cases, we do some Gibbs sampling to get some approximate posterior samples for the omega, which remember are the augmented random variables that come from the polygamma distribution. And we can use Fisher's identity to approximate the gradient, as shown here. And we found, interestingly, that rather than running one chain for a long time, we found it better to run many chains in parallel that were very short. So we found that we could get good signal with even just one step of Gibbs for training. So in terms of classification accuracy, we have some results here for different methods, including some metric learning, some fine-tuning, and some gradient-based meta-learning approaches. And we found that our method here, both in terms of the marginal likelihood and predictive likelihood, is fairly close to the top. If we just choose one of these, if we were just to choose marginal likelihood, we found that marginal likelihood does better for one shot, and predictive likelihood tends to do better for 5-shot. In terms of calibration, we also measured the calibration error for these different methods, and we found that fine-tuning approaches and approaches that use a non-softmax likelihood, like deep kernel transfer, which uses a Gaussian likelihood, and a logistic softmax based Gaussian process, they're not very well calibrated. Whereas prototypical networks and Bayesian mammal, which both use softmax likelihoods, they are fairly well calibrated, as is the one versus each based Gaussian process that we proposed. So we also have some experiments on robustness to input noise and out of distribution detection, where we found that our method does fairly well in both of those cases. It's not a clear winner, but it is among the top performing methods in each of these different scenarios. So to wrap up, we talked about how Bayesian methods are interesting for few-shot classification because they naturally handle this transition from few-shot to many-shot, and they naturally capture model uncertainty. In particular, GPs are pretty appealing due to their nice theoretical properties. We proposed our novel GP classification method that combines polygamma augmentation and the one versus each likelihood for tractable inference, and we showed strong accuracy and uncertainty quantification on benchmarks, including calibration, robustness to noise, and out-of-episode detection. In terms of future work, we may want to consider, instead of using empirical Bayes, a full Bayesian treatment of the hyperparameters may enable better adaptation. We may want to incorporate class-specific covariances into our covariance function because different features may be more relevant for distinguishing different classes. Or we may want to extend to generalized feature classification where we have to classify over both base and alpha classes. So to conclude, I'd like to thank Richard Zemmel, my PhD advisor at the time with whom I collaborated on this project. And the paper and PyTorch code that this talk are based on, they are both available at my website shown here. I'll flash up these references so anybody who's interested can pause the video and take a look at those. And that's all I had. So I'd like to thank you for your attention, and I'd be happy to take any questions you might have. Thank you.
So I believe that Richard is connected to Zoom. Yeah, hi, Jake.
Hello. No worries.
I had in my RAM the last slide. Let me pin you first. Okay. So if someone has a question, please come here because that mic is not shared in Zoom. Oops. Okay, I think that because of the lunch break, people only have food in their minds right now. So maybe we can leave it here. Oops. Thanks a lot for your talk. Very interesting.
Thank you.
Yep. Okay, so so you introduce it?
Yeah, just send it over here. Where's the file right now? Program, yeah. I know, they just go to me. Introduce, like, no, that was panel. Are we ready? All right, we're ready to start the afternoon session. It's my great pleasure to introduce my great friend and amazing researcher, Katerina Frejadaki. She's an assistant professor in the machine learning department at Carnegie Mellon University. She received her PhD from the University of Pennsylvania and was a postdoctoral fellow at UC Berkeley and also at Google Research. Her work is on learning visual representations with little supervision and on combining spatial reasoning in deep visual learning. Her group develops algorithms for mobile computer vision, learning of physics and common sense for agents that move around and interact with the world. And her work has received a multitude of awards. So without further ado, Katerina Frejadaki.
Great, thank you. Thanks for organizing the workshop. Thank you for inviting me, and I really have enjoyed the previous talks. This talk is complementary to previous talks. We're not going to talk about how we're going to transfer weights between tasks. Two main themes we're going to discuss. One is 3D neural bottlenecks and reconstruction feedback with modular representations. So the world is three-dimensional and then is projected into two-dimensional images. So we all know that. And the question is, can we use this 3D, this prior that the world is in 3 dimension to learn with fewer examples? So here is how we since 2019, we've proposed some architectures in my lab that essentially equip neural networks that take images as input with what you see here, a 3-dimensional bottleneck that has 3 spatial dimensions, X, Y, Z, and 1 feature dimension. And the feature dimension is not shown here, it's shown as color. Imagine we took the channel and then we did PCA, and then we keep only the 3 principal components, and then we colorize it. So this is what this means. So this 3D neural bottleneck, you can imagine as being the featurization of the scene behind the image. Okay, so an image comes in, and then at the output of the network, you have this 3D feature map of the scene. If we don't do that, the standard thing in computer vision is we build features directly on top of image pixels, right? So we take the image, and whatever is visible, we featurize it, and we label it and predict and so on. Now, but there are these configurations. So you and me understand that there's a cat, and in front of it, there is a fence, right? So we are able to do this spatial reasoning. The question is, how can we help our networks to also do similar reasoning? What architectural biases we need to add such that this reasoning emerges when we train our networks under some hopefully self-supervised task? So this is our choice. Our choice is, what if we don't put features on the image itself? Because the image is just a noisy, incomplete 2D observation of a complete 3D reality. What if instead the features sit in that 3D scene, okay? And here in this particular instantiation of networks I'm going to talk about, this featurization is explicit, okay? And is this 3-dimensional feature map. So here's how it looks like. You just need to design this 3-dimensional placeholder, you design its dimensions, okay? And then you can have cameras, all right, that look at the scene from different viewpoints, and these cameras can look at the scene concurrently, or it can just be one camera that moves around in time and collects observations. And these observations are now fused in that 3D feature volume. Okay. Essentially, there is a non-projection operation that is parameter free that shoots and scatters those 2D features into 3 dimensions, and then the later featurization is directly on the 3 dimensions. And this space is very convenient for redecorating and fusing information, because in the 2D image space, as you move your camera around, some things appear and some other things disappear, right? So you don't have permanence of the content. But in that 3D feature map behind the image, things can persist over time, all right? So you can be moving views and adding features to that 3D feature volume. Yes, and if you have some depth sensors, you can fuse that too. You have an explicit ready metric information. You can use it during your unprojection operation to place features in the right location as given by your depth sensor, for example. And then instead of having 2D CNNs or 2D transformers operating in images, we're going to have the same layers operating in these 3 dimensions. So what can you do with those architectures? Well, you can do exactly the same thing that you do for CNNs. Okay, you can train them supervised for downstream tasks. For example, you say, I want to detect now the objects that are in the scene. Or so I have a video as input, and the output will be 3D bounding boxes, and you can train those networks supervised with such a detection annotations or segmentation annotations. Or you can train them self-supervised. And this is something that we have found with those networks. You can train them for view prediction. For example, you have seen K images, you fuse their information in the 3D feature volume, and then you give me a new viewpoint and you ask me, how would the work look if I move to that viewpoint? And then what I'm going to do is I'm going to orient my tensor, my 3D feature tensor, and neurally render it with some combination of geometric and neural operations, and then I'll give you an image as the output of that. And the important thing here is that all operations are differentiable and end-to-end backprobable. So you have your end task, and the end task directly trains essentially the weights of that network and instantiates those 3D features. So you never need to supervise the 3D bottleneck directly. So the 3D bottleneck is supposed to save whatever is needed for the downstream task. Okay, so this is very different than let's say having explicit point cloud and supervising their occupancy and so on. So how does this prediction look like, the view prediction? You have a number of views, or you can have a single view. And then there's the encoder that does this 2D to 3D projection and 3D featurization. And then there is the neural renderer that orients the feature and generates an image. And then there is the pixel matching between the rendered image and the actual view, all right? And this is a self-supervised task because you just need to be an embodied agent that moves in a scene to be able to see a scene from multiple views. And the assumption here is that the scene is static. The only thing that is moving is the camera, okay? But most of the world is static, to be honest, right? But like very few things move in the world, like animals and people and maybe vehicles now that the last 100 years we've constructed, but most of the world is static and you can train from that signal. Yeah, and if you train it in this way, so essentially what happens is that the network learns to imagine, because one image is a very incomplete observation of that 3D feature volume. All right, so after projection, a very small part of those voxels sitting here are occupied, but once you train the network learns to complete and in paint the missing 3D information so that it can render different viewpoints, okay? And now your one question for those people that like geometry, right, and know about NURBS that are implicit representations of multi-view spaces. The difference is as follows. In those geometric networks, we call them geometry-aware networks, we put the 3D bottleneck for the sake of doing better representation learning better correspondable features and so on. Rendering beautiful images is actually not important. In fact, I'm going to show you now next what we did, where we rendered not images, but rather feature maps. So we did contrastive prediction, and the features you learn out of this are better than just rendering pixels directly. The most important difference, though, is the representation itself. Geometry-aware networks, what I just showed you, have the convolutional inductive bias. They never go through a bottleneck of one vector, okay? So the representation is keeps its spatial organization, and because you have this locality of computation, actually you can generalize much better than collapsing one scene into one vector, and I'm going to show you results of that. And of course, the whole point of those representations on the left is generalization. You want to be able to train on some training scenes, and then you dump your architecture on a test scene, and you want to be able to do well. And here is what I mean by generalization. View prediction is not a new task. Previous architectures have tried view prediction. So the question is how, representations that don't go through such an explicit three-dimensional bottleneck do on view prediction versus our architecture. And here I'm comparing with a model from DeepMind, GQN, Generative Query Network, but similar representations, similar going through a bottleneck of one vector over 2D feature map is the case with NERF models that collapse a scene into one embedding, all right? So Here, both models have been trained and tested on scenes that contain two objects, all right? And both of them do well, both of them. Now you trained it, now it's a test scene, so you show a new scene with two objects and you ask the model to render views from all over the viewing sphere, okay? And this is what I'm showing here. And both models do well. And now we're gonna take both models and test them on scenes with more objects, okay? So we have a clear, big generalization gap between trained distribution and test distribution. So here are the scenes with more objects. And what you see is that GRNN, geometry aware network, okay, is able to see 4 objects. It generalizes from 2 to 4, while networks that go through 1D bottleneck or 2D feature map, they cannot, they still see only 2 objects. So there is no reasonable generalization that happens there. And this is all due to convolutional inductive biases. For the same reason that CNNs are better than MLPs, geometry aware networks that preserve locality of computation are better than, models that have this one-dimensional or two-dimensional bottlenecks. So here's what we did. We took that network and went around and collected training data by having an embodied agent to look at the scene from different viewpoints, and then train the weights, and then put a supervised task of a 3D object detection, and pre-training for predicting images helps, as opposed to training the weights from scratch, which is not surprising. Any task, even not a good task, would help over from scratch pre-training. Now, what we saw is that the images we rendered were quite blurry, because it's very difficult to guess how the world was going to look from a different viewpoint given one image or a few images as input. So instead, what we said is, what if we give up? Rendering images is actually very good for debugging. I was able to show you those videos and say, look, we have some reasonable generalization on those toy scenes. But once you go outside of toy scenes in the simulation and you go in more realistic images, it's very hard to predict pixels, okay? Because the world is very multimodal, its appearance is very multimodal. So instead, we said, what if we just render feature maps? Okay, two-dimensional feature maps or three-dimensional feature maps. So what this accounts for is you have a set of images and you encode them into a three-dimensional feature map, and then you have your test query image here, a new viewpoint, which also you encode into a 3D feature map, and then you register both of them because you know the viewpoint, and then you say features that go to corresponding IJK grid locations should be close in embedding distance, and features that sit on different locations essentially should be far. Okay, so here I showed better because I have already warped my tensor, and as you see, the two 3D feature maps are aligned. So this is standard contrastive learning done voxel-wise. And this picture shows that our encoding is just a single image, but the encoding can use one or more of those images. And then if you do that, then you take your 3D feature map and you put a camera and you render the features. They look like that. So I essentially visualize the following thing. I put a bird's eye view, slice the 3D feature map, did PCA on the feature vectors and map them to colors. And I showed them, and you see that cars are put together in the background is put in a different color and so on. And actually, this is a better pre-training task. Okay, so the yellow curve is higher than the green. Essentially, contrastive prediction is better than image prediction directly on the pixel space, predicting image directly on the pixel space. So now your question would be, we know that geometry can drive self-supervised learning. Here is a simple task. And for example, in dense object nets, right, that was best paper in a Coral a few years ago, you would take a scene, you would take two different viewpoints, you know the calibration of the cameras, you know the extrinsics, and you know when two pixels in two different views correspond are projections of the same 3D physical point. So these would be your positive pairs. And you say, make sure the features of those pixels are close in embedding distance and pixels of are projections of different 3D physical points are far. And the same thing was done in 2.5D space from point contrast, right? A paper where it used a point cloud, and it featurized the point cloud that said, points, the same point projected in different views. The projection should have features that are close in embedding distance, while projections that correspond to different 3D physical points should have different features, okay? The difference between those frameworks and our framework is that we don't featurize the image, which means the pixels in the image, or we don't featurize the visible points in the 3D point cloud. We featurize even parts of the scene that are actually not visible, okay? So the imagination space also has features. And these features are contrastively matched, which means that you don't need to see the same thing from both viewpoints to actually try to featurize it. So indeed, you featurize beyond your observations. You really have an imagination space that you want to place features on, all right? In the same way that I see you now and I can imagine roughly how your backs are going to look like, and I can generate positive and negative examples for the back image and figure out when I'm surprised and when I'm not. And here is now a follow-up work on these representations. We call it coconuts from continuous contrastive 3D representations. So far, we've discussed about that three-dimensional feature map. And the problem with the feature grids that we don't like is the fact that they have we have problems with spatial resolution, right? They really occupy a lot of GPU memory, so you cannot arbitrarily scale them. So now you can take those features and parameterize implicit functions, okay? And these implicit functions, you can query them for XYZ coordinates, okay? And you can train them so that they generate the features in these essentially continuous locations. And in this way, of course, the hope of those implicit functions are that they're going to do much better trilinear interpolation because it's a trained trilinear interpolation. So the question here is not implicit functions or not implicit functions. The question is, how do we build a feature representation that is actually modular, okay? And the modularity here comes simply from locality of computation. Different parts of states have their own features that have been computed convolutionally for parts of the images that actually correspond to that part of the scene, if that makes sense. And indeed, these networks, coconuts, that both use an imagination space and are able to scale up the resolution outperform, of course, dense object nets, which is, don't even have a depth map, but also point contrast that has access to a depth sensor, same as this approach. And, for more details, you can look at the paper if you like. So here is the question. So we try to go from images directly to 3D feature maps to try to in-paint and a-modally complete essentially the observations. But the question is, does a model completion, is my ability for me to complete the scene come before or after I recognize the content of the scene, okay? So far, we showed the convolutional architecture to get there. And now I want to discuss some more entity-centric architectures that reason at the entity level for doing the similar decomposition plus in-painting of the input. So in the 3D neural mapping with geometry-aware networks, we first a-modally complete the scene, right? So we first go from 2D to a 3D feature map, and then we run non-object detectors. So now what we'll discuss next is such completion will jointly happen with recognition, understanding what the entities are. I am able to complete how you look like because I know that you're human beings, okay? Now, probably this needs to happen in multiple layers in the network, but we'll see one example of this. So we heard in previous talks about transformers, and indeed they are incredible. And I really liked that intuition that the reason they're incredible is that they jointly essentially segment and featurize the input. So what we did here is we grabbed some point clouds from PartNet and we trained a 3D point cloud transformer architecture similar to DETR, with a DETR head, with a detection transformer head, with object queries that essentially segment different parts. So we trained this from chairs, okay? And you see that the detector is doing good job on segmenting chairs into parts when, you know, the training data are within the training distribution. But here's some crazy shapes that do not look like chairs. They don't look like chairs. However, they share parts with chairs, right? So they have, you know, elongated edges, and they have, you know, round spheres. I mean, if you look at their parts, in part level, they do like the parts of a chair, okay? But the thing is, the detector cannot actually rearrange those parts. That's the problem. And you go a little bit, I mean, much, maybe here I want to say that you go much outside the training distribution and your detector fails, all right? And humans have a remarkable ability to really generalize outside their training distribution. And when I realized this, the first time I realized this, because I always thought, okay, we just need more data, it's trivial, it's very simple. If you look the books for infants that are very, very young perceivers, right? They're pretty young. They have crazy things, like monsters with many mouths, or monsters with many eyes and 3 hands, and some other crazy things. For example, sponges washing cars, things that I have difficulty understanding, and they're designed for infants, and infants actually get them, which is, I think, incredible. So the question is, what do the infants have? And this is, by the way, a conjecture. The question is, do we just need more training data with the current architectures, or we need to also advance our model architectures? That's the question where we're going here. Yeah, so this is the visual cortex. And we have some information of how it works. And it turns out that it has a lot of top-down pathways, right? A lot of priors are encoded on those top-down pathways. While our detectors, right, state-of-the-art detectors are feed-forward in nature. And we may say that, you know, if you stack a lot of layers, essentially you can imitate a sequential computation and iterative computation just by stacking more layers. But it might be that that may this not be enough. Right now, all our priors are encoded on the weights of the network, and we hope that the, you know, if feed-forward pass through that network will be able to parse the scene. There are a lot of very interesting papers that talk the importance of top-down actually pathways for recognition. Now, detectors don't have top-down pathways. They don't try to render back things that they have recognized, right? But there are many generative models developed recently, and I'm not sure if you're familiar with them, but there is, for example, slot attention and Monet or some capsule autoencoders that try to recognize entities in the scene. And their main, essentially, supervision comes from reconstruction. They take an image, they encode it into different entities, they render back their entities, they match the pixels, and they backpropagate, and they hope that in this way they'll be able to segment the image into parts. And okay, so the encoding part is similar to our detectors, right? It's just you go from pixels, you to featurize your pixels, and then you go into these object queries. But there is also this rendering extra module where you try to reconstruct your input and have this additional reconstruction loss. And it turns out that for simple scenes, it works. This is a clever scene, but a little bit more difficult scenes, things fail. It doesn't really work. Like to auto-encode essentially single images and objects to emerge. Now there may be some, you know, maybe things are different if you go to cross view, but let me just say that, you know, overall things do not seem to work. So why they fail? So those completely unsupervised generative models, they try to segment a scene through reconstruction, and they try to answer 2 questions at the same time: what the objects are and where they are. So they don't have any prior about how objects are supposed to look like. They try to jointly try to figure out how those entities look like and where they are in the image. And you know what we propose is, what if we don't do that? There is no, right now there's a disconnect. There are detectors that are wonderful and supervised, and of course you can self-supervise them with some BYL type of contrastive objectives, but there's no reconstruction. And then we have generative models that can render images, right? But they really don't do a good job on decomposing that, okay? So can we marry these generative models and detectors together? So what we built here is something we call generating fast and slow networks. So I'll show you what this is. First, we go back to let's say Mars idea about the world is built out of parts. So it is useful to teach our network about parts. Okay. So what does this mean? This means I'm going to show point cloud parts one by one to our network. I'm going to encode them with my PointNet++ or point transformer, and I'm going to have a single slot here. One slot is one-dimensional vector, and train my network to look at this part and essentially map it into a symbol. So essentially, these are a bunch of symbols. I mean, each symbol is of course a long vector, so that's the important thing, that essentially you learn a distribution over those symbols, and then you feed the slot decoder that takes the embedding vector and renders it back into that part. So you teach your model about parts. And where are you going to find those primitive parts? Well, you can take your chairs, somebody label those chairs, but instead of showing to your network complete arrangements of those labels, you're just going to tear them apart, okay? Every part is now alone, and then I show it to the network as an entity to be recognized. So we call this encoding the primitives. So then the thing that I'm going to change is that I'm going to instantiate now multiple slots, okay? Multiple slots. So there is a combinatorial there. We changed the architecture, okay? We had here only one entity slot, and now we have multiple ones. And now for each one of them, I'm going to have a different slot decoder, okay? And then I'm going to render them and max pool them and make a chair. And you understand that if you have trained, and then I'm going to auto-encode again my network with those complete shapes, all right? Okay, so that's what I'm going to do. And let's see how this works. It kind of works. You do this auto-encoding, then you feed this point cloud, then it's kind of segments it and reconstructs it, all right? But it fails on really out of distribution examples. So this, for example, specific chair was not showing in the auto-encoding step. So what are we going to do? We're going to do slow inference. So what does slow inference mean? We're going to take a single example, a single scene, and then we're going to update our network weights via gradient descent using this reconstruction loss. So basically, we're going to optimize the weights of the network for reconstruction, and we hope that because we already those priors about parts, that somehow segmentation will improve. And there is a very recent paper about following up on those unsupervised generative models for scene decomposition that says, look, there is no way we can optimize reconstruction at the same time segment the scene, because the better the reconstruction, sure, you can learn to reconstruct it perfectly, but your segmentation will degenerate. Okay, and they did that starting from scratch. But here we have done a curriculum. We have taught our network what are primitive parts. Okay, so here is how things look like. And this slow inference, by the way, is on a single example, not on a data set for every single example. So it looks like that. The network starts and then updates its weights, and the reconstruction improves, and also the segmentation improves. And also, you don't need to predefine the number of parts. I think this is very important. Slots that are not going to be damn useful, they're going to, essentially spit out nothing. All right. So essentially, through this gradient descent, there is a search over how to decompose the scene, over primitives that I've seen before, so that the reconstruction objective improves. Okay. And this search concerns both the reconstruction of every part as well as how many parts are there. Okay. And by the way, here these tables are outside of the distribution. We only trained on chairs. And you can do that on very dissimilar shapes. You can take the same network training only on chairs and do exactly the same slow inference on laptops and lamps and anything you like. And the compositions are going to emerge. So this is the slow inference part. So we compare here with, so what I want to show in this table is that in distribution, your fast inference and slow inference are similar. Okay, your ARI, by the way, higher is better here. But outside of the distribution, look, the 3D detector, right? The fit for 3D detector really has a very small value here. Learning to group with another baseline also, has a big gap, and our model also has a big gap, but through slow inference is able to improve that performance. All right. So the slow inference really closes the gap between out of distribution shapes and in distribution shapes. Yeah, and these are some more results of generating fast and slow networks versus feed-forward detectors. And here is now we went back to the crazy shapes that we saw, and our network is able to segment them. Not using fast inference. If you feed this shape into our model, it's going to spit out something nonsense, but then you can do a slow inference and adapt its weights in each of those training examples, and essentially there's going to be a search over the decomposition. Yeah. So the question is, how do you use how do this curriculum that I just described may not be easy to do, all right, for all different setups. So here are things that we have considered. One is that you can use these generic shapes, and if you use generic shapes as opposed to chair shapes, you will do much better out of distribution. You see here you get 0.6, while before it was 0.5. All right. So the more generic your primitives, the better, as opposed to using chair parts. What we found though is that you can get decent results if you just train the network, train this model semi-supervised. For scenes that you have labels, you can just inject those labels the same way you train a detector. All right. And for scenes that you don't have labels, then you just have your reconstruction objective, and still you're going to get the benefits of slow inference. Now the sure thing, so here's the comparison between detectors and the model. For detectors, we have a Hungarian matching, right, between the predicted parts and the ground truth parts, and there's no rendering. While in our model, there is this decoder here that essentially is trying to generate back the part content. So why I like this approach? Because I think our model should be able, when they're confronted, easy scenes and difficult scenes should not be treated the same. They should not all go through the same 100 layers or 30 layers. We should be able to have a mechanism to have a compute that varies with the difficulty of the scene. And this type of slow inference can achieve that. Now, for sure, this is not the right architecture. This is not the final answer of how to do neural architecture with feedback. I mean, this is something that we're investigating, but this is just some first, let's say, attempt. And you can do similar things with images as opposed to 3D point clouds. There, the curriculum will be, instead of parts, you're going to have single object images, and you need to have two slots, one for the foreground and one for the background, and you pre-train your model, and then you instantiate more slots and you auto-encode the scenes, and you'll do much better than slot attention models or UORF and so on that uses similar object-centric biases. Okay. And here's some segmentations. And here is, again, the model can do view prediction. By the way, for the image case, I forgot to mention that we have the same cross-view prediction. One view comes in, it is decomposed, and another view is actually predicted. So there is cross-view encoder as opposed to single image. Now, just for the purpose of investigating how the model works, we also create a synthetic data set. And you see here, there is a very tiny little object, okay, visible, but the network is able to predict that, yeah, this is a separate object, and actually it can be a modally completed into that shape, right? So we do want our detectors not to label only the visible, but imagine the invisible, okay? So in this particular model, there's no explicit 3D bottleneck, but the imagination happens in a 2D space. And here you can see the slow essential inference that, as you see the model, as it's trying to minimize the reconstruction loss, it actually occasionally finds the right solution. So the right thing to do is, during your slow inference, you find when you got the smallest reconstruction error and pick that solution as your final answer, let's say, okay? And here is the adaptation on some scenes with food, okay? So these are very interesting scenes because the food occludes. One ingredient includes the other. You do want to understand that there's a cracker here, right? It's not just these visible pixels, which is what detectors do. And here, the network can understand that there are different crackers and also renders them in the right way, in the right order, to fit, the plate, let's say. All right. And by the way, rendering pixels may be a terrible idea. The right way would be to render features and do contrastive matching, the same as done previous that I described earlier. And these are things that we're looking into. But in any case, this important common sense about how objects look, how you can segment and see how can you model it completed, and these are different results. So thank you very much. That's all I have to say. These are the students that actually worked on this work. Mihir, Adam, Fish, and Shamit. Mihir worked mostly on that last part that you saw, and Adam and Fish on the earlier part. And these are the papers in case you want to, take a closer look. And I'm very happy to take your questions.
Because that mic is not connected to Zoom.
Sure. Are there any questions?
Just one question regarding your slow pass methods. What do you think about the importance of adding the temporal domain?
Yeah. So the question is, what about videos? Because this is a workshop about videos, and you just showed images and point clouds. Yeah, that's very important. So videos are very important for supervision. For example, instead of me getting a plate full of ingredient, messy salad of fruit salad, right? I would like to observe how that salad got made. Because if I observe the process, I can have much stronger supervision about the scene decomposition. So I think supervision should happen in videos, but then once you're supervised in videos, you should be able to decompose the scene from a single image, much like all humans can. Thank you.
When it comes to the 3D feature maps, I'm curious, you showed these being used for video. So along similar lines, to what extent do these 3D feature maps learn a temporal domain or multi-view consistency? And if so, what features enable that?
Right. So multi-view. So the question is, do these 3D feature maps handle dynamic scenes? Maybe you want to say. And also, how do they have this cross-view consistency, correct? Yeah, so I don't know if you remember on these videos that we saw with the objects and 2 and 4, you saw that they really understood multi-view consistency. And the same videos, pretty similar views you can get with a single image. So you feed the object a single image, then this object, instantiates its feature map, then you neurally render it, and you see these beautiful videos that indeed make sense. That's how the world must have been, right? So for sure, cross-view consistency emerges because you supervise for that. You say at training time, make sure you give me this image when I put my camera this way, right? So for sure, cross-view consistency emerges. Does this make sense?
Yeah, it's really interesting. Thank you.
Yeah, sure.
Was very interesting. My question is that it seems that for doing these 3D representations are very useful for all the generalization, and they also seem to be very data efficient. And one of the problems that we have right now with these big transformers, for instance, is that we need a lot of 3D data. So do you think that it would be possible to export what you have now in the 3D domain to the domain? And I guess that's related to his question about do you think that maybe with video it would be possible to obtain multiple points of view, or you think that 3D vision is necessary? Like humans have 3D vision, for instance.
Yeah, so I think the question is, what do you think between the two things, which is the way forward? Great question. So the truth is that I'm not sure. That's why we develop both of them in parallel. Now, the truth is those 3D feature maps, they're features, but the map is metric, okay? And it uses calibration and so on to be built. And for sure, humans don't have 3D feature maps. So the way I think about how this 3D and spatial representation should be obtained is still we scatter the 2D features in the 3D space and we just observe them by rendering, and you just leave those features as a cloud of feature points without really needing to instantiate them in explicit 3D metric grid, for sure not. And the scene transformers have showed a little bit how to do that, okay? Now the other thing is 3D the answer to low shot image recognition? Maybe this is your question. Yeah, I mean, people have showed that if you have depth channel, right, and you ask your model to render depth and so on, maybe you'll be able to get rid of the, let's say, appearance or texture information that can be misleading or can dramatically change from train to test, correct? Yeah, so from that respect, yes, I would imagine that it will really help us to learn more shape relevant features as opposed to texture relevant features.
Do you have an understanding of how the downstream tasks affect the 3D feature representation? So whether you're trained for rendering consistency or whether you're trained for object detection, does that change the 3D feature representation? And if so, how?
Yeah, great question. So the question is how the downstream task changes the 3D features, or the 3D features stay the same independent of the task. So let me give you a concrete answer. We use these 3D feature representations for manipulation in our latest Coral 2021 paper. And we had one feature representation for grasping. And essentially you would look the features of the object and you would select which policy to use to grasp it. So the plate, you really had to go low, and for cup, you had to go high and so on. And what we found is that you needed very different features to select grasping versus to select how to push the object. Okay, so you need to pay attention to very different details. So there are some features that you learn to be able to reconstruct the world and every little pixel, but it turns out this is not what the brain does. They say even when we render, we don't render all the way down to pixels. We render up to some mid level, and somehow we are really able to adapt the feature representation for the task. And I think this may be relevant to some in-context learning that Hugo was talking about. And these are things that we're trying to work on. How can you allow in the same model to be really use extremely different feature representations depending on the downstream task? But yeah, basically we found that we cannot share features across tasks, or that you really had to fine tune. It's not like a golden 3D feature representation that will enable everything. Yeah.
Thank you very much, Katerina.
Thank you. Thank you very much for inviting me.
What this one? Yeah. But this is the end, no?
Yeah.
Oh, no, it's the second slide. Okay. Okay. I'll introduce you. Okay. So now we'll have Mohamed El Hosseini, who is an assistant professor at KAUST. And since fall, he has been a senior member of IEEE and a member of the International Summit community. Previously, he was a visiting faculty at Stanford. He's been at Baidu, Facebook, and he has a long trajectory. His primary research interest is in computer vision and especially in efficient multimodal learning with limited data in zero and few shot learning and vision and language. I don't know why it goes to the second slide. Maybe you have a timer.
There's something, yeah. Thank you so much for the nice introduction. I would like to thank the organizers and for organizing this great event, and it feels great to be back in person. So today I would like to discuss with you what we might refer to as imagination supervised machines and how it can be used for some useful tasks. It can relate to some of the topics that I think this was discussed today in this workshop. Before I start, I'd like to thank a lot of students and interns that has contributed as members of the Vision Care Group that I lead at KAUST. So we are all aware about supervised learning, semi-supervised learning and unsupervised learning, which has led to tremendous success over the past decade. And in supervised learning, we have access to all the labels. So in the standard recognition task, where we want to recognize few classes like cats and dogs, we have access to all the labels. In semi-supervised, we have access to some labels. In unsupervised learning, we have a large set of unlabeled data, and we need to learn representation, but we don't have access to any labels. One thing I would like to suggest today is that we can also improve learning systems by imaginary data. And this can happen through different applications. So I'll go through different steps in this talk, how imagination supervised learning can help recognition, creation, self-driving, and maybe express affection. So these are the references for the works that I'm presenting in this talk. So for future, you may refer to them. So let's start by the first step, imagination to see. And for that, I would like to introduce zero-shot learning. And maybe all of not all of us are aware about what brachioculate is. But if someone describes that to you in language and say that this is a bird that has a short orange beak and the plumage is dark above and white below, maybe recognizing this unseen bird species, if it's that for you, wouldn't be a difficult task. And this shows that we can imagine beyond what we have learned by just composing this component. Like we understand what beak is, what orange beak is, but that particular composition, that bird has an orange beak and has the dark plumage, and a plumage that's dark above and white below might be unique to that particular bird. This shows that people can learn and imagine from language description, or maybe we can build machines that learn similar to us. One thing I want to share with you that this is explicit imagination has been successful for tasks like zero-shot learning, and this can be modeled as something like this. So you feed a language description like the one we just introduced into a GAN model that hopefully imagine how this bird may look like in some feature representation space. A successful generative model is the one that is capable of generating discriminative feature representation for different species, even if the difference is in the peak of the bird, so that you can tell them apart from one another. And not only that, can hopefully also recognize them from seen species. This has led to at that time, this is a paper from CVPR 2018 that led to a significant improvement from 37 to 42% in zero-shot learning benchmarks. And this also has been observed by several other papers that appeared in similar time in few-shot learning and zero-shot learning literature. So why should we care about zero-shot learning? Maybe that's another question we might think about. From like biodiversity perspective, let's say that this kid is looking at this bird and out of nowhere it flies away. And in another situation, we might actually have to fly away. Otherwise, we could be a meal to this hungry bear. In both situations, and from biodiversity perspective, we care about both the bird and the bear, and we would like to identify the instances of those species at the fine-grained level. So maybe some decision makers can take some actions. So we might imagine that we might interact with this robot that loves the environment, and this like this kid who was curious to know about this bird might ask, I saw a bird that has an orange beak, and maybe the AI system that loves Mother Nature is not clear. Maybe he will ask more and more questions till it knows already what it really means, and then it can identify that bird hopefully in a certain location, and then maybe the kid can go and look more and understand and learn more about that bird. That's one perspective for generative modeling for facilitating recognition, basically. And from let's get to the second station, imagination to create. And actually, to just clarify, the system is quite. I think I needed to comment more on this slide. The system is quite similar to standard conditional GAN model. So the input here is a text, a description of the unseen class, and a Z vector that represents within class variation, and that will produce feature representation for that class that are then trained to trick the discriminator to believe that they are real. But at the same time, each one of the seen classes are assigned like a location, an index in a second hit of the discriminator that is assigned for scene classes. So, and this is how the model is trained, basically. Please feel free to stop me if you have any questions. That's the key. There are some other key machineries that suppresses the noise in the text description, but the spirit is the same. All right, so getting to the second stop, imagination to create. So it's also still about building generative models that hopefully facilitate creation of novel art and fashion. And in this case, let's say I'll go over creative adversarial networks. It's a paper introduced 5 years ago in the International Conference on Competition Creativity. And in this case, let's imagine that we start from a set of art style classes like hard instance, abstract art, cubism. And the goal is how do we encourage the model to explicitly deviate from scene art style norms, so hopefully produce something that is different and hopefully people might like and maybe might have some emotional experiences towards it. So the inspiration came from the principle of least effort by Colin Martindale. It's a theory that relates to human creativity. And what is plotted here is in the x-axis is novelty and y-axis is likability or hedonic value. And what is shown here that if novelty is low, people may not like the work. But as novelty increases, people start to like the work more and more, but not for too long. When the work is too novel to understand or to relate to distinct concepts that we are aware about, such lack of understanding will lead to lack of appreciation. So let's imagine that we just feed the raw data into a generative model, and see what happens. What we observe is that this might generate let's say the Mona Lisa again. It's a beautiful picture, but it's not a novel content anymore. And the point, the suggestion here or the idea here is that I think the GAN model doesn't have an explicit teaching signal that encourages the model to produce novel content. And creative adversarial network is about augmenting GAN model with an explicit signal that encourages it to produce something that is different from what it observes during training. So we started by these 20 art styles, including abstract art, cubism, impressionism, high Renaissance, and so. And we added a loss function, and this loss function is meant to do exactly this, encouraging the content to be different. As you can see here, that this is done by an entropy loss. So the model is quite similar to GAN model, but we added another head for style classification. So let's say if we feed the painting like the Mona Lisa, we want to trick we want to classify it as real, and at the same time this will be classified to the high Renaissance style. But on the other hand, when we train the generator, we want to trick the discriminator to believe it's real, but at the same time we want the generated image to be different from what it have been observed during training. And we do that by encouraging the entropy over scene art styles to be high, meaning it should be hard for the discriminator to classify which art style the generated image is coming from. All right. So if we have pictures like the Mona Lisa, this will lead to a low entropy because it will be most certain which class this image belongs to, high Renaissance. If we produce an image that is more in between or more like deviating as much as we can from existing style norms, that will give high entropy, and hence the loss will be what we desire. Right.
I like it. It's really cool. So who painted it? A machine.
It's actually the first work of art made by AI to be sold at Sotheby's. Sorry, I'm late, Dana. I got caught up.
So this is one of the pieces that in 2018 was featured at HBO Silicon Valley, but that was produced by this algorithm. And these are a diverse set of paintings that were generated by the method back then. And at that time, got covered by New Scientist and MIT Tech Review and and it was also exhibited in many places. Like next, we also implemented that in in the fashion space, and we observed a similar ability for the model to produce different shapes. For example, this pants was extend arm sleeves. The model didn't observe during training like something like that, but it has observed with t-shirts and pants, and hence the model was capable somehow to produce some like fashion designs that combines both. This work is led by Othman, and joint work with Antoine, Yan, and Camille. And yeah, it was it received the best paper at ECCV in 2018. So one thing I want to share as well is that these two like tasks can circle back to help each other. How in a paper where that appeared in ICCV 2019, we rethought about this wounded curve that we discussed a little earlier from human creativity perspective. We thought, how would that like be helpful to rethink zero-shot learning? And we proposed this creativity-inspired zero-shot learning work, where if we think here that in the x-axis novelty against scene classes, and y-axis is generalization performance, meaning the ability of the model to recognize unseen visual classes from the language description, and hopefully telling it apart from seen classes as well. If the model is capable only of producing for unseen classes representations in that space, like seen classes are closer to like have a smaller distance to the seen classes, right? So then the model will be confused to tell apart something like parakeet auklet from crested auklet, because they are very similar. They both have orange beak, they both have plumages that are dark above and white below, but this bird has a curved feather that comes from the top of the head of the bird. So this, if we don't have a powerful and discriminative generative model that can generate different representation given these slightly different language descriptions, it would lead to poor generalization, right? And this is not something we want. As novelty of the generations of unseen classes increases, this will expected to improve the generalization, but we don't want that to be too much to disable transfer from seen classes, because seen classes is what enable us to learn what orange beak is, what plumage means, and etc. So we just started with the same method from the CPR18, and then we added a loss function that can be thought as an exploratory learning signal that hallucinate text representations of unseen classes. Let's call that TH. I will define in a moment what that means. But let's assume that TH is a text representation that explore the unseen space of semantic descriptions of unseen classes. And then let's feed that to the generative model. That will lead to some visual generations. We want that to trick the discriminator to believe that it's real, because we want this to be a realistic learning representation. But at the same time, if TH, with assumption that TH is a hallucinated representation of an unseen class, one thing we want to encourage that this should not be classified to any of the seen classes. And hence we added a high entropy loss function over seen classes here to encourage this exploration of the hard negative space of seen classes to be hard to classify to any of the seen classes. And hence this improved the representation when we check the results on recognizing, for example, crested auklet, an unseen class, and parakeet auklet, a very similar seen class. The model was capable of improving the performance of telling this apart from one another significantly. And we have in the paper, they reported the performance on 7 benchmark datasets, and all of them, this additional loss has improved the performance. So you can get to the paper for more details. So the third station is self-driving scenarios. So in this case, we have, let's say, in motion forecasting is a task that people in self-driving cars care a lot about. And in this case, assume that you have maybe the past trajectory of the ego vehicle and also surrounding vehicles, and you want to predict where the car is going in the future. Let's say 3 or 6 seconds. And this is a multimodal problem, because if a car is at the intersection, there are multiple possible futures. It can go to the right and can go straight, can go to the left. So by nature, this is a multimodal task. So and here in HalentNet, we proposed an approach that is also related with, that is based on generative modeling, to also improve the generalization performance of this task, with a similar idea to the one that we use for creation of art and also recognition of unseen classes. So yeah, so the baseline at that time, this is like 2021. The baseline was Trajectum++ by Stanford Autonomous Lab, and they were basically an autoencoder based method that encode the past into some representation, and then there is a discrete latent variable z that represent the future intent, like the driving intent. So given the past and I sample z is a 25-dimensional discrete latent variable, and every intent is hopefully predicting a possible valid trajectory in the future for the car. All right, so this is how it is designed. We complemented this by making a difference between two things, what we call a classified intent and another one called hallucinative intent. Classified intent, by classified intent, we mean that we fix during training, we fix a particular intent, we sample an intent, let's say one of these 25, and then we predict a trajectory for that sampled intent. And then we feed it to, we put it in the map, and then we feed that to the discriminator. And we want while training the generator, we want the discriminator to classify this to the intended like z, like to the target intent, like that we input here, and at the same time trick the discriminator to believe that it's real. All right. So this will help the model to be more capable of telling apart predictions that comes from different discrete latent intent that we learn along the way. But let's keep in mind that these latent intents are latent classes. So this is one difference between this application and previous application. In previous applications, scene classes are known. We know their names. In creativity, we know existing scene art, scene style, art style classes. Here we learn these discrete latent classes. And here this loss is helping telling them apart. And there's another loss we call hallucinative intent loss, where what we do is that we sample an intent and then at a random time steps, we predict that for 6 seconds in the future. And 6 seconds means every half a second there's a prediction. This is, let's say, 12 data points. So we pick one driving intent, and at a random time step, we switch from driving intent Z1 to, let's say, Z5. Okay, but at the end, that will lead to a prediction of a trajectory. We'll feed that through this system, and it will lead to a predicted trajectory. We put it in the map, we feed it into the discriminator. We encourage the discriminator to believe that this is real. And at the same time, we want to make it hard to classify to any of the existing driving intents. So it's like a mix up intent. So what does this do is that while mixing up intents, it encourages the model to predict a safe or a smooth trajectory, and hence it makes the model more capable of predicting better trajectories. This reflected in the performance by let's say if we want to predict 6 seconds in the future, the final displacement error got reduced from 6.7 to 4.9. This is more than 27% reduction. And the road boundary violation, which is the percentage of like trajectories that hit the road boundaries got reduced from 19% to 9.2%. So getting to the imagination to feel stopped. So this is in this work we work on. It's less related to it's related to generative modeling, but from the perspective of language generation rather than image generation. But we'll get back to that after later. So in this paper, this is a joint work with Panos, Max, Gleespik, and Professor Gibbs from Stanford. And in this work, we focus more on introducing a data set that hopefully helps us study how do we build human compatible AI systems that are more aware about our emotional being. So most of the existing vision systems focus on recognizing maybe there's a cat, there's a dog, there's a snake, but maybe not much into, let's say that this is something, this is right now a bunch of applause, but when I observe that this is a snake, this might construct an emotional fear experience, for example, right? So there is probably less work in maybe in vision about that emotional aspect. And one goal of this dataset is to move one step in that direction. So the motivation is to have like some more effective captions. So and embrace diversity. Some people might have positive experience from this. From getting exposed to art pieces, some others maybe not too much. In this same painting, a person felt that this dust makes him feel uncomfortable or sick. Another person captioned this like felt that that this is reminds me with a night sky with the stars. Right? So if you contrast that to COCO dataset, this is an example of the COCO dataset, which is one of the like most influential dataset in our community. The focus more is on factual objects that exist in the image, like for example, many large kites flying in the sky, etc. But there is less focus on the emotional aspect of the unsettling balloons. Right? So and if you go into more examples on that, contrasting how we talk about birds in Artemis dataset versus COCO captions, you will observe more differences. Like this is a picture of a bird that gives me hope. In COCO, a baby sitting on a table drinking out of a cup, and so on. So the focus is just a little bit different. And to introduce this difference, that was caused basically by how we collected the data to start with. So in this case, we have collected dataset of 455,000 on 80,000 unique paintings from the WikiArt dataset, which covers basically masterpieces and interesting pieces from our art heritage over the past like 5,000 to 10,000 years. And we ask people first, choose an emotional experience. When you get exposed to this visual stimuli, what do you feel? And you have to pick one of those or something else. Something else means that he doesn't feel anything or something different, or something different from those. And then the description here is a justification of why he or she felt that way. So after we did collect the data, we observed this distribution. Most people actually felt amusement, contentment, excitement, a small percentage of anger, disgust, fear, sadness. And as I mentioned, the goal is to embrace this diverse emotional experiences, because this is it's okay to have positive and negative expressions. So in this CVPR, we had a follow-up, like a second iteration on the data set. We named it "It's Okay to Not Be Okay: Overcoming Emotional Bias and Effective Image Captioning by Contrasted Data Collection." And in this work, we observed some opportunities in the first version, where we found there is a strong bias towards like positive emotional experiences, amusement, awe, contentment, excitement, and there is far less negative experiences. And we felt that maybe there's some bias because people know that this is art pieces. Maybe they are biased towards some emotion versus the other. So And another thing that we've observed that the captions are quite generic. So some of the description we observed was something like nice looking painting with bright and nice color scheme. This is an okay description, but it's not as particular, it's too specific about this painting. And we wanted to try to do something to fix this problem. So we proposed the Artemis 2, and you can see that as a result, like this is a difference. Like before, this is a positive and negative distribution of positive and negative experiences. This is the distribution after. And the gains are basically that based on the same benchmark set, the performance with the same this training set size, there's a gain in CIDR score about 20%. And at the same time, we did human evaluation, and 73% of the human evaluator preferred generations from Artemis 2 models. I will explain a moment why this led to this result, like what explains this result, despite that the dataset size is the same. So the thing here is that we collected the data in a contrastive way. This means that we try to encourage more and more similar images to construct different emotional experiences. So, for example, let's look at this. Yeah, I think this is not so. I'm not sure if you see this, but let's say this particular example. Like this we have here a picture of like a vase, and the feeling towards it is contentment, and this is an iris neighbor painting, right? The Artemis one has this, like the blue and the deep blue purple color give these depths and makes the fruit stand out. Another, like in Artemis 2, that was the answer. The green mold on the rotten fruits on the table is disgusting. So we wanted to have by design an encouragement to have similar like paintings, like in terms of color and information and visual similarity are similar, but they hopefully construct different emotional experiences. The way we do that, and the reason, motivation behind that was actually, and the reason behind the name of the paper is actually related to the, It's Okay to Not Be Okay is actually a Netflix series about three friends who went through hard times, and they were helping each other to heal their emotional wounds in some sense. So you can think of this work as an AI or data version of It's Okay to Not Be Okay. So how the data was collected is that we pick paintings, we go over the paintings that have dominant emotional experience, whether it's positive and negative, and we asked participants, given the 24 nearest neighbors, only 4 shown here, to pick an image that is similar yet construct an opposite emotional experience. So if the given one is positive, I want the person to pick one that may construct a negative emotional experiences and vice versa. So if you look, this is like a video that shows how it looks like to annotate the data with our interface. You can see that people can hover and zoom in and take a look at the painting while picking the nearest neighbor painting with the opposite emotional experiences. And based on that, they get routed to an interface that helps them annotate this with a caption that describes why they felt in that particular emotional experience. All right. So in total, we collected 260,000 contrastive example. In terms of the benchmark setup, the dataset size of Artemis 1 and Artemis 2 are the same, but the way Artemis 2 is constructed is by the new data that we collected plus 50% selected at random from Artemis 1, and the training data for Artemis 1 is the original setup. And the evaluation is exactly the same as the original setup. So we didn't construct our own test data for fair comparisons. And you can see that this is all the 20% gains that I was referring to. And these are some example generations. We observed that the captions are are more detailed and less generic compared to the version 1. And in average, we uncovered emotional bias, and we collected Artemis 2 to overcome this bias. And this is just the example that I was referring to. And the performance was superior in terms of CIDR score and also human evaluations. 73% prefer the captions generated by Artemis 2 models versus Artemis 1 model, despite the training size is the same, and also the training model was the same. The captioning model was the same. So this is it. One more thing, and we this year at the international conference in competition creativity, we proposed something that is an improved version of CANs, like that we talked about earlier in this talk, called Creative Work Adversarial Networks. We abbreviate this as QUAN, and it's a new model that encourages encourages novel art generation. So these are some examples, and the thing that we observe is that the model is capable of produce images that are novel and hopefully higher in terms of human ratings. So these are like these two, like this slide shows the contrast between Artemis, like CAN in 2017 and QUAN in 2022. The idea of this approach is to construct a random walk class that starts from scene art style class. Let's assume that C1, C2, C3 is abstract art, cubism, impressionism, etc. And the gray points are the images, the art pieces that are generated in the current mini patch. So what we do is that we start from each one of these art style centers and then go for a probabilistic random walk for T number of steps through the gray points, and then compute the landing probability over back into these style classes, into these style classes, and we're encouraging the model to deviate better from scene style classes. Technical speaking, we construct three probability matrices. One from the scene art style classes to the orange points. So this is, let's say, 3 times n, and then another one from a transition probability matrix from every generated point in the current mini patch to every other generated point in the current mini patch. That's n times n for T number of steps, and then a third transition probability matrix of n times 3, which projects this back to a probability over the scene art style. So this is 3 times n times n to the power t, and then n times 3. That constructs a 3 by 3 matrix. But what does this matrix mean? This matrix means what is the probability of starting from class I and going for a random walk of T number of steps through the generated images, and then land in class J. And what we encourage as a deviation signal is to encourage this random walk to be uniform over all scene style classes. So no matter which class I start from, go for a random walk for the images that I want to be novel. I want to make it hard for the model to land in any of the classes that I start from as a deviation signal. And that led to convert to style GAN and a style CAN, which is a version of CAN, but implemented on top of style GAN 1 and style GAN 2, improve significantly the ability of the model to produce paintings that have ratings of 4 and 5, which is significantly better, and it was more capable of images that are different. This is the nearest neighbor distance from the training data, and have a higher likability score. So it achieves somehow some balance and reconstructed this similar wounded curve to the one we talked about earlier. So we want to generate something novel, but not so novel to generate something that we might not like. And in addition to that, we produced diverse emotional experiences. Yeah. Okay. Now, can you read it again? I guess slideshow. Slides from the current slide. Yeah. Okay. Yeah, and that led to we did some study. This is an unconditional model, but we wanted to study whether the generated paintings would have an emotional impact on human participants, and that led to that distribution. So the model was capable of producing different images with diverse emotional experiences, but 13% of people felt that it's confusing. Like maybe this means 13% of the generated images might not be very meaningful. And these are some of the captions that people describe generated paintings. So this is, for example, the appearance resembles more an exhibition of Egypt in the museum, and etc. So going back again, like this same loss that we talked about for improving novel art generation, we applied it back for zero-shot learning. In this case, you can think of the same thing, but we generated this class centers guided by the class description of seen classes, and we hallucinate unseen classes so that it goes through this same random walk, go for T number of steps, and land into land with high entropy over these seen classes to help deviate seen classes and telling them apart from unseen classes, like unseen classes from unseen. And then that led to an improved performance in zero-shot learning as well. This is some results compared to actually, I think we compared to a generative modeling paper that is appearing at the CVPR, and the performance improved on top of the CVPR 22 paper. So yeah, like this is basically the story that I would like to share with you today, and some other like related work that we do is like that's appearing in this conference, Visual GPT. This is a paper that tries to distill knowledge from GPT-2 model. Let me go quickly to the main idea. So the main idea is to have a gating mechanism that tries to distill knowledge from GPT, which is a language only trained model, to improve image captioning, which is producing a text description given an image. And the key idea is to produce a gating mechanism that can distill knowledge from the pre-trained language model versus what you have learned from the data. And the trick here was basically that we have the gate values that are close to zero, but not exactly zero. This allows small gradient to disrupt the existing weights of the GPT-2 model. And what we did simple change in this gating mechanism to cut it after a certain point, and this led to an improved performance, like in compared to this gating mechanism. So we have this like result that shows, for example, that is a picture in low shot image capturing. This is just to clarify. This is a low shot setting. Maybe this is not the case for like if you have full access to training data, this might not be valid. So a woman and girl sitting on a table with a birthday cake, and maybe other models struggle a little bit on that. This shows the performance if we train on 0.1% training data, 0.5% training data, 1% training data, and you can see in all of them there is a significant gap. We also tried that on medical report generation data set, and you can observe that the gain compared to state of the art is also meaningful. All right, Visual GPT, I would say it can connect to effective like image captioning data set that we talked about earlier, because maybe you managed to collect the data in English, but there are many. We want these models to work to be more representative for different cultures and different backgrounds and different languages, but we might not have the capacity to collect data for all languages. So maybe data efficient captioning models can enable us to enable captioning system to work better in all languages with small additional data that we collect for each one of those. So this is the point I want to make, and then work a bit on the opposite direction, effective image captioning to visual art generation. Use dark color to make it seem as if ships are going to an enormous place. We have some results from that. We extended some like technical novelty to enable the model to produce an INR-based representation, so that it constructs, actually, given that language description, it constructs a neural network for every image that takes XY coordinates and produces an RGB value. This enables the model to extend, to generate images of an arbitrary aspect ratio and complete and extend the scene beyond the scope that is used during training. At the same time, more to be conditioned on text. So it can extend outside the boundaries, and it also can generate images with an arbitrary aspect ratio. This is how it looks like if you applied it on standard dataset like birds. So it may extend the tail of the bird, like the branch of the tree, and etc. And it was based on a paper that an unconditional INR GAN paper that we presented at CVPR last year. That basically like it adapted style GAN architecture so that given a Z vector, it produces a neural network that takes as an input XY coordinate and produces RGB. And the image itself is produced by iterating at every XY coordinate and producing the actual RGB after you predict this neural network. So we recently adapted that to be conditioned on text, and we work on a bunch of other stuff for distilling knowledge for compositional recognition, like let's say, for example, a zebra climbing, climbing over giraffe. This might be a rare event, but you might still want to understand it. So we had some earlier work that will appear this Friday. So if you're interested, you may take a look. This is still compositional because most of these compositions are probably not seen during training. So it still relates to limited to learning with limited data. So this is really transformer, and last thing I want to conclude with is that we also propose at this CVPR tomorrow. Actually, we have our presentation style GAN V. Is I think to our knowledge the first video generated model that can train a successful long videos, an hour-long video, with sparse training points, like with only few frames, like 3 or 4 frames or something. This is led by Ivan and collaboration with Sergey from Snapchat. So you can see that this is how it looks like. It worked consistently better compared to the state of the art at the time. But as you know, like we are in a fast-moving field, I think there are papers in archive right now that probably beats this result. And it has, and since the model is inherited, so the point here is that it is only 30%, 30% better than the closest runner-up. Another thing is also only 5% more expensive than style GAN image generator. So this makes it light, and since it's based on style GAN too, it makes it easy to also do clip edits, like person with mustache, and then you provide a video, like you generate a video for Barack Obama, and then we just make this clip edit, and then you can clip the video similarly with it. So this is just perks that are inherited from style GAN too. These are some other generations with jellyfish motion. I think we have this is style time lapse. This also can extend stably for hours. Maybe some of the limitations that maybe after some point maybe some of these motions might repeat. I would say this can be a room for future work, and yeah, and these are the references and for the work that I discussed with you today, and thank you very much for being with you today.
We have a bit over time, but maybe we can make one question. Okay, thank you very much. So now we have 2 spotlight talks. The first one is by Karim Urgil's CFI constraint-based fine-tuning approach for generalized few-shot object detection. and this one will be virtual.
Wait, pause. Have to put the volume on it. No.
Hello and welcome everyone. This is Karim Gerges from Robert Bosch Research, running in Germany. Today we'll be presenting our paper titled Constraint-Based Fine-Tuning Approach for Generalized Few-Shot Object Detection. So to begin with, few-shot object detection, or FSOD in short, is a subdiscipline of few-shot learning, inspired by our cognitive ability as humans to learn new concepts from a few examples. So the goal is to adapt object detectors quickly on new tasks with scarce data. So as we can see in a simple example on our right hand, that we perform a base training stage where we train on base classes with abundant data, and then we try to leverage this knowledge or prior knowledge to learn the new classes with scarce data in a fine-tuning stage. However, one drawback of such an approach is that fine-tuning only with novel classes can result in catastrophic forgetting, which is the phenomenon where we forget the classes we have already learned, which in this case are the base classes. So later came generalized few-shot object detection, which is an emerging subdiscipline of FSOD, focusing on detecting novel classes while alleviating the forgetting phenomena. So the goal is to adapt now object detectors quickly on new tasks with the scarce data without forgetting the old classes. And this is usually done by leverage a few shot of base data. So as for the recent GFSOD methods, TFA attempts to avoid forgetting by fine-tuning on base and novel classes using 3:1 ratio. Then later came ones that tackled the problem in an incremental setting where it meta-learns a class code generator to synthesize class code for the novel classes. Then decoupled fuzz RCNN also was based on joint fine-tuning of base and novel data with some architectural modification and gradient manipulations. Last but not least, retentive RCNN proposed an ensemble learn-based approach that is a distillation-like manner that leverages both the base and trained RPN and detector heads along with the fine-tuned ones for alleviating the forgetting. So another paradigm that shares a similar interest of learning without forgetting is the continual learning. An interesting line of work in continual learning is called gradient episodic memory, or GEM for short, which aim to represent the forgetting of previously learned classes or tasks when the angle between the lost gradient vectors of previous or base tasks denoted by GB and the proposed gradient update for the current or novel tasks denoted by GN as obtuse. So hence it projects the proposed gradients for the current task orthogonal to the previous task gradients in case of violation as shown in the figure below. However, the question is this constraint enough to alleviate forgetting in our case? So to this end, in order to encourage more effective knowledge exchange between both tasks and GFSOD, we further constrain the objective function and hence deriving a new gradient update rule. So in contrast to GEM or AGEM approach where always the proposed gradients are projected orthogonal to the base or the previous task gradients in case of violation, we also impose a new constraint where we involve the base task gradients in the optimization function, and hence deriving this single update rule denoted at the end. So what this is an adaptive reweighting of both the base and novel gradients to balance their contribution during the fine-tuning stage in order to alleviate forgetting and reach a better optimum. As for the experiments, we'll firstly present the results on the MS-COCO benchmark for 5, 10, and 30 shot settings. And also, since retentive RCNN proposed a new ensemble-based evaluation technique, we denoted in the second column by with E for fair comparison. From this table, we can see that CFA consistently is able to experience less forgetting with improved overall performance across different models. Similarly, with the VOC dataset, we can see that applying CFA in different settings and models contributes to improved base performance as well as overall detection performance. As for the multiple runs, we perform multiple runs on MS-COCO dataset with different seeds, and we can see that CFA contributes to higher certainty detection. So to sum up, the proposed CV algorithm acts as a plug-and-play module for transfer learning-based FSOD frameworks, and it helps alleviating the forgetting on base classes while improving the overall detection performance. And it does that without increasing the model capacity nor the inference time. Thank you so much for your time and enjoy your day.
Thank you. Now we'll have the last spotlight before the coffee break from Saurav Gupta. And then we'll be back at 3:15 with the talk of Dima Daman.
Hello everyone, my name is Saurav Gupta. I'm working as a research engineer in Mercedes-Benz Research India. This work is in collaboration with my colleagues Saurav, Abhay and Rahul. This talk will describe our work on how vision transformer networks can be used effectively in weakly supervised object localization. In WSOL, the goal is to leverage weak supervision to know the location of the object. In this setup, we are constrained to achieve this without any bounding box annotation, thus saving a lot of annotation cost. Below, we show generated localization map for wolf and bird respectively. In WSOL, we need to understand which weak labels to use. In our case, we use object class labels as weak supervision. Next, we choose a network architecture and train for classification tasks using our chosen weak labels. Finally, we need a map generation mechanism using which we can aggregate learned features from different layers of the trained network. It is very important to train a model in a way that we get rich features which covers the entire object. We identify some common problems that exist in WSOL. Generally, classification models have tendency to only look at discriminative features as they are not directly trained to perform localization. For example, in case of dog, only eyes are highlighted. Also, localization maps are not class specific. For example, the map activates multiple regions across the image apart from volleyball. Third problem is that due to cluttery environment and background noise, localization maps are not very precise. We try to address these problems using our method VTOL, as you can see in the third column. Here we list some key contributions of our method. We choose Vision Transformer to train a classification network due to its self-attention mechanism and better capability to learn long-range interactions. Next, we introduce an architectural change to Vision Transformer. We add patch-based attention dropout layer called PADL layer, which aids the model to discover non-discriminative regions for better localization. We also introduce gradient attention rollout named GAR, a novel map generation mechanism which gets rid of negative contributions and introduces class dependency. Combining above key contributions, we achieve state-of-the-art results on ImageNet and CUB datasets. We compare our method with the baseline approach where we take standard vision transformer and perform classification. It tokenizes the image in the form of patches and learn interactions between them. In VTOL, we make an architectural change by adding PADL layer in each encoder block as seen in the diagram. Motivated from ADL layer in CNNs, we design a PADL layer which processes the output from each MLP layer. This layer comprises of two main components, patch drop mask and patch importance map. Patch drop mask drops the highlighted region based on a drop threshold. Patch importance map highlights the activated region using sigmoid operation. One of these components is selected randomly during training time based on an embedding drop rate alpha. When patch drop mask is selected, the network is forced to look at remaining portions of the object to classify it correctly. As seen in the crane example, each block progressively discovers other parts of the object as the earlier layers have dropped the highlighted ones. This scattered information in different layers of the train network is then aggregated through our map generation method called GA. Here we showcase the effect of using PADL on generated localization map. In case of training without PADL layer, entire objects are not discovered, whereas with PADL layer, entire region for barbell and leopard are localized. In VTOL, we improve the attention rollout mechanism by introducing a gradient term, and we name it gradient attention rollout GAR. Here, first two equations directly come from attention mechanism in transformer. We compute the gradients corresponding to softmax attention metrics and take a dot product. We perform first three steps for each layer and recursively multiply to get the final localization map. We also compare our method against another map generation method called layer relevance propagation (LRP). We showcase some examples how introducing gradient maps helps in achieving class dependency. We can clearly see that in case of tie in basketball, Our method does better in generating class-specific localization map as compared to attention rollout, which highlights the person as well. We compare against other state-of-the-art methods in WSL on ImageNet dataset. We achieve best scores in all the metrics. Here we compute Maxbox accuracy V2, which is a better measure of localization for both datasets. We achieve a large boost over previous methods. We also compare qualitatively on ImageNet dataset with other SOTA methods such as CAM, ADL, TSCAM. Our method not only highlights the object boundaries precisely, but also highlights equally the interior portion of the object, which are non-discriminative and are unlikely to get highlighted as per classification task. On COB dataset, we can observe that our method can detect whole object despite the object being blended with background and in cluttery environments. Thanks for listening.
Yes, this means that yes. Let's wait 1 minute. 1 minute more.
Yes. Well, okay, got it.
Yeah.
Right. I don't have a problem with that.
Okay. Now I'm going to introduce the next talk. It's my pleasure to introduce Dima Damen. She's a professor of computer vision at the University of Bristol. She's currently an EP SRC fellow, and she focused her research in automatic understanding of object interaction, actions, and activities using wearable visual and depth sensors. You may know her because of the Epic Kitchens project. And she's also program chair in many computer vision conferences. I'll let you the floor.
Thank you very much. I like yesterday somebody asked me, "Are you Epic?" I'm like, yeah. So I think my name is now called, like synonymous for the data set. Thank you for the introduction and for the invitation and for this very important workshop. And I like the name of the workshop is Limited Label Data. So I'm going to start by asking which really is more important. So we have these three things that we build our current computer vision and machine learning models on: data, labels, and then tasks that utilize the combination of the data and the labels to achieve certain missions. And I want to argue that we have limitations in all these three axes. So we certainly, in certain cases, have limited data, right? We can't get the data. Of course, there is the other extreme we all are aware of, which is we have the data, but we might not have the labels. But there is also the question of we might have the data and the labels and we're not asking the right questions. And over the talk, I'm going to kind of talk about these three things, particularly the limited data problem and our experience with the long tail problem, despite the amount of effort you might put into collecting data. Then, of course, I'll make more emphasis on the limited labels, but I'll also focus on our ongoing work on trying to think about how to utilize better the labels and the data that is available. And let's start with the first thing, limited data. And for those of you who haven't seen Epic Kitchens, I always tell them, if you haven't heard of Epic Kitchens, don't tell me. It kind of drives me mad. So I'm hoping the majority of you have heard of Epic Kitchens by now. And if you've heard of it and you haven't seen it, then this is the type of footage that we have collected by giving people cameras and asking them to go and collect. Basically, put your camera on before you walk into the kitchen and record everything in your own kitchen. And what this gives us is the ability to recognize certain actions. So for example, we have enough examples of people in various settings, in various countries, opening their oven. And I always like the fact that it's natural. So the top left view is actually the heat that kind of comes into you when you open the oven that actually has been projected onto the camera. So this is the type of footage that we have. And for open oven, I think we're sorted. We can now recognize opening an oven anywhere using egocentric camera. But if you look at the data that we have, then this is what we actually are monitoring over around, couple of minutes. You have these actions that are fairly long, like grating the carrots. This is following up by this very, very short action of putting down the grater. And of course, we have the truth, which is anything that's naturally collected is long-tailed. So the y-axis here is log scale. Don't let it deceive you. This is extreme. So we have a lot more examples of certain things than others. And this is the case of actions. And this is also the case of objects, right? So we have a lot more of certain things than others. The most common vegetable in Epic kitchens and apparently in all of our cooking is onions. We've seen enough onions by the end, but there are lots of things that we might have seen only once. Right, so if we talk about images, then everybody understands this long tail or few shot problem, starting from I haven't seen any example to I've seen a few examples or synonymous with the word tail class to that I have seen enough. But I want to tell you that in videos, we have this other complex problem. In addition to the instances, we have the lengths of certain actions. And that really introduces additional complexity in learning. So you have these short and rare actions, like breaking glass, right? It's like instantaneous. But if you want to recognize it, you're not going to find enough examples and you're not going to find enough frames. Of course, there is the other extreme of things that are long and frequent, washing dishes. But there is the other thing that is short and frequent, like opening drawers or opening oven. But you have rare and long, like sharpening the knife. And why am I making the distinction that length really matters? Currently, it's because of the way we deal with videos in video settings. So let's take this not frequent, but long enough video of someone sharpening a knife. And let's see how our models deal with this input. Currently, up to my knowledge, unless someone had changed things, we sample a few frames from these videos and we feed them into whatever you like, whether it's a 3D or a transformer, but you still need to sample a few frames. And with these long actions, we can do these combinations of different samples, allowing us to really learn a lot, right? Because we have enough possible transformations. The problem is when I don't have enough frames. In fact, the short actions, in my opinion, or experience until now, are a lot harder than the long actions and offer another level of complexity in few data in videos that isn't really the same in images. Right. So long tail really introduces this additional complexity in videos. Short actions are really severely disadvantaged. And collecting more data doesn't help. So if you've heard about Epic Kitchens, you might have heard about this brilliant effort led by Meta AI and Kristen Grumman to collect Ego 4D. And we've scaled from 100 hours to 6,700 hours, and we still have the same problem. This is log scaled. We still have the same long tail, and whatever you do, as long as you actually have a limited number of examples of something in the world. So that doesn't solve it. And of course, saying, I want to have a balanced model, let me throw the majority of my frequent actions, produces worse results. So we really don't know what to do with this next step. So let's talk about the current methods. None of them are real solutions that we have tried and telling you what we're currently trying to explore. The one I am very passionate about, I call it compositionality in actions. And this is a paper that we've worked on a while ago, ICV 2019, where we wanted to learn two different embedding spaces for verbs and nouns. So we basically take the sentence and separate the verbs and the nouns. And we only want to learn the verb, right? So the whole thing is about, is this a put or an open, regardless of the object? And then the other space is purely on nouns, regardless of the action. And of course, these two spaces, you can then go from them and combine the information, okay? Combine the information from these two embedding spaces into the standard space that we have. But by forcing the model to go via this compositionality, you're actually forcing the model to understand what is the action here and what is the object. So in this space, this is a very kind of simple model. You can think of it of any blocks. But the most important bit is the fact that the video is projected using two different projections. One projection that focuses on the noun and another different projection that focuses on the verbs. And then you can combine them in whatever favorite way. But if you look at the outcome of these models, and let's focus on one of these spaces. So this is the noun space. And you look at the activations for one neuron in that space, and you realize that it's actually figuring out all of these are chopping boards in different actions. It's actually managing to merge these into the same space, regardless of the actions. And if you look at the verb space, you find open and close of all sorts of objects put together. And that compositionality allows you to, of course, to do zero-shot learning, right? Because if I now know what's open regardless of the object and what's chopping board regardless of the action. That's one way to go around the long tail. And we have been really working with plenty of the examples out there for long tail. And I can tell you nothing really yet works on the extreme examples of EPIC or Ego4D. So there is a real need for people to think about long tail in video. If that's of interest, we'll welcome your input. So I'm not going to talk more about the long tail problem. I'm going to move into maybe what most of us have been working on, which is the limited labels. And I'll start by thinking about limited labels, which is labels with limited effort as opposed to less labels. And that's one of the things we've done when we collected Epic Kitchens, which is to ask people to narrate the videos by giving us a rough timestamp around the action. So we don't have the very expensive start and end time. We have a rough thing around the action, and we call these timestamps. And in this work, we were starting from these rough timestamps and trying to learn a model. So the input is, roughly the action is here, and the output is now you have to learn a model that recognizes the action. So basically, what do? You start with a rough estimate of the action. So you still don't know, this is the initial thing. You sample certain frames, you train a model, then you figure out the response of that model, and you refine your estimate. It's not a huge refinement because you're roughly around the same location until you exactly get the moment in time where someone is opening a fridge. And something I learned when we were working on this project is that when you do that, you don't get the start and end times that humans have labeled. You get these very peculiarly, unique discriminative moments. So if you have the example, for example, of, so this is the refinement over time. You can see these kind of proposals estimated, and you can see the ground truth. And in many cases, you get something a lot closer, smaller than the ground truth. You get the moment that someone is actually opening a drawer or moving a glass. You get something a lot shorter or more discriminative. So it's very difficult to deal with these if you want to go back and evaluate on our traditional start and end times, but it's a way forward. The next bit I want to talk to you about is domain adaptation. And again, we've done a lot of work with that when we collected Epic Kitchens, because we collected another version of the dataset 2 years later, and we realized that the models don't generalize. And that's 2 years later, not 10 years later. All the effort we've been putting in collecting data, imagine if in a couple of years, none of it will be really useful. So in this work, we were looking at actions specifically again, and looking at the multiple modalities that actions and videos offer and how these can be useful for domain adaptation. So we are looking at our standard 3D CNN here, and an RGB and an optical flow, training on a single environment where we have enough examples, and then trying to generalize into another environment. And we all know what happens, it doesn't work. But what's really shocking is the fact that these spaces don't even overlap. Like you look at the space and there is nothing really common between the RGB space of one kitchen and another, despite all your effort that you're training for certain actions. And in this work, this was actually CVPR 2020, the era where self-supervised was really picking up, and we just plugged it into domain adaptation. So what we have is we take modalities of the same action, modalities of different action, and this doesn't need any labels, right? Because you can even do that on the new kitchen with no labels. And just by doing this self-supervised exercise, you end up grouping the big red space that was the new kitchen into these actions that are similar to one another by doing the two modalities. And then with some adversarial knowledge, so this is a gradient reversal layer that attempts to stop the discrimination between the source and target. Eventually, you end up with doing really well. This is someone cutting in one environment and then someone cutting in the new environment, different object, different background, different chopping, different person. And if you rely on this source only, these are spaces that are very, very different. With the self-supervision, you get the clustering and they do get closer, but they don't fully overlap. And with the combination of the self-supervision and the gradient reversal, you end up basically recognizing this cutting environment, this cutting action in the new environment. Okay, so let's move into, I think the reason why I was invited to give this talk is because of our work last year on few shot action recognition led by Toby, who's done a brilliant effort in that. And I learned a lot about few shot and how few shot is formulated through this work. So the concept of few shot is as follows. You assume you have a fixed number, say 2 shots of one action. Let's go back to our examples of cutting. And you want from these 2 examples to recognize new examples of that action. And interestingly, the way this is currently formulated is very, very limited. You assume you have 3 actions and exactly 2 examples of all of your 3 actions, which is like anti what I was telling you about the long tail, right? We never have this exact, right? 3 ways, 2 shots. Apparently, this is how most of the few shot methods currently are formulated. So again, you have this support set and you're trying to learn a classifier using the support set, which classifies the query videos. And interestingly, all prior works in video have assumed that each video is treated separately in the support set. And in this work, we wanted to do something differently. We built this on something that was out there, the cross transformers out of DeepMind, which was really focusing on basically taking a query image and looking at evidence of the correspondence in the whole of the support set. So that was the first inspiration for this work. So basically you construct a class prototype from all the relevant subsets, and we wanted to copy that into all the relevant frames from the support set. But it's not enough to do that on individual images when you talk about actions. So we relied on another really old work that I really like. So this is ECV 2018. If you haven't read Temporal Relational Network, go and read that. I think it still is very relevant, and we haven't picked up on that yet in transformers, where you actually build a representation from a different n-grams of frames. So you have 2-frame relations, 3-frame relations, 4-frame relations. And that's really important because some actions are more fine-grained than the others and thus require more samples to be recognized. So we put the 2 ideas together into what we call TRX, Temporal Relational Cross Transformer. And it goes as follows. You have your query video, say of 4 frames, and you have 2 examples in your support set of class 1. And we build these pairs. So we take 2 frames and we built a 2-frame query and a 2-frame key and value, basically. And we build that from the full support set. So that means we basically here have a transformer. You're trying to basically take the query as a combination of frames from your query video. These are the key linear map projections of your whole support set. This is softmaxed. And then you have the value linear map. And that gives you basically what we call a class prototype, i.e., how similar is this class to your query video? Of course, we started here by only a pair of frames from the query video. That might not be sufficient. Of course, you can compare that to the query, but we want to do that also for all possible combinations of frames. So what you have at the end is this representation of class 1, this representation of class 2, but that has attended to your query video to know what really is most similar. And in the paper, we think that, as we said, 2 frames isn't enough if you have fine-grained knowledge. So we try the same approach for triplets of frames. Similarly, you can produce triplets of frames and find the combination. This is not as heavy as it sounds, because basically most of the effort is on the backbone, which is shared. This is a small head on top of a shared backbone. And if you look at the results, then really this work last year clearly outperformed everything that's out there, and also showed us how people compare to different subsets of different things. So Toby kindly prepared a nice code that allows you not only to compare to TRX, but to things that have existed before us. And if you've used this work, then it's a very well usable GitHub repo. Critically, we showed that some datasets are a lot harder than others. So if you compare kinetics to something V2, which is a more fine-grained data set, you see that looking at a single frame versus 2 frames versus triplets and 2 frames doesn't make such a difference on kinetics, but makes a huge difference on data sets like something. And critically, as in this work, we really focused on utilizing the size of the support set. And thus we have this thing that says maybe in one example or one shot, we don't outperform, but as you go into bigger shots, you clearly outperform. And we show that actually we are utilizing those other support sets. So this is the number of videos in the support set that queries utilize, with the majority of the queries utilizing at least 2 or 3 videos from the support set to make their decision. Okay, so basically, if you've seen this in the paper, you look at it, what it does is that it says, this is the query, and this is the 2 frames in the query. And this is the best support for those 2 frames. And because we use something like temporal relational network, they need to have the same order, but they don't need to be next to one another. So these 2 frames match these 2 frames, etc. And we showcase that for examples like triplets, you can also get better understanding. And I think this is one of my favorite examples where you can see that the person is throwing the paper in their hand, and these 2 frames are things on the floor, which find support for things on the floor, and things in the hand, which cite support from things in the hand, because these videos have all these combinations. Okay, and again, another shout out for Toby's GitHub, which if you want to do few shot video, start there. Okay, moving further, again, there is a lot of emphasis on what can we do with limited labels, self-supervised or synthetic stings. And I want to tell you about UnweaveNet, which is a work we're presenting this CVPR on Thursday, led by Will in collaboration with Carl Bondrek at Columbia. Going back to Epic, and I think one thing that at least has inspired my career is watching the data. So we have these examples of people waking up in the morning, you walk into the kitchen, you start preparing your coffee, so you put the kettle to boil, but while it's boiling, you're not really standing still waiting for it to boil. You go maybe and realize there are some dishes to wash, or you want to put the toast in the toaster. You basically interleave or move between different goals until you can achieve all of them. And that's how we operate. And from the experience of doing activity recognition for years, I know that this is not how we think models need to work with activities. We think the person is going to start making coffee, finish making coffee, and then start making food, right? And that's how most of our data sets and models operate. But if you collect data naturally, you realize that is not the case. And we wanted a model that replicates that understanding, can start from the very beginning, parses the video, and recognizes the switches between different goals. And this ended up being something very similar to what we've all learned in maybe year 1 of computer science. So we have basically a model that has 2 things. It has a controller. It decides what to do with the current clip. And it has a memory, which we call the thread bank. And these 2 together produce an estimate of what you want to do with the next step. The controller is a transformer. So basically, it takes these learned memory information of previous actions. It takes the current clip, and it learns projections of the threads and the clips, as well as this token for new threads, because you want to be able to start new threads as well. And this transformer then just basically contextualizes the clip with the threads and decides which of these best suits the current observation. And eventually, you can update the memory. A few things on UnweaveNet, it looks like, why am I talking about that in limited knowledge? And I'll tell you why, because of the way we train this. This is trained end-to-end, because you really need to understand what clips and threads mean from the data. And it's trained in ways that language models have been trained until now, so teacher forcing. That means you fill the memory up till now with the ground truth, and you just train for the current decision. So at each time step, everything is populated by the ground truth assignment, and the loss is imposed on the current decision. When we realized we needed to train this end-to-end, we realized we will never have enough labeled data. And that's where we now relied on lots of this synthetic or self-supervision. So we proposed self-supervised training for UnweaveNet that basically starts by saying, okay, let me invent a story that has 3 threads. The first thread has 3 clips, etc. We're inventing something, and then we're taking one video and positioning our invented stuff into the video, right? So we kind of are putting something in the video, and these clips have some variability in distance and location. Critically, they are from the same video, otherwise it becomes a trivial solution. Then we really interleave them, making up this synthetic story, which we then use to train the model, because this is already, we've built this. So we know the decisions. Is this a new thread? Is this resuming a previously paused thread? Is this, etc. So we've built all of these, and we have thousands of these we can then train the model using. That's not enough, because that doesn't really tell you anything about goals and switches. But on top of this, you have a small number of annotated data that we produce, I think around 1,000 stories that we've actually labeled. And the combination of both makes a big difference. So let's show you the outcome. Let's show you this UnweaveNet, what it does. This is now the inference. So we're watching a video, we're making a decision. So everything now is new. There is nothing in the memory bank. This is the number, the clip and the ground truth. So you're starting by saying, okay, I think the person is doing something. And then at certain point, you can see this switch. So a new thread is more likely than the current thread. And then with time, you're kind of figuring out the person is moving from one thing to the other. It's really very hard to see them with the video. So Will has produced these visualizations of short clips with the clip index, with the prediction, the ground truth, and the decision score. And you can see the model basically saying, I'm still doing the same thing. And these examples are important because you don't want the model to just keep predicting, especially when there is large head motion, like stretching the pizza dough. But also, UnweaveNet is capable of looking at the video and saying the person is dicing meat, then they go and rinse the cleaver, then they come back to dicing meat. And this notion of comeback and resuming doesn't exist in any of our problems until now. Of course, as well as other things. I'm setting up the motion machine, then I'm clearing, then I'm washing my hands. Okay. How are we doing with time? Okay. We don't know how we're doing with time, so I can keep going. So next is, I have 20 minutes, fantastic. What questions? Next is the tasks. And perhaps you've seen this in UnweaveNet, is this notion of what do we actually want to train on? And we've had loads and loads of data, and we have been in many cases not asking the right question. Why? Because we don't know. I've told you about this long tail problem, right? So what do we do now? We either train with the long tail, and thus the long tail is killed. If you look at any outcomes of Epic Kitchens or long tail datasets, you see that the tail recognition is 0. Or we go and kill the head, and we introduce this problem of few shots, as if the head doesn't exist, only have few shots. And we say, okay, that's how we work. We don't really know how to learn from the whole bunch of data, labeled or unlabeled, that we have. Worse, even when we have models that can utilize the data, we are unable to assess how well they do. And in action recognition, for a while, one of the problems we have is bias in the data, right? So you think you have correctly recognized the action, and then you go and look at what the model had learned, and it had picked up the handle of the cupboard as an example of something. It hasn't seen the action. So over the past year, we and the team have been working on these new annotations. So this is more labeled data, but its attempt is to understand models. So what you can see here are pixel level annotations, dense annotations on Epic Kitchens. And you can see the transformations of objects over time. And I'll just play a few of these. This is data that will be in the hands of researchers in a month's time maximum. If you know Epic Kitchens, then this is data that has been created by people without any instructions. And here we are annotating this data with dense knowledge. And again, this is suffering from exactly the same set of problems. It's long-tailed. It is spatiotemporally different. There are things that have very small pixels and very small time, and things that have many pixels and a lot of time. So what we're calling Visor, and this is a collaboration with the universities of Toronto and Michigan, is 270,000 manually segmented hands and objects, which we have interpolated into more than 10 million filtered dense masks. It's still not a lot. It's 36 hours of Epic Kitchens. 30 hours will be released and 6 hours will be the test set. And again, video object segmentation. So let's see what we have. Why am I introducing this? Because I think this is the long tail problem really, really exposed in truth. So this is what you will have with Visor. You will have these frames that have been labeled. You'll be able to have semantic knowledge. So you have the left hand, the right hand, you have the hob, you have the saucepan, you have the spice being poured, the spice container, the spoon that is occluded, the soup, and then what's in the hand, right? So you have every active object. You don't have segmentations of the rest of the image. Additionally, you have this additional information. So we also have this open vocabulary that we have mapped into a closed vocabulary of classes as well as macro classes. So that really helps in case you want to do more generalization. We also have what Epic Kitchens always had, which is action. So with every image, you know what the action ongoing is. We have knowledge of what the hand is in contact with. Is the hand in contact and which object it is in contact with? And we also have the knowledge of if something have been exhaustively or non-exhaustively annotated. I'm going to show you just a video, and you can see that we haven't labeled every single image. We've interpolated them into dense knowledge, but we have this long-term understanding of actions and interactions. We have these segments, and we can see the object in action undergoing transformations. So the person is picking up the peeler, and then they're actually peeling, and you see the peel formed. They're peeling the other object. They're washing the peeler, and you can see the unweave net concept going back and coming, clearing, etc., etc. So back to the same problem. You label pixel segmentations, the y-axis is log scaled, and you have the long-term problem. What do we do? How can we get rid of it? Of course, we also have the same problem of bias, right? If you have the link between actions and objects, you know that, when you're washing, there is a sink and a tap, right? These are related. You don't see them in other types of actions. But at the end of the day, unless we start really looking at the data we have, labeling it with enough information to be able to ask difficult questions, we will not be able to go forward. So there is limited data, there is limited labels, but we also need, but we also have the combination. So what am I presenting? I'm saying data will always be limited. Don't believe all this craziness that we have infinite amount of data. We don't, and people who've tried to collect data of birds and plants know that at the end of the day, you will have a lot of something, and you have something that is very, very rare. How to deal with that? Interestingly, people in machine learning don't want to deal with long tail. They believe that that's not their problem. So maybe that's a problem we need to address. We all know how that limited label is an issue, and we found ways around it, whether it's self-supervision or whether it is trying to do compositionality. So we're making progress with limited labels, but we're not making as much progress with limited tasks. And I think the combination of the three is what makes us move forward, at least in my humble opinion. Now, of course, I always get the pleasure of the invitation to come and present this work to you, but this is hard work of a large team over the years that have believed in trying to do fine-grained action understanding and have pushed me as well as the community to make sure that this is of interest. And I think I'm happy to take questions. Opinions are also welcome. Yeah. I have to repeat the question, don't worry.
Hi, I'm thinking of Columbia University. I have a big question. So basically, I just thought about even that we are on supervised learning.
Yeah.
And this is the major overhead is labeling, right? Without labeling kind of video, just task also like many people that are wearing head-mount camera and that one. Huge amount of unlabeled data and probably can solve the data issue.
So thanks to a collaboration of 11 universities, I don't know how to do that without boring you because I want to go back. Is there a way to scroll into specific slides this way? No? Okay. So that's what we've done with Ego4D, right? We went and said, okay, we were never big enough. Let's go and build this combination of different universes. So we have 11 universes. We collected data from 931 different people in 74 different cities. We asked them to collect a variety of things. What we ended up with is very much the same problem. So the long tail has not disappeared. You know, yes, this is the natural number of examples of certain things in the world. They're not exactly the same. For example, if you ask people to record what they do in their daily life, there are things you do a lot more than others. So what do we do with this data? Are we going to throw the head because we will never collect lots of examples of the tail? Right? So the problem persists. We can give people cameras, and we've done that. And we've recorded hours and hours, 6,700 hours. We still have exactly the same problem. We still have cases, sorry, I can't read these in detail, of activities that we only have 5 examples of. We have cases that have, it's interesting, like it's peculiar how similar this distribution is to Epic Kitchens, which is 100 hours, right? We still have the same problem. So what do? Either we have to throw the head or ignore the tail or deal with them separately, which is the few shot problem. Like say, okay, I'll focus on this, I'll ignore that, and I'll focus only on this. And that's the few shot problem. I don't think this is gonna take this anywhere, right? It's unless we try to deal with this, deal with the fact of life, we're gonna remain stuck. And remember that I haven't projected here the other problem I talked about, which is actions can be long or short. I haven't repeated the question. I'm aware of that now. Yeah, the question was, what if we just collected more and more data? Give people cameras. And again, you know, that's something we now became an expert of. We know how to give people cameras and how to think of all the ethics and other stuff, which is very critical as researchers starting in a new area like wearable. I think, you know, there is at the end of the day, limited data of certain topics. You will never be able to say that problem will be solved if you collect indefinite. And if you collect indefinite and do things like the current datasets, give me 100 examples of every class or 1,000 examples of every class, you're killing the head because the head has 1 million examples, right? Yeah. Does that answer your question?
Yes. Okay. Follow-up is, would this be a different challenge for few shots if we are scaling up the number of data?
So this problem is known as long tail versus few shot, right? Because currently the few shot problem assumes you only have few shot, unless the problem has changed since the last time I've looked. The few shot world assumes you only have few shot of all the classes. This is a problem of long tail. Some people call it open set learning, etc. The main concern here is if you keep collecting, you will keep increasing this, but that shape is not going to change, right? And currently we have this assumption, as we said, that you have the same number. Few shot is about, I don't know, 5-way 5 class. Even if it is 50-way 50 class, it assumes you only have 50 of every class. This doesn't really, it doesn't make sense. How can you collect exactly X number of exactly X classes? So again, we've worked on few shots and we published papers on that, and I think they are great papers, but I think the problem needs to be redefined.
So what about 5-way, like a million of every 5-way?
Sure. 5-way 1 million classes assumes you're going to throw the dates. The question was, what about 5-way 1 million classes? But what about those other classes for which you have 1 million example? You want to throw the 1 million minus 5 and only keep 5? There are 1 million. You can just fish in the water and you're going to get them, right? Throwing them doesn't make sense.
And if you take them, then this would be more challenging
Problem. I think that my argument is we should form problems that match real life. If we form problems that don't match real life, they will remain as problems we can talk about in CVPR, but they're not going to really go further into solving real life. You're welcome. So I think that my final message is video is really, really hard. And I know many people avoid working with video because the learning curve is tough. You need more GPUs and all that kind of madness. And perhaps the way forward is collaborate with other people who want to do video, cluster, and work on video rather than giving it up. It's really worth it. And it is where, well, life is video. It's not a static image. And so again, it has this additional dimensional challenge of long and short that I am yet to see that being even discussed or addressed. So it's a critical topic. And if you've worked on this and I haven't been aware of your work, please send me an email saying, we've done this, we've done it, we've thought about it, or I would like to work on this. Anything that solves long actions, short actions, few, rare, complex, I'm keen to look at, or even an analysis in a paper of whether this method works in short versus long actions, which is yet to come into any benchmark, rather than, with all my love for kinetics, 10 seconds is the length of every action. That's again not true. Not true. There are 1 second and there are 3 minutes. Thank you for your time. Oh.
And so based on your understanding, what's the difference between those potential video and those
third person.
And so because for both types of videos, they are also like problem.
Absolutely.
Yeah,
no, the problem doesn't exist only in egocentric. All the truth.
Yeah. So
yeah.
Based on your understanding, what's the unique part
on egocentric?
Video?
In what I have presented, there is nothing unique about egocentric. All the problems of addressed exist in video understanding, whether it's third person, whether it's one on YouTube, right? So let's talk about some of the data set out there, like how to 100 million, a brilliant work, and Antoine and Ivan and all the team have done a brilliant job. But what did they do? They collected, say, 100 examples of every task. But there are tasks for which there is only 100 examples, and there are tasks for which there are million videos. Okay, so again, the same question should be addressed. Why are we throwing all those 99,000 because we can only find 100? Yeah, that problem exists in all things. The length of actions exists in all things. Why am I passionate about egocentric? Because I think what it tries to address is the problem of untrimmed video, not edited video, right? So an untrimmed video introduces a lot more complexity than edited video. And I know we use the word video, but edited and unedited are different worlds. And I think unedited has more problems and things, but at the same time, it also has some solutions. If you look at someone opening a door from an egocentric perspective, the viewpoint looks the same every time. And if you do third person, it looks very different. So I argue egocentric is easier from the viewpoint independence concern, because you always see the thing you're cutting, you always see it from the same perspective, which I think is great. You have a bit of head motion, but you can deal with that. But most of what I said is a problem in video understanding, whether you're doing egocentric, sports, right? How many football matches can you find versus some obscure sport? How can we deal with the wealth of data we have that will never be the same number per class? Yeah, we know that doesn't work, huh? All these focal losses, they introduce something, but they don't solve it, right? Long tail is an unsolved problem. Anybody told you anything else? You know, I can argue for telling you it's an unsolved problem. And we're very far from dealing with long tail.
It's different from those third-person videos, right? And the challenge is that some videos utilize those unique parts for our model design.
Sure, there are unique things in egocentric, particularly you focus on hand-object interactions. But again, the three problems I addressed, limited data, limited labels, limited tasks, is not specific to egocentric. But sure, egocentric offers an amazing knowledge into how hands impact the world. And that's what I like about egocentric. But even if you're not passionate about egocentric and you want to do video, please address those questions. Thank you very much.
Thank you. There is a limitation. I cannot see the mouse. Where is the mouse? No. Yeah. Okay. Okay, now I'll introduce the next talk. It's my pleasure to introduce Leonid Sigal. He's an associate professor at UBC, and he's also a CIFAR chair at the Vector Institute and an MCERC chair. His research interests lie in the areas of computer vision, machine learning, and computer graphics, with the emphasis on approaches on multimodal representation learning, recognition, and understanding analytics. So thanks for coming to the workshop.
Thank you very much. I'll try to get back to the beginning here. Okay, great. So thank you for the organizers for inviting me to give a talk. And I just want to say that I'm really excited for actually physically being in front of people and talking to students and having a physical conference. I have students who are in their third year who haven't been to a physical conference, which I think is really sad. So it's great that we're back. Okay, so what I'm going to talk about today is data efficient learning for granular scene understanding. A lot of work from my group could be sort of characterized in these ways, but I'm going to focus on two specific works that are sort of more central about talking about these topics. But before I talk about what we actually have done, I want to a little bit motivate the second part of the title, which is the granular scene understanding. So why do I care about particularly doing data efficient learning or learning with less labels in this particular domain? And to think about that, essentially, what I want to do is go through the reason why I think we should do data efficient learning in the first place, right? Why are we here in this workshop? So the first one is just pure scientific curiosity, right? So essentially, if we look at models that are successful, deep learning models that we're working with day in and day out, they started to work reasonably well at this rate, but they require a lot of annotated data. And if we look at exactly the amounts of annotated data that they require, it's pretty exhaustive, right? Like if we look at GPT-3, which is a state-of-the-art NLP model, it required 400 billion words. And if you calculate someone reading at about 150 words per minute, which is pretty quick, there's going to be 400 years of continuous reading, right? So this is at least an order of magnitude larger than what a human does. So in terms of comparing these methods to human, clearly we're not quite there yet. And so there is a clear scientific question of, can we actually build algorithms that's going to sort of match that performance? So that's an interesting question, and I'm also interested in this. But to me, this is kind of insufficient, right? There's got to be a task, or there's got to be a problem that we're also trying to solve as computer vision scientists. So the second reason why we want to learn with limited data is that inherent inability to collect large data sets. So for certain problems, we just can't collect data, right? If we look at medical imaging, for example, certain rare tumors, they occur very rarely. They only have 100 or 200 cases every year, right? We're not going to be able to collect a million examples of a particular tumor. And this is a real problem, which I have a colleague that works in medical imaging. He's facing this day in and day out. Right, so that's an important problem to solve. But again, sort of for me personally, I don't work in sort of domains where this is particularly a challenge. So what is the most motivational for me is sort of this third point. And the third point really has to do is, what do we do when we want to scale vision, right? So if we want to scale vision to actually operate and recognize everything in the world and be able to build algorithms that are really scale up in terms of the number of categories, the objects that they detect, understand the world, and so on, we're going to be inadvertently faced with this problem. And to be able to see this, we can just look at different tasks in computer vision. So sort of going from left to right here, you have image classification, detection, instance level segmentation, and going even further, something like a scene graph generation, where you're not only grounding objects or finding objects, but also relationships between those objects, right? And so as the granularity of those tasks increases from left to right, essentially, what's also happens is that the cost of annotation increases as well. And there's a nice paper from ECCV 2016, where they actually tried to measure the speed of collecting annotations for these different tasks, or at least some of them. And you can see those numbers at the bottom, basically for image level labels for images in COCO or similar data sets that we're using. It takes about 20 seconds per image on average. Whereas if we go for segmentations, that's about 12 times as costly, right? So, and if we go to for example, scene graphs, it's going to be even worse, right? So the cost, and the cost is both in terms of time and money and so on. And so I would argue that it's going to be essentially, backing up to the point of the previous speaker, it's going to be infeasible to really collect the data necessary to be able to address the whole plethora of classes and tasks that we want to do, particularly at the granular scale where those labels are very costly to collect. Now you can go back to me and say, well, wait a minute, Leon, but there are large-scale segmentation datasets and detection datasets, right? We have them now. Okay, so let's look at that. And if we look at that, there's one thing that becomes really apparent, and it's the fact that it's not the number of instances, but the number of categories doesn't scale so well, right? So if we're looking at categorization, for example, ImageNet or Open Images that are two of the larger data sets, then they have sort of annotations for about 20,000 categories of objects, which is pretty good. That's about how many things a human can name. But if we start to look at detection, for COCO, it's 80 categories. Even for Open Images, which is the largest, to my knowledge, data sets out there, there's about 600 categories. And if we go to segmentation, then that drops to about 350. For COCO, it's still 80, right? So now we're kind of at least 2 orders of magnitude lower in terms of categories that's been annotated than for the classification task. And this is what's really motivational to me, is try to figure out how do we actually be able to scale the detection, segmentation, and various other more granular tasks to the scale of what we can do with classification. All right, so I posit that this is sort of an interesting and important problem, and I'm going to tell you about some of the techniques that we're doing to actually be able to solve it. And it is quite challenging, right? So if we want to do things in object detection or segmentation domain, it's quite a bit more challenging than doing it in classification. And this comes from our own personal experience, where we try to apply sort of models for few-shot or classification models that don't do so well in detection tasks and other more granular tasks. All right, so that brings me to the first work I was going to talk about today, which is UNIT, Unified Knowledge Transfer for Any Shot Object Detection and Segmentation. This was work done jointly by 2 of my PhD students, Siddhesh and Raghav. And it was actually presented at the virtual version of this conference a year ago. Okay, so the setup is what I said, is basically we want to learn effectively detection or segmentation networks using as few labeled images as possible, doing it as a very data efficient manner. So we're not the first ones, of course, to think about this. There are classes of methods that address these types of challenges. One of them is weakly supervised object detection. And in weakly supervised object detection, what you're given is essentially an image level labels, and you're trying to learn detectors, right? So on an onset, this is really good, right? Because that addresses the need to have these bounding box or segmentation annotations. We can just use all of the data in our Open Images with 20,000 classes. It should all work. Of course, it's very difficult to get these models to actually perform well in terms of the detection tasks or segmentation tasks, for that matter. The other paradigm that people have been developing is this few-shot object detection paradigm, where a scenario is a little bit different. You define the base classes and novel classes, and you assume for the base classes you have lots of instances of bounding box annotations or segmentations, and then and so you can learn good detectors, and then you want to transfer that information somehow to the novel categories that have only few annotated instances. And then there is yet another setting, which is semi-supervised object detection setting, which is essentially an extension of what I just talked about, where in addition to these base categories and novel categories, we also assume image level annotations for both the novel and the base classes. And our algorithm is going to be in the space. And within the space of semi-supervised models, there's two variants, what we're going to call zero shot, which allows you to deal with no annotated object detection instances or segmentations for novel classes, or the few shot, where you do have a few instances that have been annotated. Okay, so one of the issues with previous methods and these three paradigms that I've talked about is that the work in these areas has been largely siloed. And so the types of approaches that you use for each one of those formulations is quite different. And so one of the onset things that we wanted to do is propose a fairly simple unified framework that would be able to scale seamlessly across the different settings and also across the levels of supervision. This is also backing up this claim that we have long tails and we want to be able to deal with sort of different number of instances which might be present for particular classes. Okay, and just as an aside, I want to say that when we were doing this, we were quite doing this alone. Now there has been other work that looks at different forms of supervision that was done either concurrently or actually is at the one on the right is actually at this conference. So I want to go give credit to work that's been done. It's now termed omni supervision. So that's a very interesting direction that I'm going to come back to a little bit. Okay, so let's talk about our approach. What do we actually do? So our model builds on top of FastStar RCNN, which is a traditional object detection pipeline. That pipeline essentially has two stages. The first stage, given an image, produces a set of proposal bounding boxes that may contain objects. And then the second stage essentially would take the features out of each one of those proposals and classify them whether in fact that proposal contains an object of interest. And if it does, regress the bounding box or regress the segmentation in order to actually ground that object in an image. And so what we're going to do is basically modify the second part, which does this detection and segmentation. And we're going to do this through two stages, which we call base training and fine tuning. I'm going to explain what those things are. But essentially what we're going to do is we're going to learn a mapping from weakly supervised to much stronger, much better, fully supervised detectors for the base classes, because we do have enough annotations to be able to do that. And then we're going to use the mapping to then transfer those mappings into a novel classes that may or may not have any instance level supervision. And we're going to do this using a multimodal similarity metric that I'm going to discuss in a minute. Okay, so to ground this a little bit, because I'm talking about base, novel, right? These are a little abstract. You can think when I'm talking about base classes, you can think about COCO, right? So any categories that have object instance annotations, have segmentations, that data is fully annotated. And when I'm talking about novel, think about something like ImageNet. So image level labels, but for a large number of classes, let's say, 22,000. Now for actual experiments, we do a little bit less scale in that, but this is the vision. Okay, so what do we do for the base training? For the base training, we do two things. First, we train weakly supervised detectors for both base and novel classes. Remember that we assume that we do have image level supervision so that we can do that for both base and novel classes. And we're going to get our detectors that I'm illustrating using a function f, which is represented using a neural network. Now, the second thing that we do is for the base classes, we also essentially use learn adapters or refiners that refine those weak detections into a very good, strong detection performance, right? So effectively, what we're doing is expressing a proposal classifier as a linear combination of the two terms. The first term is our weakly supervised detector. The second term is our refinement. And you can think of those as producing just logits that you're summing together. Now, this is what happens for a classifier. You can do the same thing for a regressor. The regressor, you start with proposal boxes, right? And then if you have additional data, as we do for base classes, then we can essentially train regressors that would refine those bounding boxes. And we can do the same thing for segmentation as well. I'm just not showing on the slide though to clutter. Now that's what happens for base classes. What do we do for the novel classes? Remember, for the novel classes, we might not have any instance level data. So for the novel classes, we still have a weak detectors, so we can take those. We have proposals, so that part is okay. But what we need to do is somehow transfer information from our base detectors to our novel classes. And the way we're going to do that is using a linear combination of these refinement networks, where the linear combination is modulated by this function S, which is a function of the features of the proposal itself, which is going to measure a similarity between the base classes and the novel classes. Okay, very simple. It's just a linear combination. So now, given this, we actually are able to do zero shot already, right, for novel classes. We don't need any instance level annotations for them. But we could have cases where for certain classes, we do have additional bounding box annotation or additional segmentations. What do we do with that? Well, then we just add an additional refinement term on top of the first two that I illustrated before. That's going to directly essentially fine tune to those few instances. Okay, so now we've essentially just decomposed our detectors and segmenters. So essentially what we've done is introduced an inductive bias in the form of this decomposition that actually turns out to be fairly effective for what we're doing. Okay, so now the key to this working is essentially similarity. How do we measure the actual similarity between the base classes and the novel classes? We do this using a multimodal similarity measure where we take a product of two similarities, one which is lingual, that's agnostic to the actual proposal that we're looking at, and the second one is visual, which is actually as a function of the features of the proposal that's being considered. And the similarity is basically of the size number of novel classes by number of base classes, right? That's the overall similarity, but it's going to be different for every proposal box. So in terms of lingual similarity, we do something very simple. We just do a dot product of glove embeddings. Those are embeddings for the words that define our classes. If we have classes that's made out of multiple words, we just sum up those embeddings. So something very simple. And what you can see here is the similarity between the novel and the base classes, and it looks fairly, fairly intuitive. Airplane, for example, mostly looks like a car in the air, and it looks a little bit like a boat. The horse looks a lot like a dog and a little bit like a sheep, and so on. Right? So now we can take those refinement networks from dog and the sheep and transfer them to be able to refine the horse detections. Now for visual similarity, it's even simpler. What we can do is just take the base classes and evaluate the weak detectors on the proposal themselves. And then we get essentially a vector that tells us how similar that particular proposal is to every one of our base classes. And so for airplane here, it's most similar to bird, a little bit similar to the boat, and for some reason, a bit similar to a person, but not everybody's perfect. Okay, so now given the similarity, what we can do is train this whole thing. We can train it end to end. We can use any weak detection algorithm you choose as long as it's differentiable. We use a particular one, which is OICR, and we train it jointly with standard faster RCNN loss. Okay, so let's look at some results of this. So the first comparison is to previous semi-supervised methods, which this is sort of apples to apples comparison to what people have done in the past. And actually LSDA, which is listed here, which is a method out of Berkeley, was really one that motivated us to look at this problem and was inspirational for what we've done. But you can see that despite kind of simplicity of what we're doing, and we're not using any sophisticated similarity metrics and so on, we do quite well and better than previous methods by a few points. We can do this with a few shot scenario where we have 12, 33, 55, 76, 96 labeled examples. And again, sort of across the board, we can see the improvement with the closest state of art. We can also do comparisons to few shot object detection. And here we actually see that we perform quite a bit better. Now, one not of caution here. So this is not apples to apples comparison, because what we're doing is we're actually assuming that we do have image level labels, whereas the few shot object detections don't assume this, right? But those labels that are readily available, right? We have ImageNet, we have other data sets. are actually giving us a lot of bang for a buck here, right? Our performance is double what the few-shot object detections do. And we can do the same thing for segmentation. And again, here we can see quite large improvements. And finally, what we wanted to look at is what if we actually limit the supervision, right? So as I told you before, the previous two comparisons weren't really apples to apples. This one is. So here what we say is well, what if you take how much ever time is spent annotating object detections for the methods mentioned here, and you spend that time basically just doing weekly supervised learning. So for the same time that you can annotate a bounding box, you can annotate about 7 images with image level labels. And if you do that, then you actually end up doing better, right? So this points to the fact that if you had a limited budget, at least if you have a fairly small budget, then doing weekly supervised learning is actually better than doing a few-shot learning. And then we also did this a little bit more formally, where we studied sort of how we can compose these different tasks. So we can sort of mix few-shot supervision at bounding box level with image level supervision. And you can see that if you only have few weekly annotated labels, you actually do worse. But if you start to get to 50-50 or more of weekly annotated labels, then you do quite well. Okay, so these are some of the qualitative results. These are all the classes that, this is 0-shot actually, so these are all the classes that weren't seen, didn't have any annotated object bounding boxes or segmentations. So it works pretty well. Okay, so in summary, this was the first thing I wanted to talk about, is basically a unified semi-supervised approach that operates at different range of supervisions and also the types of supervision. We have sort of semi-supervised and weekly supervised data. And it's fairly intuitive, where we just use a linear combination using a multimodal similarity metric of the refinement networks that we learned for base classes to essentially produce our target classifiers. And we also started to scratch the surface on relative importance of image level supervision versus more granular supervision, which I think is an important thing to think about. All right, so I talked about object detection and segmentation, and now how are we doing on time? Oh, okay, good. Good. So now I want to focus on the second project that I wanted to talk about, and this one is on scene graph generation. Right, so this is a more granular task where, again, you want to, it's kind of like object detection. You want to detect all the instances in an image, but also between the instances, you can have relations that tell you whether, what is the relationship of one object to another, essentially. So this was presented at ICCV last year, about 8 months ago, and this was done by Sudesh and Suhail, who are also PhD students in my group, and it's called segmentation grounded scene graph generation. So just to define the task of what we're looking at scene graph generation. So scene graph is a graph-based representation of images that encodes objects in terms of the nodes in a graph and relationships in terms of an edges. So if I illustrate the task for this particular image, what we're trying to do is detect all the objects that are present in here. Those objects are going to get classified. So those are the labels for the objects. And then they're going to be transformed into being nodes of a graph. And then the directed edges in this graph are going to be actual relationships. For example, person is holding the umbrella, person is wearing a hat, person holding lamppost, and so on. Right? So it's a structured representation that we're trying to get out of the image. So prior work did a lot of work in this area, looking at different architectures, loss functions that we can do for this task, and also the long tail distribution, which is something that was discussed in the previous talk. This is really a problem for this domain, where there are there's a long tail where some of the relationships really don't happen very often, and some of the objects don't happen very often. And so there's been recently, actually, I don't have any citations on this slide, but there has been a lot of recent work on how to balance that and be able to get scene graphs that operate well both on the head and the tail classes. But all of these methods that sort of predated what we're doing made one particular assumption, and that is that the grounding of objects was essentially at the boundary box level, right? So all the objects were detected essentially with an object detector, and then the relationship were estimated between them, but effectively all the grounding was done at the boundary box level. Now, we posit that it's actually would be much better if we do this at a pixel level, because depending on the aspect ratio of individual objects, there still might be a lot of clutter within the bounding box that would prevent you to actually reason about the relationships effectively, right? The relationships really focus on the intersection of where the two objects meet or interact with one another. And so being able to essentially get at that information more precisely by having segmentation in that mask, we believe would be helpful. And in practice, we do see that that actually, as you will see, gains the performance. Now, the second part of this is that in addition, by grounding to the pixel level, what we can do is improve the segmentation performance itself, because essentially a scene graph is a contextualized representation for the entire image. And so we can take the information, sorry, we can take the information from all the different objects, integrate it, and be able to refine the segmentations that we have. Now, the main challenge here, though, is one of data, which is consequentially is the topic of this workshop. And the reason is that because most of the, or all of the scene graph generation data sets don't actually have segmentations labeled, right? So they have the rich labels for relations, they have bounding boxes, they don't have any segmentations. We could go off and label all of that data, but this would be prohibitively expensive. And it's also going to take a very long time. So instead of doing that, what we try to do is try to see how can we actually use auxiliary data from data sets that do have segmentations in order for us to actually solve this task without having sort of consistent segmentations on the same data set. Okay, so what the contribution of this was that we have a novel framework for pixel level segmentation grounded scene graph prediction, which can be integrated with any scene graph generation method. We actually make no assumptions about what the underlying scene graph generation method is. You can take any state-of-the-art method. We actually illustrated multiple methods in our paper, and you can add this to it. And we use transfer and multi-task learning in order to do that, and in particular, zero-shot transfer for segmentation, which is going to build on the, some of the constructs that I actually already talked about in the first part of my talk. And we'll see that this results in about 12% improvement on the scene graph prediction performance, and also improvements on the segmentation performance as well. Okay, so let's look at the problem setup. So as I mentioned before, we're going to have two data sets. The first data set is what you typically have for a scene graph generation framework. So this is a large set of images with bounding boxes and the scene graphs as annotated here, but notably no segmentations. Now, the second data set that we're going to have is an object detection or segmentation data set, which does have segmentation and bounding boxes for detection, but notably does not have any scene graphs that are annotated for that data set. Okay, so we're going to call that our auxiliary data set. Now, importantly, we make very little assumptions about what those data sets are, right? So you don't have to have the same categories of objects in the two data sets. You don't have to have the same images annotated in two data sets. The overlap between the two could be sort of minimal. And in particular, way we're going to do this is for our auxiliary data set, we're going to use MS COCO again, so that has 80 categories with segmentation. So that's what we have for our auxiliary segmentation data set. And for the scene graph generation, we're going to use Visual Genome, which is a standard data set that you use for that task, which has 150 object classes and about 150 relations. So one thing to note here, right, there might be some classes in common, but clearly there's at least 70 classes in the Visual Genome that were never, can't possibly exist in COCO, because there's only 80 categories there. Okay, so what do we do for a model? So for the model, we build on the standard pipelines for scene graph generation. So standard pipelines for scene scene graph generation looks something like this, where you typically have an object detector. That object detector detects potential objects in an image. From those objects, you extract the object features, and you also extract relational features that are typically pairs of features from the potential objects that are in possible relation. And you do some sort of propagation among those feature representations, usually using like a recurrent neural network, LSTM, transformer, graph neural networks. You take your pick. There's different papers that do different things in this context encoding part. And then eventually you have a scene graph head that would essentially, for every node, will predict a classification label. That's a label for an object. And for every edge would predict a label for a relation. Right? And then you do typically a cross entropy loss at the end that backpropagates and learns all of these components. And what we're going to do is just slightly augment this to say we're going to do the zero-shot segmentation. We're going to infuse the features of both objects and relations with those segmentation masks. And then eventually at the end, instead of just having a segmentation loss, instead of just having a scene graph loss, we're also going to have a segmentation loss. Now, if you think about our two data sets and you think of them flowing through this diagram, you will notice that only the images from one data set will basically only get one loss. The images from the other data set will get the other loss because they just don't have the annotations to be able to deal with both losses. That would require us to actually have for the same image two different types of supervision. Great. So all of this could be summarized in 5 stages. I'm going to go through them relatively quickly. They're pretty simple. So the first stage, we do what is typically done for these types of models, which is we train an object detector. In this case, we do faster RCNN, which is fairly typical. And so that can generate bounding boxes for all of the objects in our scene graph visual genome dataset. Now, in addition, the same backbone and the same faster RCNN is trained to also do segmentation on our auxiliary dataset, right? So we can just combine those two. And then once we have the segmentations for our auxiliary datasets for our 80 classes in COCO, we can essentially just do a zero transfer to do zero-shot segmentation for the categories in our scene graph detection dataset, which doesn't have any annotation itself. And to do this, we essentially just use the lingual similarity, which is what I talked about before, using glove embeddings again. So we just take the segmentations from COCO and we linearly combine them to get a segmentation for a particular category within the visual genome dataset. Now, once we have these segmentations, we can simply infuse that information into the bounding box representation Z using a simple neural network. I'm not going to go into the details of what that actually does. That's in the paper, but it's a very simple operation where basically we just combine those two sources of information. So that gives us the new object features, which are now infused with the segmentation information. Now, for relational features, in addition to doing what typical scene graph model would do, which is taking the features of the two boxes in question and maybe the union box, what we do is also create a mask that would ground the relationship itself. And a way we do that is by essentially doing a Gaussian smoothing on the two masks of the objects in question and taking a product of those two Gaussian masks. And what that operation actually does is essentially creates a high density region, high likelihood region on the interface between the two objects, which allows us to focus the information sort of where we believe the relationships sort of most actively are acting. And the parameters of the Gaussian smoothing are actually learned as well. So we actually can learn how much to smooth at the same time as we're learning everything else. Okay, so as I said, our approach could be integrated with any scene graph generation method. We've tried it with two, VC3 and Motif, which were at the time kind of state-of-the-art methods for doing this. So I'm going to show you some results using that. And but in general, you can integrate it with any approach you like, just using the task-specific loss that approach integrates. And so finally, what we also have is a refinement mask, which is going to refine our masks once we do scene graph, essentially propagate the features and do scene graph predictions. And so now we're going to get better masks that are post kind of scene graph that you can think of actually doing this as multiple stages where now these masks be fed back into the model and so on, but we haven't actually done that. Okay, so let me show you some experiments. This is run in 3 different settings. The first setting is the predicate classification, where we're given an image, bounding boxes, and object labels. All we need to do is predict relations. So this is the simplest of the 3 tasks. The second one is scene graph classification, where we're given images, bounding boxes, but we need to predict both the object labels and relational labels. So it's a little bit more complicated. And the first one is the scene graph detection, which is essentially you're just given an image and you predict the entire graph. And in terms of performance, we use mean recall that's been established as a better metric in this domain to essentially deal with this long tail distributions for scene graphs. And we also use average precision for segmentation performance. So let me show you a little bit of performance. It is a long, obligatory table that's in all of the vision papers, but let me focus on a couple of things here. First of all, just showing you that we did do this with 2 different baseline, motif and VC3, and in both cases, just adding this type of segmentation head and this type of information into the network actually improves the performance across all of 3 tasks quite consistently. We also tried it with different backbone. So in the object detector, again, it's pretty consistent in terms of increases in performance across all 3 tasks. We can also look at segmentation performance, and this is on COCO using mask, as comparison mask CNN. And you can see that here we also see different improvements for particular tasks. So in particular for the predicate classification, where we are given sort of additional information in terms of bounding boxes and labels, this actually helps the segmentation quite a bit, but also for other tasks, we also perform better. These are some qualitative results that you can see. So on the left is the baseline model, on the right is our results. Notably that you can see that in our case, we actually get segmentations. To my knowledge, this is the first work where we try to attempt to ground things into segmentations or pixel level predictions for scene graph generation task. This is another example. You can see that things like cats and various other things do pretty well. And we also do better in terms of scene graph predictions, particularly predicting labels that are better attuned to the content of an image. And this is a result just to show you that the segmentations also do better. So on the left is the baseline, which is effectively mask RCNN, and on the right is what happens after we do this with our method after we refine it. Great. So in summary, this is essentially a model agnostic approach for segmentation grounded scene graph generation and prediction. It works with any underlying scene graph methods, including ones that were developed after we actually did this work. There's nothing specific to the scene graph detection method that we're using. And one nice thing about this work that we're also showing that we can simultaneously improve performance in both tasks, both the segmentation and the scene graph prediction. Okay, so that kind of concludes. Do I have a few more minutes? Excellent. All right, excellent. So that concludes what I wanted to talk about in terms of promoting our work out of a group. And what I wanted to do a little bit is to talk about what I think is interesting for the future. What do I think are interesting open problems, and what are we actually looking at, and what you may see in the next year or two coming out of our group, and hopefully not just our group, other groups, because I think these are important problems. So one of these is omni-supervised learning, and this is essentially a focus on effectively learning with all forms of supervision that you have, right? So siloing ourselves into only learning under a particular form of supervision or particular number of examples per supervision is too constrained. I feel like we need to be able to operate in this sort of much more general framework where we just want our models to consume all possible data that's available to them, do this in a way that is most efficient in terms of whatever annotation is available, produce for us detectors, segmenters, seeing, understanding methods, all sorts of things that are as good as possible. And so, the work that I talked about is along these lines. I also mentioned two other works that do this omni-supervised learning. They actually do much better in terms of dealing and focusing on different forms of supervision. In addition to image level supervision, they look at things like scribbles and points and various other forms of supervision that you may imagine having, and combining all of that information in order to be able to learn in this heterogeneous scenarios. Now, the second thing that I think is important, and this hasn't been addressed as much, I feel like, is sample selective learning and inference. Actually, on the inference side, it's been addressed more. And this is kind of an idea where not all data samples are created equal. And so they should be sort of, each sample should be sort of treated with care, right? And so in the inference side, there are actually methods to do this that, for example, use dynamic networks that would change the network architecture or change the network weights conditioned on the sample itself. And this is typically done for efficiency reasons, because at inference time, you want to deploy your methods and use as little computation as possible. But what I'm thinking in terms of a future is that we should also be doing this at training time, right? At training time, we also will have annotated instances, and not all of those annotations are going to be equally effective, right? So some images are going to have large objects that are much easier to detect and deal with. Other will have small instances, occluded instances, and so on. And we should be able to sort of carefully tune how we're learning from this data in terms of making most efficient use of that data. And on the same front, if we are sort of if you're buying into this premise of having data samples that are not all equal, then comes the continual learning and active learning, right? Where you actually want to be able to tell what kind of supervision do I want for a sample? Do I even want the supervision for a sample or not, right? What is the most optimal for me in terms of learning a model? And this is something that we're sort of actively looking into and working, but this is very hard, right? This is an entire other field which people are working on. And then finally, the third thing is something that Dima also mentioned, is imbalanced distributions of labels and dealing with this long tail. This is especially problematic for granular tasks because simple strategies for essentially balanced data balancing don't tend to work very well in those scenarios, and so you have to have more sophisticated models in terms of weighing losses or doing various other things to be able to deal with these types of distributions. And there's also a question of what is actually optimal. What do you actually want, right? Do you want all the classes at test time to be sort of equally weighted and the errors to be equally important or not? Okay, so those are the four kind of future things that I think are important, that I think I'm trying to work in my group. I welcome you to work on these topics as well. I think they're super interesting. Now, this is from a perspective of kind of classes of ideas. There's also all sorts of methodologies, right? Weakly supervised learning, semi-supervised learning, self-supervised learning, transfer learning through foundational models, role of generative models, which was talked about in the morning, data augmentations, and so on, right? So all of those things are interesting. For me, all of them are important. All of them play a role. But in the context of these larger kind of questions and ideas that I talked about on the previous slide. Right. So that's all for me. Thank you. And of course, this work is all done by the students. This is actually a pre-COVID picture of the lab. It's a little bit different now. Hopefully we'll have an updated picture soon. But thank you for coming, listening to my talk. If you're ever in Vancouver, which is, I welcome you to visit, please come. Visit our lab, give talks, write me emails. Thanks. Any questions?
You have time for 1, 2 questions. Yeah.
You have to repeat them. About the first work you showed.
Yes.
So you talked about like two similarity metrics that you use, the lingual and the visual one.
Yes.
And there are some data sets in which don't really have textual embeddings for the labels of the images. So one is more important, the lingual or the visual similarity metrics? Like, what's the weighting?
So I have to. We did have an ablation in the paper. So I'll just repeat the question. The question was, in certain data sets, you don't have class labels, and so you would have to sort of result to only visual similarity, presumably, and which is more important, the visual or the lingual similarity. In our experiments, to my recollection, the lingual similarity was much better, relatively speaking. But of course, if you don't have access to it, then you can't use it. Now, one thing that you can do, even if you don't have kind of semantic labels, you can learn embeddings for non-semantic labels and use the similarity of those embeddings as a proxy for a lingual similarity. So you can do something like this, but we haven't actually done that. Yes.
Actually, my question is about the second half of the presentation. Oh yeah. My question is about the second half of the talk. So I noticed even in general in SceneGraph literature, like the mean average recall is still relatively low as a metric. We're still getting between 10 to 20%. What do you feel is really holding back SceneGraphs from being a lot more, I guess, recalls? Is it the data itself, the visual genome? Is it poor coupling between the vision and language that we still haven't figured out in SceneGraph? Thank you.
Yes. Should I repeat this one or okay? So the question is, what is holding back the performance on scene graph generation because the performance is relatively low? It's a good question. So I don't have a very specific answer to this, but I feel like one of the challenges of scene graphs in particular, because the metrics are effectively on the triplets, it's subject, predicate, object relations. And so the space of those triplets is much larger than the space of typical object detection labels or the relational labels by themselves. And so in comparison to others' tasks, the data is labeled more sparsely, right? Because the space of the output space is larger. So I think that's a challenge. There also this challenge of imbalance, and that's been very significant in the past couple of papers that have been published on this area. There's a lot of work on how do you properly balance the data in such a way that you actually do sort of well both on head and tail classes, and that actually drives the performance up quite a bit. So we have paper under works now where we also look at that, and that actually could improve quite significantly the performance if you just focus on the tail classes, but in such a way that you also don't give up on the head classes as well. Yeah.
Yeah, thanks for the great talk. I'm interested in our first work. We're trying to integrate both the language information and the future of real example together for detection. So my first question is, did you use any pre-trained real language model, for example, the clean pre-trained model? And my second question is, I'm wondering the comparison between the text-based model and the future-based model. I'm wondering, so how many future examples do we need to get the same performance as the text-based model? For example, maybe one shot is better than the text model, or maybe we need 10 examples. Do you have any ideas about that?
Sure. So let me answer. I'm not sure I quite understood the second question, but let me do the first question first. So the first question was about whether we tried any language vision models in terms of some of these embeddings and other things. And the answer is not yet, but I think if we did, that actually would improve the performance. So I believe that actually would make things better. And we just haven't gotten around to doing that. I think that would improve things. I think the second question had something to do about how many shots we need.
Yeah, I'm wondering the performance comparative between the text-only model and the future-only model. So how many, for example, how many future examples do we need to get the same performance as the text-only model?
I see. So I can partially answer that with the results that I showed. right? Because there, what we did is we essentially spend our budget weekly annotating the data. So instead of sort of spending one shot to get one bounding box, right? We spend that amount of time essentially just getting image level labels, and we were able to do better in that case. So I think at least to a certain extent, the sort of weakly supervised models or these foundational models, or whatever you want to call them, multimodal models with language and vision, would actually do quite well initially, but then eventually you're probably going to need some samples of what the bounding boxes actually are around the object to further refine the performance. That would be my guess, but that's purely a guess at this point because we haven't done any experiments to back that up. Yeah.
Thank you very much.
Los va a introducir Costas.
Now we'll have the panel discussion.
These microphones are good for the people here. They hear by the microphone for them. And this one is where the people from Zoom hear. So we will.
Maybe bring that up. Since this is its extent, maybe if we go further, it will allow more people to look. Huh? Yeah, let's go as far as we can. Do you want to? Yeah. Basically, this is the extent. So if you want to get closer, there are more people can talk into this. That was the idea. Yeah, exactly.
So used to being
distancing.
Far from other people.
Distancing. Yeah.
I have to fight against my instincts.
Yes. All right, hello, my name is Costa Trapanas. I'm one of your co-moderators.
Hello, everyone. Thank you all for coming to our workshop today. I'm Xinhua from Computer Vision Group at Microsoft Research. So firstly, I did my PhD at UC Berkeley, working with Professor Travadaro, and I designed some data vision algorithm, especially for visual object detection. I'm really happy to moderate this session.
Okay, so for those that are in Zoom land, we're doing something a little bit experimental. So if you want to see the video of the panelists, please pin Costa Trapanas. Okay. All right, so before we begin, I just want to echo Leon's thoughts. It's amazing. I'm so happy to see all these faces live and in person. It was about a year ago when I'm just sitting in my room, my office, looking at these endless Zoom meetings, and I'm thinking, is this a new normal? Well, I'm happy we're back again. Okay, so if we could start off with our panelists, just introduce yourselves briefly, and then we'll begin.
starting with Katerina.
Yeah, hi, I'm Katerina Fragiadaki. I'm an assistant professor in the machine learning department in Carnegie Mellon University. I work on 3D perception, representation learning, manipulation, language grounding.
Yeah. Hello, my name is Mohammed Al Hussein. I'm an assistant professor of computer science at KAUST, and I work in learning with limited data in images and 3D.
Right. My name is Dina Damen. I'm a professor of computer vision at the University of Bristol in the UK, and I work in egocentric video understanding.
Sorry to interrupt. So those in Zoom land, hit cross that so you can see the video and panelists.
So like a TV studio. So I'm Miguel Arachel. I lead the team, Google Brain team in Montreal, and I also have a position at University of Montreal and part of the MILA, so the Quebec Institute of AI. And I've been working in few-shot learning for a number of years.
Hello. I guess I'll try to speak to that microphone as well. So my name is Leon Segal. I'm associate professor at University of British Columbia, and I work on a number of different things: multimodal learning, sort of core vision tasks, generative models, all sorts of things.
Hi, I'm Zhilin Yu from media research. I'm a senior research scientist, and I work on vision transformer and general visual recognition models, and also weekly and self-supervised learning problems.
Jake, are you there? Are you online?
Yes, hi.
Oh, can we hear you now? Say something.
Yes, hi. Can you hear me?
Oh no, David, we can't hear Jake. Here.
Um,
I can't hear Jake.
Can you talk again?
yes, hi.
Oh, that's funny. So Zoomland can hear him.
That's a challenging.
Fun hybrid. Sorry, just one moment. So it's not muted. Yeah, volume. So if I can't, Jake, you should be able to hear him from here, right? Yeah. Oh, change just the speaker. Speaker. Oh, okay. Jake, try again.
Hello?
Yes. Okay, that's a little bit better.
Great.
Loud and proud, go for it.
Okay, so my name is Jake Snell. I'm a postdoc at Princeton University working with Tom Griffiths. I completed my PhD recently at the University of Toronto under supervision of Professor Richard Zemmel. And I've worked in few-shot learning and also more recently on uncertainty quantification and robustness in machine learning.
All right, so what we're going to do is we're going to start off with a few warm-up questions. Panelists, feel free to be controversial. And in terms of the audience, there's going to be a chance midway through to ask questions or at the end. But also, if there's something pressing, just stand up and ask the question. Okay? All right, so the first question is, what do you think of the current status of learning with limited labeled data, especially for scene and video understanding tasks? And anyone, just any of our panelists can speak up.
I think we kind of, probably all of us touched on it in our talks, right? So I think for me, the current status is, in video particularly, is balanced learning. We haven't yet touched on the long tail in video as yet. And that's probably the main concern.
All right, let me just with a follow-up question. So what do you think? So I think Dima mentioned one of them in terms of challenges, but what are the opportunities?
There is a lot of data.
The opportunity is that you, I mean, sort of talked about this as well, is we shouldn't ignore data that exists. We should make use of the data that exists, but at the same time, acknowledge that some people will argue, but I would say that we're never going to have enough data to actually do well on everything that we want to do well on. So it's sort of this duality of, on one hand, having a lot of data for certain things, and on the other hand, having an opportunity to do some interesting science, to be able to actually use that data to do better on things for which we believe we might never have enough data.
All right, next question. As many foundational models like GPT-3 or CLIP show impressive few-shot and zero-shot generalization, what's your view about learning from massive unlabeled data versus learning from limited labeled data sets? Go for it, Nima.
I don't think any of these are doing zero shot. We don't know what they've seen, right? What's the assumption that this is zero shot? So I think I argued there isn't currently yet any evidence that any model has done zero shot unless we've seen the data.
Strong response. Who else?
I would say I back this up as well. I think it's hard to argue for that unless we have evaluation protocols that can judge if the given input or something is something that we definitely didn't see before. And I think if you train, let's say, a CLIP model and then evaluate an ImageNet, you cannot really guarantee that these set of concepts that you evaluate on are not seen, and then call it.
I guess I have like a follow-up on this. Like, but what about the composition? So for example, if I've seen some concept and then I want to generalize to some like unseen ones, but which is a combination of the same concept, do you think that will be a kind of zero-shot generalization in some way?
I would say yes, it's a compositional unseen. Yeah. And there are some compositional unseen that are harder than others. Like if you have seen only the individuals too much, but not pairs of them. So it can be easier if you see pairs of them than if you would see only the individuals.
As long as there is an acknowledgement that this is zero shot in compositionality, right? I think I'm tempted to ban the term zero shot until it is correctly being used. It's mad. Now there is a case where people are saying, oh, I have a test set and it's zero shot. Like, this is a test set. The term is now being overabused, I think. So
zero shot has its own literature. So
yeah.
So Leon, you touched on zero shot. You want to jump in there?
Not on zero shot, but in terms of a hearsay, because I don't remember the actual reference, but very recently, a couple of weeks ago, I actually read a paper on Archive that touched on this issue, which basically just reversed the composition. So like white dog on the sofa versus white dog on the black sofa versus black dog on the white sofa type of thing. And essentially, it was all of the recent models, visual language models, which I tried a whole bunch of, were a little bit better than chats, essentially, in distinguishing those two scenarios. And yet those models do very well. So I think my interpretation of what they're doing is very much closer to kind of bag of words, where they recognize there's certain sort of objects that exist and then form sentences that are sensible out of those words, as opposed to looking at intricacies between interactions of attributes in those objects and various other things within the C. I think that's much harder.
Anyone else want to jump in there? Go ahead.
Yeah. I want to also echo on this problem briefly. So I think actually I think the question is that whether you want you compare training on large scale data versus training with a few labeled data. So I actually think these two are not contradicting to each other. The real point is like it's a case by case scenario, and also they both have different roles. So from an application perspective, there are certain applications that require you to train on large scale data, especially safe critical applications such as autonomous driving. It's actually sometimes from I think I came from a industrial background, so in the industrial applications, people talk about the also other dimensions besides these the science problem in weakly supervised learning. So, for example, in many cases, it's easier to actually just label a lot of the data, and it's usually give a reliable performance. So people prefer to do that. But in some cases, actually, you can transfer these large-scale models to in-domain applications where you only have very few labels. So actually, there are auto-labeling problems where you only have a few labels. So you can leverage these large-scale pre-trained models. So in this case, actually, both are needed. And also from a research perspective, what I think is there are different roles. So first of all, I think label is never going to be avoidable. Like even as human, we receive, it's not totally unsupervised learning. It's actually both self-supervised mixed with some sort of supervision. Even if you are talking about these larger scale training, let's say CLIP or ImageNet, you actually have implicit supervision inside that. For example, these images are object-centric, meaning they actually encode a lot of localization information, and rather than like these unconstrained scenarios where you have a lot of cluttered objects. So I tend to think that larger scale self-supervised learning are more, you can use it for learning very good representation and learning bottom-up representations, while a few labels, you get to a point where you have such a good embedding that you only need a very few label supervisions that comes in top-down form and finally give you the mapping, semantic meaningful mapping. That's how I see this problem. Yeah.
Emma, you want to jump in there?
Can I also say there isn't anything called unlabeled data? So there's a human who stood, framed an image. They have provided a boundary label from the infinite world of something that's interesting. That's labeled. Yeah, that's labeled. That's already is some, human intervention. So I think we're over abusing some of the terms. So again, all of these models trained on web data, there is even too many steps. Someone has taken an image, thought it was worth uploading it in the right place with some knowledge of relevance. That's a huge amount of label that we have to acknowledge is what we're currently trying to learn from.
All right, so let's move on to the next question. So there is a rich set of literature on low-shot learning on images. Many of you have contributed to this. So however, it's relatively underexplored for video understanding. So what do you think about the main challenges and possible directions for learning from limited labeled videos? Is it simply an extension from what we've done on the image side, or there's something special about videos that we can leverage?
Yeah, I think that's always the big problem, right? There are some videos from which if there is a single image, that's enough. And there are some classes for which you need video. And I think even this is, our data sets are mixed with combinations of these efforts, which makes it very hard to understand which bit of what we're learning is video. So we don't have like a data set that's, there are a few attempts, right, of increasing complexity, but yeah, how much video we need in video. We've published a few papers like as a community on this, not yet enough. It's not enough. When do we need video?
Yeah, I mean, as a person that works on video, it's always been vexing where you see a model compared with just using an image versus video, and the video doesn't add much, right? Doesn't mean that the video is not important, but a lot of times there's a bias in the data set, a large bias in the data set towards, certain special frames, for instance. Does anyone also want to add?
Yeah, but I think it's also about potentially what you're trying to get out of the images, what are the labels, right? If you're sort of have broad classes of activities, then it might be sufficient, right, to distinguish them, to have one or very few frames. But if you have other tasks, for example, kind of a finer grained task where you want to judge performances, then I think that would be very hard to do without an actual video component.
At this point, are there any questions, comments from the audience? All right, so there is, oh, go ahead.
I would say also that maybe there's a lot of bias in the existing data sets for human activity. So, for example, you can see that in images, it's models are quite advanced. They can detect scene graphs, relationships between many different objects. Maybe most activities in videos are currently more biased towards human. I have attended some of the animals, CV for Animals workshops. Animals also do things, right? So the composition between different objects, including humans as well as animals, something that could be, I think, extended.
Katerina, you want to jump in there?
Yeah, maybe one comment is as follows. So to talk about video in general, for example, me when I think of images, I think of photographs. So what was said earlier that people take and upload. So I just think of visual genome ImageNet Coco. But when I think of video, I mean there are the egocentric activity videos. Then there is the robot trying to manipulate things. Then there are surveillance videos with multi-object tracking. Then there is a navigation videos of of robots moving the world. So there are like too many things with two very different tasks. So I think maybe it is really hard to put under a single umbrella. And for many tasks, if you can parse correctly every single image, then of course the video can help out. I mean, by the way, a video is also like a surveillance camera not moving outside your house, and it's just taking pretty much still images. I think for images, we all think about the much more tight tasks like image classification, object detection, segmentation. While for video, there is a gazillion things out there that have many downstream tasks. And another comment I want to make is earlier you mentioned clip and you put it on the unlabeled data, I think, but clip is trained from captions. So maybe what we say label, right, is not clear what we mean by label. So object detection, you put a mask. Still, right, if I care about point-to-point correspondence, still it's a weak label for my downstream task. So the question is, how can we learn the most out of the coarsest scale of labels across the different tasks? Maybe.
All right, anyone want to jump in there or?
Do I?
Yeah, go ahead.
Okay. Yeah. I want to also echo what Costa just mentioned, because so I think my personal 2 cents is that there are things that video can do, and there are things that maybe video isn't a very good way to provide. I might be a little bit. I know a lot of you are working on video, but I might be a little bit pessimistic about some aspect of the video. So a lot of the frustration, as Costa just mentioned, is like sometimes the video. The problem is there isn't this kind of image net moment in video hasn't come yet. The reason I feel is like currently a lot of the video data sets are human centric, but actually maybe I'm wrong, but if you want to use video to learn very good representation, you want to have a lot of variation between classes. So right now the best way to get a very super good representation seems to see a lot of classes, a lot of different like image text pairs, and see a lot of variation so that you get very good representation. In this aspect, video data sets, sometimes the problem is the lack of variation and the number of the classes. That's one of the potential problem. And so I think video, the good thing about the video is maybe it can provide some reasoning or some task that requires the context. That's the part where the video can do. But if you want the video to provide the representation, one of the challenge, at least I see now, is that sometimes like it doesn't compare as good as simple image-based architecture, because with image-based architecture, sometimes you can easily pre-train on these large scale image data set, and using the video, that's sometimes it's very difficult to find the data set to pre-train. That's a problem I see right now. Yeah.
Sorry, in defense of video. Right.
Here we go.
Yeah. So we're expecting video to fit our needs. We want no redundancy, high diversity, and that's what we want. That's what we have models for. But that's not what video is. As Katrina said, a video outside your house with nothing moving, is a video. It's highly redundant, crazily redundant to the extent that we don't know how to deal with it. And that's the truth. So trying to fit it into our models, I think, is unfair. Video has high redundancy. We need to deal with it. And things happen, in life with that in mind. Like now, we're watching the audience and, this is an interesting video. But if we complain that it's actually, people haven't moved too much, they're just nodding and that's not enough, and thus we don't have diversity. That's trying to fit the problems into our models. Yeah, they could be smiling behind the masks. Yeah, so that's what video is, and it has interesting problems. We just need to think of it differently. It's not IID data, it's not low redundancy, and it is very difficult to manage, very large in size. So, and it has its interesting problems. So I think we should just not try to fit videos into what we have.
Yeah, I think that's a great point. Because you mentioned something when I felt that in my research before when I was working on video, which is that it was always disappointing that something that was purely frame-based and kind of ignored the temporal component was kind of doing as well as any of our more, sophisticated attempt. But if I think about why was I frustrated? I was frustrated because I wanted a paper that said that I had a model for video, and then I couldn't say that. But really, who cares? Because if you're solving the problem enough, it doesn't matter whether it's using the temporal element of it, because ultimately we're doing all of this work to really solve problems that are useful, not to come up with a sophisticated method that has a nice reasoning in a paper that's published at a conference. And so I think we have to distinguish two settings, which is somewhere, and I guess maybe that's part of the challenge when we work in video, where you don't know whether if your results are not great, is it because it's not understanding the temporal dynamics? Or is it just that there's really just not enough data, or you've not figured out how to exploit more data to actually get good performance, possibly by ignoring the temporal dynamics still, and because maybe it's actually not that useful, much like you said, because in some situations you just don't need it. But the data that the system is ingesting is by nature, temporal, or it's video. And so I think it's important to keep that in mind. And maybe it just means, I think partly, as you mentioned, I think in your presentation, it's the kind of data that's kind of, resource hungry. You need maybe more GPUs, and for sure, for research-wise, it can be kind of frustrating to throw so much resources into a problem that maybe doesn't need all that much. But in the end, I think maybe it's just about accepting the fact that there are settings where what the system is expected to take as input is video, and then it is what it is.
Just to jump on this point a little bit. But I think the redundancy of a video could actually be a point of opportunity, particularly if you think of it more holistically, right? And if you think of ingesting video during training, that gives you a lot of views of objects and other things from different perspectives. And that, in a sense, gives you opportunity to easily label, right? Like you can transfer labels across the frames and so on. That could actually improve various other tasks that might not be video-based. So the video could improve, traditional vision tasks as well. I mean, ultimately, that's how we learn, right?
It could be also that natural to have systems that does that. I discussed with the other day was a marine biologist who said that in coral reefs, for example, when fish eat too much from the reef, right? This is something that you need to report, because if that happens more than a certain limit, maybe some decision makers need to take some action to do something with the reef to help with the conservation. So I imagine these things might also extend for wildlife, like for animals and stuff like that. And all of this, I think, will be cameras set up in surveillance setting. A lot of the motion there might be not really interesting, but when something happens.
I mean, possibly if you want to design a system that is also compute efficient, the redundancy might be useful. When I'm watching everyone here, I'm not actually processing the pixels of the full field of view that I have in front of me. I'm shifting my attention, and in any given situation, that'd be true. That is what allows me to kind of be able to process all of the otherwise, available, potentially theoretically available information. I think that might suggest that you might want to ground some of your evaluation based on constraints such as, being real time. And I think there, you will find some pretty complicated and interesting, technical problems or scientific problems that would need to be addressed, where redundancy might just be a win. It might be something that makes it much easier to tackle problems like that.
I think these are very good responses. I think one point I heard from the conversation is probably the reason why video representation doesn't really outperform like image representation sometimes is we don't really ask the right question and evaluate them in the right way. So okay, now we have a question here is like what if like you were to design a new challenge or new benchmark for video understanding next year, and what would be the possible angles or things you want to address in those benchmarks?
I think, we've been doing this every year. I think that my goal is one model that solves all these tasks rather than a single challenge, right? Yeah. And if for people who've been following the Epic Kitchens challenges, I'm super excited that now solutions are borrowing from things from other challenges. So domain adaptation is helping anticipation, which I was surprised to kind of see that this is doing. I think we need one model because we have one model, we have one brain that understands all these tasks. So I think it's time now to do multitask in video. Multitask has been helping in images. We haven't done it yet in video. So I want mega challenge with multiple tasks.
There's probably a lot of space for more self-supervised or, trying to go after training from lots of available unlabeled data in the space of video. I know there's some work there, but that is definitely something I would expect to transpire towards some of these benchmarks that are grounded in specific semantic concepts you're trying to discover. I'd be curious to see, there was, you mentioned work with call, and I remember the work on to colorizing video, and that sort of led to a natural object detection. And that sounds super relevant in the context of tackling, long tail kind of concepts and categories. And I would expect there to be something to do there. And I think a lot of few-shot learning is very much grounded by defining a training curriculum, an upstream training curriculum that leads to really useful, flexible, and sort of actionable kind of representation that you can quickly deploy on a downstream task. And I think self-supervised learning has a huge role to play there. And that's definitely, a concept that's not been as explored as say in single image.
And just to say, despite the fact that we now have large scale models, there isn't yet a model that can take a 30 FPS high resolution video as input, right? So our best models scale down to, I don't know, 300 pixels, and then sample one frame from every 30 frames or 10 frames. That's like the best possible thing, and that's what we can ingest. We're not putting videos in. So claiming that we want temporal understanding is out is tough. It's tough.
So if I had to design a benchmark, I think I would try for something much simpler. I think I would give some videos of manipulation activities, and I would give in the simulation, so they would have an amazing simulator, and I would have people demonstrate, and I would have pixel and part trajectories densely in space and time, and then people would use those, thousands of demonstrations that I would have in this awesome simulator, and their job would be to predict a model trajectories so that they really understand space and time. I think this type of state tracking is missing. I think we're very good in coarse car tracking, but to really, figure out manipulation and fine-grained action and imitation of those activities by robots and so on, we really need to go to more fine-grained understanding. So maybe this is where I would invest my resources.
I keep telling them when there is a simulator that can cut a cucumber, let me know. I'm really looking for that one. Just a simulator that can take a cucumber and produce a video of it being cut into only two. I'm not interested yet in slicing. So when that happens, I think we can do a lot. But if anyone is doing any work on simulators, we're desperate.
I mean, it's good you could combine simulation environments or not. Actually, this is incredible, but people really push better and better simulators, but you can combine tracking on whatever. Even in the real world, I would put more emphasis less on putting action labels on the video, but rather putting dense trajectories of entities in space and time. So I would also hire Amazon Mechanical Turkers maybe to label real videos that cannot be easily simulated.
Okay, so yeah, so I think my next question is a bit high level from I think you all mentioned some of the data biases, especially in human-centric videos. So what do you think are risks of this like algorithm built on top of those data, and what would be the possible ways to address that?
If the performance of models is as bad as is, no risks. Once we solve the problem and we can do models that actually work, yeah, probably there will be risks. Yeah.
That's a cool answer.
Anyone else? Or
Well, I mean, this is not quite a. I mean, your question made me think of something where I've always found that technology for few shot learning made that particularly interesting, which is, to me, it was always a gateway towards having systems that are really adaptive. And what that meant is, it potentially meant that we could correct them also very easily, meaning that if you do find that they're, for any situation, you should, when you deploy a system, you should think about what might be the risks in terms of the deployment. You should have use cases that are testing these kind of limits. And I think if we have models that really are capable of a form of few shot learning, that to me would mean that you can identify these problems and can fix them fairly easily by collecting very few examples of these problematic cases, and it would sort of learn to fix its behavior. That is to me why I find, from a technology standpoint, why I think investing effort into having really good few shot learning methods is really valuable. That means methods and systems that are really flexible, that we can sort of configure for our particular use case when we deploy them. And that would sort of be, if we can really have particularly flexible and good few shot learning methods, I think we can potentially sort of bypass that problem. To the extent that, in any situation, we should have these use cases that we think might be more challenging to be able to catch them before they come about. And if you're able to do that, then it might mean you're able to collect a few examples of these situations to correct and interact with your system. And hopefully that leads to a more robust and safer deployments.
Okay, so due to the time limit, my last question is, as there are a lot of students who are just the first time attendees at CVPR, what kind of advice you give them, if they are interested in this field? So basically, it could be like a suggestions in high level, or how do you do, what's the starting point if they wanted to do a learning from limited videos type of thing?
Find the problem you're passionate about. Keep hitting your head against it until it's solved. Be stubborn. It takes years until you kind of get something going. I think but find something you actually really like. I always, tell them, if you find that your eye is looking at another problem, you're probably not interested in yours. You should be able to get to a point where I need to solve this, and you can focus on it. And then whatever that problem is it's limited learning or video, or you'll enjoy the process, the madness of the process, maybe.
I'll give advice that has nothing to do with limited labels, but has to do with CVPR. I think, find 5 or at least 5 papers that you think are really cool. Go to a poster session, talk to the people presenting, and try to go to lunch with them. Because they're going to be, if you end up working on that problem, they're going to be people you're going to email, you're going to see again, you're going to ask for code and various other things. It's really good to do that, to establish kind of the network of people you can talk to about the problems that you care about.
All right, so we're out of time for the panelists, but are there any questions from the audience? Sure.
I had one, but the chart was much earlier than this, so I think we should not.
No, this one, they rescinded it. Go for it.
So no, I didn't quite catch the name, but you mentioned that in real life scenarios, so for example, like autonomous driving, you need huge amounts of data to make it reliable. But I think that if you need this much data for the model, then it really isn't reliable in the real life, because that means that it needs to see every edge case, every scenario. And then in real life, we'll see some value with, I don't know, red umbrella instead of blue one and run straight through. So don't you think that means the models aren't really ready for the real life?
So yeah, so I think of
So if you could just repeat the question.
Oh yeah. Okay. So I guess the summary of the question is that since some safety critical applications such as autonomous driving require so much data, so does that mean it's actually unreliable? So I think there is no simple answer. Of course, everyone knows autonomous driving is a very difficult, challenging problem. We're still in the process of solving it. We can run the very good successful demos in many cases, but there are also very challenging scenarios. However, I think I kind of maybe disagree on the point, because as a human driver, we have a lifelong time to learn from lots of data. So if you are requiring, so basically, we care about this generalization. Everything is about generalization. And if you care about generalization, there are two aspects at least. One is like you need to have enough knowledge or data support to make the model be robust. So that is why we talk about large-scale data and self-supervised learning, because once you have a lot of data, it's not scalable to learn with labels. So that's why we care about self-supervised learning. But on the other hand, it's like the model should be robust enough, given limited data. So how can we make the model even more robust if we have a certain amount of data? But to your question, actually, if you think about human learn all these things in a lifelong time. So I think it's not very fair to say, okay, machine should just learn on very limited data and it should be able to generalize very well. The world is very complicated and there will always be long tail cases. It's very difficult to avoid. But that being said, a lot of the things can be solved through engineering and system design. Like that's why we have LiDAR, we have all these sensor redundancy. So things can be alleviated, but I still think it's a right way to let the model see enough data, and time and time again, it has proved that this large-scale data, large-scale training is the main driving force for the visual community to move forward. So I believe in that.
All right, so anyone want to jump in there, or Katerina?
So maybe one tiny little point is that I mean, we've heard a lot that we need a lot of data, which is absolutely true. But of course, data shine within a model. And when we say all things will emerge on their own, I was just reading the paper that Hugo suggested us to read from DeepMind. It turns out that things emerge on transformers that did not emerge on RNNs. And you know, transformers are, some colleagues of ours came up with it. So I think amazing models will come out from the community. And I think just putting too much trust on whatever is out there may not be the right thing to do. It's okay to try. Of course, the discrete jumps are much more rare, like MLP and then CNN and then transformers. So your chances are you may spend 5 years trying to come up with a better model and may not. But it's a good, you know, place to fight. So it's not only the data. I can feed data on some really dumb model and nothing is going to come up, right?
All right, so we are out of time. So let's thank our panelists again.
So now we have the closing. We will announce the paper award.
Now I'm going to proceed with the closing remarks. First, I'll announce the sponsor, the awards, the Best Paper Awards. We have a Best Paper Award sponsored by NVIDIA and also for, with the GPU and also with money by ServiceNow and Unity. Best Paper Runner-Up, which also is money from ServiceNow and Unity, and another runner-up also from ServiceNow and Unity. So the first honorable mention award is for Saurabh Gupta for VTOL, Vision Transformer for Weakly Supervised Object Localization. Can Saurabh come? Is he here? No? Okay. So no coming, no money. No, I'm joking. So the next one is for Karim Girgis. Okay. Finally, the Best Paper Award is for Zheng Feng Lai.
Yeah. Hello, I'm here. Thank you.
So finally, thanks again to all the organizing committee. And thanks a lot also to all the invited speakers who made this workshop so great. And hope to see you next year.
Thanks, everyone.
To receive the awards, please send us an email. We don't hear you. 1 second.
Hello, can you hear me now?
Okay, now yes.
Yeah. So my colleague is there from Robert Bosch, Michael Herman. He's already there in the room. Can he pick it up for me?
One second. Now, can you talk now? Can you talk again?
So my colleague Michael Herman is there. Can he pick it up for me?
Problems. 1 second.
Mike.
That's my colleague. So I can pick it up for you.
What about?
Yeah. Yeah.
1 second. Let me disconnect this and see. Let's see.
Perfect. Great. So you're going to sign it, and I will. Hi, Karim, can you hear me?
Yeah, I can hear you. I can hear you, yes. Can you hear me?